Very high interest for Turkish culture through the centuries, and it's really a pleasure to be here to present my results that was got during the pandemic time, this last 3-4 years. The story is it was very surprise also for me, the story I'm telling you. And I will try to share with you the surprise I got. I remind you to contribute to the proceedings. This conference has been really a turning point in the history of study of quantum mechanics. There's been a lot of majority of people that start to think in a different way, looking for complexity and real quantum materials, both from the point of view of technology and the fundamental physics. So the proceeding should be a very important moment in the history of science. So the story I'm speaking about is a long story. It started in '87 when I was studying valence fluctuations and heavy fermions materials. In heavy fermion materials, you have a narrow band and a wide band. And I've been lucky to have, I guess, a supervisor when I was postdoc in Frascati, Ugo Fano. And Ugo Fano wrote the paper in 1935 on the configuration interaction between a localized and delocalized states. So when I started to do 50 years ago, the first beam line in Frascati, with Ugo Fano, we said we have to show to the community the fact that with the X-rays, you see local atoms where they are. So you don't know anymore the K-vector, you know the position. But in quantum mechanics, you have to use an X-ray microscope to see the position of atoms and to see the clouds. So when after from January we went in Bangalore in '87 and everyone was speaking about valence fluctuation. Anderson gave the first talk, and then in the famous New York March meeting, a paradigm was established that ITC is due to the strongly correlated single gap Hubbard model. So on the contrary, we were thinking always in the sense that you have two components, localized and delocalized states. And we proposed in 2015, in 1993, that we have to shift from the paradigm of a single band Hubbard model to a quantum manipulation of two-gap superconductor, multi-gap superconductor, in a complex materials made of localized and delocalized states. And we have seen that in this work, in this meeting, we had a lot of study of network quantum dots, quantum wires, and quantum wells. And we think that this is the real quantum world where superconductivity can emerge on the macroscopic and in the different time scales. Then was only 2 years ago, 2-3 years ago, that with my collaborator Antonio Valletta and Maria Vittoria Mazziotti, for years we were calculating a composite material made by insulating a metallic pattern using the Schrödinger equation. Then I realized that in the Schrödinger equation is not a quantum, it's not a real quantum because there is not the spin. there is not Fermi energy in the Schrödinger equation because electrons have no spin. So there is no Fermi energy. So in the calculation, in the computer code, you put your Fermi energy by hand. And so I said, why? We should use a Dirac equation. So it took a few seconds to say, but it took about 5 years to have a computer code that solved the complexity of a heterostructure with the Dirac equation. It's very strange that in solid-state physics, we teach that you have to use, for electron in a band, you have to use the Schrödinger equation. But then you have no Fermi energy. You have to put by hand. And then you teach metals. And I say, this is crazy. So we have, like we do experiments, we have to use theory as it is, the mathematical tool, and it should work exactly. It took more than 4 or 5 years. And then when you put the Dirac equation, you have the spin. But the spin feel the Paschen-Bach effect. If there is an electric field, when Wenzel and Kronig discovered the spin, and Ulbeck got the Nobel Prize, it was because an electric field modified the interaction of electrons. And so you have an electric field. If there is an electric field, you have what we call the spin-orbit splitting. And then you have an energy scale. And then this energy scale of the spin-orbit splitting can be of the same order of magnitude as the Fermi energy and the pairing interaction. What happened? So that was a very interesting. So we solved the Dirac equation, and we have the computer code now that we can give to everyone. And tried to see what happened with a complex material, where you have a patch of insulating and metallic, like has been presented by Erika Karlsson yesterday. And we also observed that you have localized and delocalized coexistence metal insulator materials. So the fact that you can have, in superconductor, you have insulating and metallic wires was discovered by us in 15 November 93. We made the patent, we published the paper, we sent the letter to Nature. And our date is 15 November 93. In 15 November 93, by X-ray spectroscopy diffraction, we found that in the BISCO you have wires that are order of 1 nanometer that are metallic, and then we have wires that are insulating, no doped, and these are order 1.5 nanometers. So all the periodicity is order of 2.5 nanometer. So after 15 November 93, we have more than 30 years. We did the first resonant copper X-ray diffraction with Radaelli on BISCO, and we have seen really the structure of BISCO, and you have this doped region with the distorted lattice, and the regions with undistorted lattice. You see, this is completely flat, undistorted, and this is distorted due to the electron-lattice interaction. So all the details were published in Physical Review B, and has been always confirmed by many people. Then in 2000, was a scientist that told me, but your friends are crazy, because they have the phase diagram of cuprates with the density, with doping. Density means the volume, but they know the axis of pressure. How you can have a phase diagram in thermodynamics only with the temperature and volume, without pressure? So you have to introduce the pressure. If you introduce the pressure here, you have to introduce the strain, and you have the strain, you have a critical point in the phase diagram, where you have what Erika presented yesterday, phase separation. At the critical point, you can have a critical opalescence. And so that we worked on this work also for iron-doped superconductors. And then we arrived to the idea that you have a patch of metallic quantum dots, quantum wires, quantum wells, and then they condense by, it is called Josephson junction at zero voltage, but actually it was discovered by Majorana in 1933 when he was visiting Heisenberg. So you have exchange interaction, and the exchange interaction make a condensation of this metallic and the insulator. So the electrons go everywhere, go both in the insulator and both in the metal, and you have a quantum entangled many-body effect. What Majorana say, quantum materials, quantum condensed matter, he say very well in the paper of 1933. Quantum condensed matter appear when the wavelength of the electron is the same size of the size of the material. So the proton or neutron should have the wavelength that are the order of magnitude of the neutron size. So that's what always Fano told to me, that if you want to have quantum mechanics, you have to look for a case where you have the wavelength of the electron is exactly is order of magnitude as the size of confinement. And then you can have a different class of confined particles, and so you have a subband or mini-band or atomic-like effect. So how I can realize a case where we are nearly a heavy fermion case, where you have a delocalized band and a localized band, and you can tune the localized and the delocalized, the large Fermi surface and the small Fermi surface, a flat band and a steep band. By Lifshitz transition, I met Lifshitz in 1979. He was a very nice person. And he pointed out that there is a phase transition of 2.5 order when you have a Lifshitz transition, when a new band appears. But actually, Kugel, without me, reanalyzed the story. And then you have a first order phase transition if the electrons are interacting. So if you take a Fermi gas or non-interacting electron, at the Lifshitz transition is a 2.5 order of magnitude, or 2.5 phase transition, so it's very weak. On the contrary, if you have a strongly interacting particles, you have a first order phase transition. Okay, so this, to make short the story of my life, we focus at the case where you have all the story came when you have a small Fermi surface and a large Fermi surface. This was the theory of Schul, Matthias Walker in 1959, 1 year, or Moshkalenko, 1 year after BCS. This was the fermion-boson theory that T.D. Lee proposed, and actually was proposed first by Tomonaga for the pion gas in the nuclear matter. What was the surprise of these last 20 years was that in this case, all the electrons that are free, if you have a strong boson condensation, they all go down, and this is very small. If here nothing happens, because very little thing happens, because you have a small perturbation of the exchange interaction, and the perturbation should be small to have a resonance, like Huygens pointed out. If you have two pendulums, we have to put a weak interaction. So for a weak interaction, nothing happens. What is interesting is where, on the contrary, you have a large Fermi surface and a small Fermi surface that is not so small, is quite large, a little bit large, in such a way that here you have the BKS-BC crossover. So this is a regime where superconductivity appears. So we claimed at this point for 20 years, and in this case, it still is not so clear for the community that you have two gaps, and the gaps can be very different, but there is a single TC because you have entanglement between the two states. So In our patent of November 93, we presented these figures. These are the claims of the patent. The patent was United States, Europe, now is nearly 30 years old. Then you can have a superlattice of wells, a superlattice of wires, a superlattice of quantum dots, and a superlattice of quantum dots, quantum sphere. So you understand my pleasure be here at this conference where there is many, many talk about superlattice of quantum dots for quantum optics, superlattice of wires, superlattice of layers. So we are very happy that finally this scheme come up. So we studied a lot all this story, and Perali made a theory very well, very fundamental, where you have that the maximum TC, you see, as a funnel-like resonance. So you have when you have a back crossover, you have a TC go down, then TC go up, and then come up. So you have a maximum TC, you have a room temperature superconductivity or high TC superconductivity in this intermediate range, where you are moving your chemical potential near the bottom of the appearing band, but not so much. So the energy should be of the order of the boson energy that you exchange, or the interaction, or spin-orbit coupling. And now we arrive after this introduction to my results I present today. So it's possible that we tune the spin-orbit coupling in such a way that we keep our system in this case. And in order to do that, you have to solve not the Schrödinger equation, but the Dirac equation. Why you need to solve basic quantum mechanics? You cannot use type banding models, because in type banding you make approximation. If you want to know some fundamental point in quantum mechanics, you cannot make approximation. It was Fano told to me. You cannot make approximation. You have to calculate the quantum interactions with the 20, I think now we are about 30 decimals, because these numbers go in the denominator during the iteration, and your computer says 0, and then you have no results. So you have to have a precision of the computer huge. In such a way, you have to calculate all the steps with the 25 decimal precisions. Okay, so the simple idea, I speak about quantum wells because it's the most simple case. The fact that a system of quantum wells is superconductor is under the eyes of everyone. These are electron-doped superconductor, metal insulator. These are bismuth. This is magnesium diboride. So you remark that we predicted the magnesium diboride superconductor before the discovery of magnesium diboride. The patent is 93, and magnesium diboride is 2001. Then intercalated graphene, iron-doped superconductor. So what is the simple quantum system that we can attack from fundamental physics or quantum mechanics with Dirac equation? Is superlattice of layers. Superlattice of layers is simple. You have an insulator, and you have a metal. So you have a potential well, a one-dimensional periodic potential. You have a metal, a potential barrier that is an insulator, and then you have electrons that run because the size is small. So you have to calculate the tunneling from first principle. You cannot put a number like that. So you have to calculate really the potential barrier. So we selected a barrier of order of 500 milliV. That is common in semiconductor and also in cuprates. We consider the potential barrier of order 500 millib, a periodicity of order of 4 nanometers. So from 4 to 2. But we can go up to 5, 10 nanometer. So if the barrier is 3 nanometer, in the type banding approximation is like infinite. But if you calculate exactly, then it's not. You have a transparent, you have a proximity, you have what is called the interface superconductivity. And then you go to to the Lipschitz transition. For a superlattice of layers, you have a cylindrical Fermi surface. Then you have an appearing Fermi surface with the 3D small sphere. Then you have a Lipschitz transition. This is without a spin orbit. Now you introduce electric field and spin orbit, and then you go to see what happened. If you put a spin orbit interaction, you know you have a Rasba, you have velicity, you have a negative and positive velicity, and then you have a two Fermi surface that have a positive and negative velicity. And what Rasba and Gorkov did, they are very nice person, but they realized that they cannot study physics in this regime here. They have to study the physics where you have a large Fermi surface, where you have a two Fermi surface with the positive and negative velicity. And they made a good theory, Rasba and Gorkov, fantastic work, where the spin orbit coupling is much smaller than the Fermi energy. No, spin orbit, yeah, it's much smaller than the Fermi energy. You have a Fermi energy, and then you have a spin orbit coupling, changing everything, but very low. So the Fermi energy should be very high, but when very high, the Fermi energy are two Fermi surface, and so you are in the regime of two large Fermi surface. So you are in the regime of a BCS regime. On the contrary, Perali theory that made worked in this field for nearly 30 years, pointed out that you have to go in this regime. But when you go in this regime, you have to find Bianconi, Mazziotti, our group, that they, okay, in order to go here, you have to go to fundamental physics. You cannot make any more approximation because Fermi energy is not a large parameter. And then you have to change your Hamiltonian and introduce the Rasba Hamiltonian, where you have a parameter alpha that measures the effect of spin. But the effect of spin is due to the Dirac equation. And then in a superlattice of a layer, Maria Vittoria Mazziotti is a great scientist. And there are not many women that do fundamental quantum physics, and she's really talented, incredible, and she dedicated perhaps the master thesis and the PhD thesis and 2 years of postdocs. Now she works on this field by the last 5 years, 6 years. And then you have two bands in the superlattice of a layer. You have the first band and then the second band. And so you have this kind of band structure pattern. When you increase now what you can do to see the interaction, well, you do like a Paschen-Bach. Paschen-Bach calculated the effect in the lines of atoms as function of the electric field. So you change the electric field. You change the electric field, and you modify everything in the bottom of the spin orbit interaction. It's an internal electric field. So in the insulator, in the potential barrier. And so you have increasing the spin orbit interaction. You have a strong variation of the density of states. But density of states is not the relevant point in the history, because everything is controlled by Majorana exchange interaction. In the Majorana exchange interaction, you need really the wave function and calculate the overlap of the wave function in the real space, not in the K space, in the real space. And then you find that everything changes. The Lipschitz transition is completely unusual. You have a variation from I touched it. Okay. Okay, in a superlattice of layers but the superlattice of layers is a model that can be applied for a large variety, but you have insulator and metal. you have this new band to Rasma. They are very beautiful, and so when the new band appear, where you are in the back regime, you have donuts. You have donuts, and then the donuts evolve. They touch. There is a circular number of critical points of the Dirac point, but the number of Dirac point is not a point, but is a circle. And then you have this negative and positive velocity and negative velocity. And then you have the other bands, the lower band. The other electrons have two large Fermi surfaces. So the paper is in PRB, it's very clear, we have all the details. And okay, you go on to, we solved both with type banding and, so okay, you go through all the quantum mechanics definition of the gaps, and you see, we use Bogoliubov quantum theory perfect, without approximation, where each gap depends on all the other gaps. So in a multi-gap system, when you have this kind of four, like here you have a four Fermi surface, each gap in one point depends on the gap in the other point. So it's completely entangled. So the system is only one, and the computer code should, now the pairing interaction is k-dependent. So you have a distribution of states where they are k-dependent. Okay, so you have a very complex system, but actually, what happens is that the gap, the superconducting gap, is huge in this circle of critical points. And look at TC. This is 150 Kelvin. Pairing, coupling, Cooper pair, the coupling for the boson is 0.225, 0.2. In the other band, the coupling is 0.1. So TC in the first approximation should be 1 Kelvin, 2 Kelvin. Then you calculate it without trick, and you get 150 Kelvin in the weak coupling with exchange interaction. There is no trick. If you increase the spin orbit, the electric field and the spin orbit interaction, TC go to 160. So you have at the beginning is a small variation. There is a large, then it's going up. You see here the resonance. This is the fun of resonance that is going up. Okay, then you have the pairing inside the single band. You have inside the single band, you have exchange of a boson. And then G is the coupling for the boson standard, we can call Cooper pair, but you can call anything that is intra-band pairing. These are the number in the BCS theory, 0.15, 0.3, 0.35. And this is a Lipschitz parameter that tunes the fun of resonance. You see, you have 150 Kelvin in a specific region, not everywhere. So you need that the chemical potential and the internal coupling and the exchange interaction is determined by geometry. But you have these two parameters. And in the phase diagram of cuprates, this corresponds to doping, because you change the chemical potential. And this corresponds to strain, because you change the coupling. So you have a specific, in the phase diagram of cuprates, generally people does this way, or you can cross it in many different ways. So the most recent work we did now, a paper is accepted in a journal Applied Physics, so it will appear in few weeks. The problem is, which is the pathway? If I have this region where I have TC go up, we reach 160 Kelvin without pushing any parameter out of the limit of the validity. If this, actually we got 0.4, but we think that 0.4 we can have some instability. So at 0.3, you can go very quick, you can get standard superconducting. Non-superconducting, you take a superconductor and you make a lattice and you get amplification. Okay, so we studied this case, and we reconsidered the story of magnesium diboride, because magnesium diboride is very simple. Magnesium diboride, you have a Cooper pair in one band, and you have exchange. And then we took the paper published in Physical Review in 2008 with all the parameters of magnesium diboride, where we can derive eta, G, all the experimental numbers, and TC. And then to make the story short, okay, we recalculated all the story. Maximum TC happened here at this critical point of circular Lipschitz transition. And then we found that in a system like magnesium diboride, the superlattice of layers with the intraband coupling, electron-phonon coupling, the path is this one, the path. When you change aluminum by aluminum at place of you follow this place in this resonance world. And changing spin orbit coupling, you have these different pathways. When you plot in a single axis phase diagram, you see that TC, look here, look for example here, you see TC is maximum, not at the maximum of the density of states. Generally, you think that the TC is controlled by the density of states and coupling. When you introduce the exchange interaction, this is no more true, because all the dome is controlled by Majorana exchange interaction. And then you have that the maximum TC is determined by this kind of pathways, where essentially we don't go to the, here you have a back regime. This is the Fermi regime of the second band, but there is a back BCS crossover that is followed as we expected, but it was a surprise. So we stayed for 3 years understanding where the pathways when I put pressure in the hydrides, or when we put pressure in cuprates and TC increase, which is the pathway. So, and now we found that taking magnesium diboride as inspiration, without the magnesium diboride, the chemical pathway is this one. And then you see that the density of states has nothing to do with the TC. So this is fundamental theory, and these are the case of magnesium diboride. It's exactly this experimental data of magnesium diboride. So you have this kind of regime. So now there is a paper by Shen on the cuprates that found that the dose and TC is completely decorrelated, and this is quantum mechanics calculations. I don't know my time. 5 minutes. Okay, so I'm near the end. So this gives me the possibility to come back a little bit and to share again fastly the story. I try to repeat because the introduction was very long. So let me go back to essential point. So the essential point was this one. So if you have a complex material, you have a Lipschitz transition for the appearing band. You have this corrugated Fermi surface that appear. But if you put a spin orbit coupling, then this topology of the Fermi surface is much, much more complicated. This was the case that was considered by Ras by Gorkov. So the case, Ras by Gorkov, the case where you have too large Fermi surface. Actually, when you go down, there was no theory, nobody did the theory. It's too complicated. You have to spend, so Vittoria took perhaps 3 years, Vittoria and Valletta. They are really, Valletta is my collaborator, co-author, and his job is working in the CNR, and he made a quantum calculation for all for quantum technologies. So, and then he is very strong in computer science, and he made this fantastic program that works. In order to solve this divergence of the quantum mechanics, he found a paper published in 1895. Yes. So we found in order to overcome all the problems to find. They stopped for 6 months because we increased the number of. Okay, I cannot tell you the story. It was very dramatic, like to build a beamline and synchronous radiation. And then, but when you go to the raw energy, you have this beautiful topology coming up. And then you see that what play a very important effect is that the two bands that interact, it's a two-gap superconductivity. But the two gaps have a different symmetry, because one is a 0, is a S, and the first is P. So you cannot have hybridization between the two gaps. This is very important, because if you get hybridization, then you have a single band material. In order to have a two-band materials that works, should be some symmetry forbidden mixing of the orbitals, in such a way that the two gaps remain always well defined. Because if you make hybridization, like in heavy frame, if you make a hybridization, then everything becomes more trivial. This density of states was calculated by a different group, but nobody understood why you have this kind of singularity. This kind of singularity is nothing to do with it looks like a one-dimensional material, but it's not. It's due to the topology of the Fermi surface. And all the tricks come from the interaction. In the interaction, you have this exchange term, and to use, you cannot get with any. And all the story, all you have to spend time is you have to get this self-consistent gap, because each gap depends on all the other gaps. And then the coupling is K-dependent and energy-dependent. And then this is the K figure that determines the resonance, is the distribution of the coupling in the K space. In the two bands is different. So the story is. The story I want to send a message is that perhaps I come back to the symmetry, there's been several talks in this meeting where the symmetry is determined by the symmetry of the pairing, if it's a D wave, S wave, is depending by the lattice symmetry. So the lattice symmetry determines the symmetry of the wave functions. And then what you get, the symmetry of the gaps, originate from the symmetry of the lattice. So the manipulation by technology of fine-tuning order of 3 nanometer. 3 nanometer is a perfect. We found that 3 nanometer is the right size to create a quantum device that have a TC can go up to 150 Kelvin. You have only to adjust the parameter with careful. I think that in this conference I've seen a lot of technology that now we are in the point that we can do. 30 years ago, people said this is impossible. Also for technology is important the fact that you have states due to positive velocity and negative velocity. For two bands, you have 4 different wave functions. And then changing the small parameter, you can change the balance between the different gaps. This is gap 1 and gap 2. And then you have a deep complex butter, but everything can be, you can create by computer the superconductor you want. That's what I say. You can create with your computer, if you have a good nanotechnology, that you control the size of the wires or the layers with the order of 0.5 nanometer. You can make the things of 1, 2, 3 nanometer. You can calculate exactly, and you will get exactly what you calculate. So this is a procedure for material design, because there is no tricks. So you just put the parameter of your materials that you put, and the architecture, the symmetry of the architecture. Okay, so this is my message. There are 2 papers. One is in Physical Review B that already is out, and the one will appear in a journal of Applied Physics. Is a special issue dedicated to women making impact in science. So finally, we show that theoretically and numerically, you can calculate the electronic structure of superconducting property of quantum layers with spin-orbit coupling, modulated by ferroelectricity because you change the electric field. Rasbach spin-orbit speed induce unconventional Lipschitz transition of the Van-Hoff singularity, and the negative velocity states have an unusual Van-Hoff singularity of extended circle of critical point. It's like when you have a graphene, you have 1 point. Here you have a circle of direct point. And the TC go up, TC increasing the radius of the circle. When you increase the radius of the circle, you go from 40 Kelvin to 150 Kelvin. So the number of critical points make up. So these results provide the roadmap to design a new ITC material, tuning ferroelectric effect, a lattice parameter, and practical application. I think we are now at the point where it's possible to make TC as close to room temperature, remaining in the weak coupling regime. Thank you for your attention.
Thank you very much. So the paper is open for discussion. Maybe one question. We have time. Yes, please.
Thank you, Antonio. It's a very nice presentation. I may have missed something that you were presenting. Is it possible to make a comment that if even we reach room temperature superconductivity, the wave function could not be larger than the size of an electron eventually? The wave function representing the electron cannot be larger than the size of an electron.
The size of
an electron.
Can you
in
repeat?
Physical terms, yes.
Can you repeat that?
Yeah, well, okay, let's put it that way. The coherence length would be much smaller. And even if we reach room temperature superconductivity, that may not find any application possibilities.
No, I think I refer also to the paper presented by in the spin-off yesterday on the. So in the multi-gap, you can have a very small coherence length in 1 point, and the coherence, you know that the coherence length is related with the gap. Is so then in another place you have another electron that has a very large coherence length, but they are completely entangled. So the quantum state that you create has not a small coherence length or a large coherence length. We have many coherence lengths. In the computer code, embed all the computer length possible, all the gaps. many gaps in the gate space and the real space. And then you obtain TC. So TC is a scalar. So it's nothing to do with the gap. But it is only in the BCS approximation. They say that this is a single band, everything is spherical, and so on. But it's, you know, BCS, I don't speak badly about BCS. BCS was a great discovery because they discovered that a particle, infinite wave, so the K vector is very defined, can condense in a condensate, making with very, very small interaction. So I think the important paper is the Nambu-Iono-Lasino, so that show that you have a massless particles that create, the gap is like the mass of the particles. So a massless particle that create a mass. But when you are in our world, like when I think of biological system, when I think about Antonio Bianconi speaking, I have a cell that, well, atoms are all dense, all collected. And if a cell don't work anymore, I can die because make percolation and I can die tomorrow or this morning. Because it's just enough one that everything can collapse. So it's the same in quantum mechanics. In quantum mechanics, you can have your DNA, your RNA, but they all have to work together. So here the same. All the gaps, you have many different gaps, many complicated. You can have a pattern. I study the other side of my group with Gaetano Campi and others. We study this pattern scale-free. When it's scale-free, it's perfect, because when it's scale-free, you have a strong in a critical opalescence. Everything is, you can have a disorder and order in the same time, because now you have path waves that are infinite in a very disordered material. So this is a different talk. But it's related. So, but our mind, when we think about quantum mechanics, have to change. It's nothing to do what Galileo said or what Aristotle. The idea of the atom of Democrito have nothing to do with our point of view of the world today. So we are in the world of quantum mechanics, very complicated.
Okay,
Thank you.
Yeah, we are over time, so we have to move on. So let's thank Professor Bianconi again. Okay, so the second plenary talk of today is going to be presented by Professor Pietro Gambardella from ETH Zurich. And the title of the talk is Manipulating Chiral Spin Textures by Electric Currents.
So, good morning, everybody. I hope you can hear me well. So I'd like to start by thanking the organizers for the invitation to come here, Professor Geinzer, Jan Avci in particular, and also the people who contributed to the work that I will discuss today. These are students and postdocs in my group at ETH Zurich, and also we have collaborators from the Paul Scherrer Institute, the group of Lara Heiderman, and Marta Rossell at EMPA, and then our collaborators at IMEC, Kevin Garrello, Sebastian Cohen, and at the University of Salamanca, Eduardo Martinez in particular. So we will change subject with respect to the first talk and discuss the manipulation of spins by electric currents. And so this is roughly what we call spintronics or spin orbitronics nowadays. And sometimes I ask myself whether we are doing anything new in this field, right? And then when I listen to superconductivity talk, I'm kind of reassured, because superconductivity has been around for more than 100 years. And I think we're still trying to understand it, still trying to improve it. So now, if we look at certain concepts that are around in spintronics, right? One famous one is the domain wall racetrack memory, where information is encoded in magnetic domains, for example, up and down, as you see here. These domains can be injected and then shifted across a so-called racetrack, which is a stripe of a thin film magnetic material, and then detected at certain positions, right? Now, this idea is not new. In fact, it turns out that in the late 60s, it was already explored precisely in thin film systems, although not so thin, where domain walls were nucleated inductively and then shifted along predetermined magnetic stripes on a thicker film by a combination of either inductive, so Ørsted fields, or rotating magnetic fields. And also, if we look at skyrmions, so skyrmions are very fascinating chiral spin objects where the magnetization swirls around with well-defined sense of rotation in different systems. So these skyrmions can also be moved, in particular by electric currents and spin orbit torques. They can be generated by current injection. They can be detected by Hall effect, magnetoresistance, or optical Kerr effect, for example. Now also here, this is a concept that is quite similar to magnetic bubble memories that some of us may remember from older times, where magnetization was encoded in these cylindrical domains that span the whole thickness of a film. And these domains can then also be nucleated inductively and shifted across different locations of a magnetic layer with superimposed electrical and magnetic elements on it. And this type of memories actually were fabricated, commercialized. There are also personal computers that use this. I think the last one was in 1985. So, and also if we look at magnetic random access memories as we think of them today, right, we have an array of magnetic tunnel junctions where information is encoded in the alignment of the magnetization of the free layer relative to a reference layer. Now, this type of systems are also reminiscent of the famous ferrite core memories that were the most used type of random access memories for about 20 years here. And so here also the information was encoded in the magnetization of a toroidal ferrite core, and it was written and read by current, by electric current. Now, these systems actually, so there were practically 90% of random access memories in the 1970s, in the early 1970s, were made using these systems. This is the memory that went to the moon with the Apollo system, and it survived in the space shuttle up to the 90s because people were afraid of changing systems that would introduce errors. So are we really doing something new in this field, right? And the answer is yes, right? So one point is that we're using different effects to read and write magnetization. And another more practical is that when we look at the performances of these memories, we see that such a memory here, the typical dimension of a magnetic bit is a millimeter in size. This is a picture taken with my phone of such a memory. And so to store 32 kilobits, you need a cubic feet of this type of arrays. Right? And these memories could operate up to a megahertz clock cycle frequencies. They need very large currents for being read and write of the order of an ampere. And so if we compare to what we can do today with magnetic tunnel junctions and integrated on CMOS circuits, then we see that we are indeed doing much better in terms of integration density, scaling, switching speed, and also the power that is required to operate these memories. So if we look at the current architecture of a computer, right, where nowadays magnetic materials are basically used for mass storage, so hard disk drives that store terabytes of data, it is indeed possible to replace some of these higher level memories with magnetic equivalents. The advantage being that some of these, so all of these magnetic memories are non-volatile, which implies a saving power. But also some of these memories are more scalable, for example, relative to SRAM, for example. So there are advantages in using spintronic memories, although there are also many challenges. So it is right now too early to say whether this will happen on a massive scale. Right, so what we are concerned with today is the fact that we can manipulate the magnetization using spin currents and orbital currents, which are generated by charge currents. And so this relationship between the three different types of currents is actually very interesting also from a fundamental point of view. And then if we want to manipulate the magnetization, then we'll see that there are spin textures that are actually better suited to respond to current-induced spin torques than others. And so it is also important to understand this and see how they can be manipulated. So the interaction between a spin-polarized current in a magnetization is well known. We can think of a current, an electric current with spin polarization, so a majority of spins polarize in one direction, entering into a ferromagnet, and this is equivalent to a flux of magnetization that enters into the ferromagnet. And once this spin current enters into the ferromagnet, then the spin current can be absorbed, and that will transfer to the local magnetization a certain amount of angular momentum, and this gives rise to a spin torque. Now the point is, how can we create a spin polarized current, right? And so the most used and famous case is that of polarizing an electric current by letting it flow through a magnetic layer, where the difference in spin conductivity between spin up and spin down electrons polarizes or partially polarizes the current. And then if this current flows through a non-magnetic spacer into a second magnetic layer, it can transfer the spin polarization to the local magnetization of the second layer, and this gives rise to the so-called spin transfer torque. And this is effectively a transfer of spin angular momentum from one layer to the other. Right? And now the advantage of using this type of system is that at the same time that you can manipulate the magnetization of this so-called free layer, you can also read out the magnetic state, because the parallel and anti-parallel alignment have low and high resistance respectively. But there are also alternative ways to generate spin polarized currents, and these have to do with spin-orbit coupling, which promotes the conversion of a charge into a spin current and vice versa. And there are essentially two types of effects: those that induce spin-dependent scattering, like the intrinsic and extrinsic spin Hall effect, and those that induce a homogeneous spin rotation, like the Rashba-Edelstein effect. So the Rashba-Edelstein effect that we've also briefly seen in the previous talk occurs when we have electrons flowing at the interface of a material with surface inversion symmetry, asymmetry, sorry. And in this case, there is an electric field at the interface of a material generated, for example, by charge transfer between two dissimilar elements. And this electric field is then seen by the flowing electrons as a magnetic field due to a Lorentz transformation that has this V cross E orientation, so it's orthogonal to the current and to the electric field itself. Now this effective Rashba field then generates a spin polarization along its direction. And so this leads to a homogeneous in-plane spin polarization. Spin Hall effect is also well known. This occurs either due to extrinsic effects of scattering by charge impurities, very similar to Mott scattering, or to intrinsic band structure effects related to barrier curvature, which acts as an effective magnetic field, spin-dependent magnetic field in K-space. And so electrons that are flowing into a material with strong spin-orbit coupling are deflected according to their spin direction towards opposite edges of the sample. In this case, it tries to an accumulation, to transverse spin currents and accumulation of spins at the interface of the conductor that occurs on a length scale that is material dependent. This is the so-called spin diffusion length that, for example, in platinum is of the order of a few nanometers. Now, the parameter that we use to characterize this effect is the so-called spin Hall angle, which is the ratio between the spin current and the charge current in charge units. So it's an A-dimensional quantity. And for platinum, we get numbers in the order of 10%, which means that we can convert a charge current into a spin current with an efficiency of about 10%. Now, these effects can be detected directly. So this is an experiment that we did some years ago where we had a very simple structure, so a platinum Hall bar of, say, 5 to 100 nanometer thick, and a scanning magneto-optical Kerr effect microscope where we focus the laser beam onto the surface of this Hall bar. We scan the laser beam across it as we inject an AC current in this Hall bar. And what we see is that apart from the optical reflectivity, we can measure the Kerr rotation during current injection. And indeed, we observe a non-zero signal. This is a longitudinal MOC that tells us that we have spin accumulation in the plane of the sample. And this signal scales with the amplitude of the current as expected. So now if we want to use these effects to manipulate the magnetization, what we usually do is to deposit a magnetic layer on top of a non-magnetic conductor where either a spin Hall effect or Rashba-Edelstein effect are present. And we exploit the fact that the spin accumulation at the interface of this material will eventually diffuse into the magnetic layer and give rise to torques. And just by symmetry argument, we can distinguish between two torques, two directions orthogonal to the magnetization, which we call then the damping-like torque and the field-like torque that act similar to magnetic damping or to a magnetic field. Okay. And we can also consider the effective fields that correspond to these torques. So these effects can be used, for example, to switch the magnetization of a single ferromagnetic layer by injecting current pulses into a planar structure like this. So we have, again, a platinum Hall cross here with a cobalt dot, just less than a nanometer thick, perpendicular magnetization. And if we inject strong current pulses, we can reversibly switch the magnetization between up and down due to the action of these torques. So this works quite well, and in fact, we can include these effects in magnetic tunnel junctions. Here you see one that was fabricated at IMEC, where we have a cobalt iron boron free layer, MgO tunnel barrier, cobalt iron boron reference layer, and a tungsten bottom electrode, where we can pass a current and generate, by a spin Hall effect, we generate a spin orbit torque. And so if we then look at, we can then inject current pulses in this structure and observe the switching. Now, the interesting thing about this type of devices is that they're actually three terminals. So we have the bottom SOT electrodes for current injection, but we also have the top electrodes for readout, to read the tunneling magnetic resistance, which can also be used to inject the current and therefore apply a spin transfer torque on the system. And as we apply a voltage to the top electrode, we have another effect, which is heating of the junction itself, and also so-called voltage control of magnetic anisotropy, because by essentially electrically gating the free layer, we are changing the charge distribution and the magnetocrystalline anisotropy in this system. So all these effects can in fact be used together to improve the switching properties of these systems. Here you see an example of measurements done on such a device where we first just pulse the current through the top electrode. So this is spin transfer torque switching, where you see that these are single shot time traces of the magnetization in the free layer. And that tells us that the switching times are quite random, in fact. Right? But if we then switch from the spin transfer torque to spin orbit torque, we also get quite broad switching time distributions. But now, if we start applying the voltages and current in such a way that these different effects that I mentioned before combine together in a constructive way, we see that we are reducing strongly the distribution in switching times, and also the time it takes for the magnetization to reverse. And we can indeed squeeze these times by a very substantial amount in the structure. Okay, and so these are the switching distribution in terms of so-called incubation time and transition time. We will see later that we associate this incubation time to the time it takes for the current to nucleate a domain, and this reversal time to the time it takes for a domain to propagate across the structure. And so we can essentially switch, if we crank up the currents and voltages in this system, we can switch in very small times, and we're essentially limited by the bandwidth of our measuring system here to go faster. Now, it's easy to understand spin orbit torque switching in a macrospin picture. This can be done both for perpendicular and in-plane magnetized systems. For perpendicular systems, one also needs an in-plane magnetic field parallel to the current to break the symmetry of the damping-like spin orbit torque. But essentially, these are well understood mechanisms. However, it turns out that macrospin switching is not what we observe in general. Right? We need very small magnetic systems to preserve macrospin behavior. So in general, we have to deal with nucleation propagation of domain walls, and here is where the spin textures become important. Now, in thin films, we have generally two types of domain walls, Bloch or Néel, depending on whether the magnetization rotates in a helical way or in a cycloidal way. And in perpendicular magnetized thin films, the Bloch wall are generally favored by magnetostatic considerations. However, if we consider how a spin current acts on the magnetization of the domain walls, we have two substantial differences. Right? So in the case of Bloch wall, the injected spin current is parallel to the magnetization in the domain wall. And in this case, the torque is zero. On the contrary, in the Néel wall, we have a situation where the injected spin current is orthogonal to the magnetization in the wall, and in this case, the torque is maximum. So clearly, for spin orbit torques to act on domain walls, the Néel configuration is the most favored one. And now this is kind of fortunate, because it turns out that in magnetic systems coupled to non-magnetic conductors where you have strong spin orbit coupling and also surface structure inversion symmetry, the Néel walls are the favored ones. And you can see that now if we visualize the torque as an effective field, then the effective field in these walls has the direction of an easy axis. And so, for example, this field here will tend to expand this domain, in this field here will tend to expand this other domain here. And so it's a very effective mechanism for moving domain walls. Right. So as I said, then in this type of systems, naturally we have the formation of nail walls because we have also, because of spin-orbit coupling and structure inversion symmetry, we have also an interfacial Choleszinski-Morier interaction, which is mediated by the atoms in the non-magnetic layer that favors non-collinear alignment of the spins in the domain wall. And not only that, it also induces a well-defined chirality in the walls, so a rotation of the spin cycloid here. This was actually observed first by spin-polarized STM in the group of Wiesendanger in Hamburg, where by looking at the magnetic configuration of two monolayers of iron on tungsten with perpendicular magnetization, as you see here, these are alternate domains of up and down magnetization. By changing the coating of the magnetic tip to in plane, it was observed that at the domain wall position, the magnetization actually alternates. And this is a signature of chirality, which was understood a few years later when it was finally recognized that the interfacial DMI plays a very strong role in determining the spin texture of thin films. This you see here, for example, in this spin spiral configuration of a monolayer on tungsten. Okay, so how does it work in practice? This is a micromagnetic simulation of current-induced propagation of a domain wall with parameters that correspond to cobalt platinum. And so we have this nail wall configuration. We have a damping-like torque, and then this torque is equivalent to an out-of-plane field that will expand this domain. And so then if I start the simulation, this leads to propagation as well as a tilt, which is the result of the combination of the torque and Choleszinski-Morier interaction. And this tilt also leads to asymmetric domain wall propagation velocity. It's important to explain also the Skyrmian Hall effects in these systems. So can we see how important are these effects in a real system? So here we made an experiment where we have a cobalt dot about a nanometer thick deposited onto a platinum current line, and the whole thing is deposited on a semi-transparent silicon nitride membrane. So you see this is the platinum current line, this is the cobalt dot, and we mount this onto a PCB sample holder. And we then use so-called scanning transmission X-ray microscopy at the Swiss light source to image the magnetization in time and space. What we do, we focus an X-ray beam with a spot size of about 25 nanometers onto our sample. We scan the X-ray beam, and we measure the transmitted X-ray intensity, tuning the X-ray energy at the cobalt absorption edge, which gives us, at the same time, elemental and magnetic resolution. As you see here, these are XMCD, so X-ray magnetic circular diagrams, contrast maps of this dot for up and down magnetization. So, and then we do a current pump X-ray probe stroboscopic experiment. And so what you see here, this is these are the current pulses in red, and this is the trace of so it's the integrated XMCD contrast as a function of time. And if we look at the switching events here, see if the movie works. Okay. You'll see that in time we have first nucleation of a domain and then a propagation of the domain walls. And this nucleation and propagation events, they follow a very peculiar pattern, which you see schematized here. It tells us that the nucleation as well as the propagation direction of the domain walls are specific to the combination of current and in-plane fields that we use to control these systems. And this, which you see then summarized here, is very specific to spin-orbit torque-induced domain wall motion, where we have, in fact, first the nucleation of domain wall on the side where the magnetization tilts due to Choleszinski-Murray interaction, external field, and torques, both field-like and damping-like spin-orbit torques. And then the propagation of the domain walls follows a diagonal pattern. That's the direction where the propagation is faster in this system. Okay. And the fact that we can measure this in a stroboscopic way tells us that this is a very reproducible switching dynamics. And in fact, we find it not only in ferromagnetic systems, but also in ferrimagnetic systems. Now here, things are even more interesting because we have two magnetic sublattices that are antiferromagnetically coupled, so the transition metal sublattice and the rare earth sublattice. And so they form a system with a partially compensated magnetization. You actually also have a compensation temperature where the magnetization is exactly compensated. And they're very interesting because they display very fast field or current-induced dynamics, particularly at the angular momentum compensation point. This has been shown, for example, in the groups of Jeff Beach or Yoon-Sung Yang in Singapore. They have a tunable perpendicular magnetic anisotropy. They have DMI. They have low stray field, etc. Now, if we repeat the type of experiments that we've done with scanning transmission X-ray microscopy with a dot that is cobalt gadolinium iron in composition, and we record the traces of the magnetization in an element resolved way. This is for iron, and this is for gadolinium. This is the current pulse. We see that the two magnetizations do not switch at the same time. There is actually a transient region of the order of 2 nanoseconds where we have ferromagnetic alignment of the two on average. So this is very unusual. It was also very much unexpected to observe this decoupling, which people normally tend to assume that the magnetization during current-induced reversal in these systems, they're always rigidly antiferromagnetic with respect to each other. And if we look at the spatially resolved maps, we see that whereas iron switches as we've seen for cobalt, so nucleation of a reverse domain on one side and then propagation of a domain wall, gadolinium doesn't seem to switch at all first, and then it sort of loses contrast, right? And then after several nanoseconds, it recovers a magnetization that is anti-parallel to iron. So that's surprising enough, but even more surprising is that if we look at different sets of dots with similar composition, we observe a different dynamics. Now, the dynamics is faster, and we have domain wall propagation in both systems, but the domain in gadolinium is actually delayed with respect to iron. And we have also a third case where the dynamics is even faster, but now fully synchronized. So it took us, I think, about 2 years in measuring six beam times to understand what was going on. And so here are some conclusions. First of all, we have these 3 different cases, right? And then if we want to describe a decoupling of the magnetization, we have to take into account 2 things. One is that the spin orbit torques, which means the absorption of a spin current from the platinum underlayer into the ferrimagnetic layer, is not the same for the iron and gadolinium sublattices. It has to be faster for iron than for gadolinium, leading to a master-slave type of dynamics. Okay. And the second one is that if the 2 sublattices decouple, that means that the antiferromagnetic exchange cannot be so strong. And the fact that we saw that this coupling can vary from sample to sample means that it's actually a variable in our study. So after many experiments and tests, and we measure more than 20 samples in different beam times, we came to the conclusions that the microstructure of the alloy plays a very important role here. So it's not really the detail of the stoichiometric composition, but is the way the atoms are intermixed in the ferrimagnet that determines this different dynamics. And so as we grow the sample by sputter deposition, we have, and this we have seen by E-beam diffraction and TM studies, we have clustering on a scale of a few nanometers of rare earths and transition metals. And this effectively reduces the antiferromagnetic exchange between the two lattices because you have clusters of rare earths, clusters of transition metals, and so they interact only through the surfaces of these clusters. But since the mixing enthalpy of these different elements is negative, over time we get aging, and aging goes with a better mixing of the two species, and this leads to faster dynamics. And so then we think this is what explains the dynamics in this system. How much time do I have still? 12 minutes. Okay. Good. So now in all these systems, the domain walls are nail type or partially nail type, and this also extends to ferrimagnetic garnet. This is another example where we study current-induced domain wall motion due to current injection in platinum, but now we have as magnetic layer an insulating ferrimagnet. It's thulium iron garnet. And here again, we can move domain walls. We can also probe the nature of these domain walls by scanning NV magnetometry, which measures the stray field profile over a wall. And by fitting it, since Bloch and Nell wall have different stray fields, we can actually characterize the walls in this system. And this work was presented by Saul Veles a few days ago, so I will not spend a lot of time on this. Saul also presented a study of current-induced skyrmion motion in again, thulium iron garnet platinum, where we see that we can induce the formation of skyrmions by current pulses, propagate them again by spin-orbit torques, and we observe a skyrmion Hall effect. And this is again consistent with the fact that we have nail wall surrounding the skyrmion core here. Okay. And what Saul also measured is that the motion of these systems is strongly affected by pinning. So although in the images that we present, the skyrmions appear to move in a sort of flow-like way, the motion is really much more hopping-like. Good. So in the last 10 minutes, then I want to discuss a related topic, which is, since we've seen that chiral spin textures are so important in determining the efficiency with which this magnetic domains moves and skyrmion moves, what can we do to engineer the spin texture? Okay, so there are several ways of doing this. For example, by changing the substrate overlayer materials by electrical gating. And here I will present a different way. So generally, whenever we have interactions between magnets, we can then exploit them to couple different parts of a system. Right? This is true for dipolar coupling. It's true for exchange. And we have two famous examples that are used in magnetic devices. Exchange bias, so coupling a ferromagnetic layer to an antiferromagnet by exchange at the interface. This leads to the stabilization of the magnetization in this system. Or coupling through a non-magnetic spacer by the conduction electrons in the spacers, and this is called the RKKY coupling. And both these interactions are used to stabilize the magnetization in magnetic tunnel junctions that are actually used in MRAMs. Now, we can also think of doing something similar with the Jaruzelski-Moria interactions and couple layers in different ways. For example, it is possible to couple now two ferromagnetic layers in a way that is unusual, so with orthogonal magnetization, because the DMI promotes this non-collinear coupling of the magnetization. And this is work that, for example, Jan did a few years ago. He showed this beautifully in cobalt terbium layers separated by platinum spacers. And this leads to this inter-layer coupling. Now, in the remaining time, I will focus on a coupling induced by the DMI, but for planar structures. And the idea here is that, again, if we start from this picture of nail walls induced by DMI at the interface between two a magnetic material and a heavy metal, then if we have a way of changing the magnetic anisotropy of part of the magnetic layer from out of plane to in plane, we can realize planar structures that have this orthogonal coupling, mediated by half a nail wall, in fact. And this works in practice. So what we can do, for example, if we start from cobalt platinum, we can partially oxidize only a certain region of the layer. So here you see this is a oxidized top cobalt interface. This is not oxidized because it's protected by an aluminum layer with a tantalum mask on top of it. And so the non-oxidized region has in-plane magnetization. The oxidized region has out-of-plane magnetization. This is also seen by polar MOG. And if we then study the coupling of the magnetization in this system this was done by X-ray photoemission electron microscopy, again at the Swiss light source, we see that whenever, so here we have small islands patterned on platinum where we have a region that is magnetized out of plane, the red one, and a region that is magnetized in plane where this is not oxidized. Right? And what we notice is that there is a correlation between the out-of-plane magnetization and in-plane one, which is exactly what we would expect for the nail walls and for the chiral domain walls in this system. Okay. And in fact, if we measure the magnetization of the out-of-plane region as a function of applied field using the Hall effect, for different orientations of the in-plane region, so either, say, left or right, we see that the switching of the out-of-plane part is actually, the switching field is determined by the direction of the magnetization in the in-plane region. So this is a kind of lateral exchange bias induced by this DMI coupling at the interface. Okay. And we can also use this coupling to induce field-free spin-orbit torque switching of the out-of-plane region in the same structure. Now, it's very interesting to realize couple structures in the plane. So here we can connect two out-of-plane regions by an in-plane spacer. And this leads to effectively antiferromagnetic coupling between the two out-of-plane regions. And we can see that depending on the length of the in-plane spacer, switching one region, which we make larger than the other one, can lead to the reversal of the other out-of-plane region. So these are sort of synthetic antiferromagnets in 2D. We can also make, using the same principle, synthetic skyrmions and skyrmioniums, so where you have more than one winding of the magnetization here. And so here we have different concentric regions that are antiferromagnetically coupled by in-plane spacers. Okay. Of course, these are static objects, and they don't move because they are fixed by lithography on the system. So we can use this in-plane DMI coupling to engineer different effects, so lateral exchange bias, synthetic antiferromagnets. We can pattern artificial spin ices and skyrmions. We can induce field-free switching. And we can also inject domain walls using such lateral interfaces. And last, this is the last point I would like to show, is that we can modify the magnetization in domain wall racetracks to perform operations on domain walls. So consider such a magnetic stripe where we have patterned an in-plane region inside. So inside an out-of-plane magnetized track. Okay. Now we inject a current in this structure. We have a domain wall propagating, approaching the in-plane region. Okay. And so what happens in this case is that the approaching domain wall is annihilated on one side of the in-plane region. It flips the magnetization of the in-plane region because of magnetostatic and spin orbit interactions, and leads to the emergence. It leads to the emergence of a domain wall on the other side of the in-plane regions, but now this domain wall has opposite polarity. So here we have up-down, here we have down-up. This is actually verified in practice. Okay. This is measured by Stixim. Here, different times this domain wall here arrives, it's annihilated, and it emerges on the opposite side with opposite polarity. So I'll be a bit faster here. So using this effect, we can essentially realize a knot operation on domain walls. So inverting the polarity of a train of domain walls, for example, we can cascade different gates. We can also realize majority logic gates, so where we have more than one racetrack converging at a single region. In this region, we have a thin in-plane spacer that couples antiferromagnetically the magnetization on each side here. And so so the coupling is always antiferromagnetic, but now depending on how many sides of the racetracks are magnetized up or down, say the bottom part will either be up or down, right? And we can then realize different types of structures where, depending on the number on the magnetization direction in the inputs, we have different types of outputs. Here, this is a NAND type of gate. This is a NOR type of gate. And the difference between the two is that we have this third terminal, which we call the bias terminal, that determines which of the outputs will eventually be the lowest energy configuration. Okay, so I think my time is basically up. I just mentioned that we can realize more complex structures by cascading different gates, exploiting the fact that the domain walls can cross, they can fan out. So we have this type of operations. And so this is very interesting for the future. And just to mention a challenge, all these things work very nicely, but if we want to improve on this, we need materials where this spin orbit torque efficiency, which is practically a spinel angle, has to increase, right? And this is not only it has to be large, but it has to be large in materials with a low resistivity, because the power required to move domain walls or switch is actually proportional to current square times resistivity. So, and here we see these are heavy metals, these are topological insulators, and ideally we would like to fill this corner rather than this one. Okay, so I'll skip that, and I'll thank you for your attention.
Okay, thank you, Pietro, for this comprehensive talk. So, questions? Okay, yeah, maybe I can ask one. Yeah, Ransom.
Hello. thank you, Pietro. Very nice talk. I'm not very objective, but I found fascinating spintronics. You skip all the last slides about orbital current generation. Can you just say a few words? What are the challenges and the opportunities of this new, let's say, effect? Thank you.
Yeah, sure. So the orbital Hall effect has been mentioned also in talks yesterday. It's a very interesting phenomenon by which an electric current leads to the accumulation of electrons with opposite orbital momentum at opposite sides of a sample. And it is also believed to be an effect that comes before the spin Hall effect. So you can have orbital accumulation if you have a material that has so-called orbital textures. That means that the orbital character of the wave functions varies with momentum, but without spin-orbit coupling. And then if you add spin-orbit coupling, then this leads to a coupling of orbitals and spins. It can also lead to a spin Hall effect. So this effect was predicted actually in 2005 by Bernavig and colleagues, and then was taken over again by Kontani and colleagues for transition metals. It was forgotten for a long time until Hyewon Lee and colleagues in Korea calculated, and again, these effects in transition metals, and showed that the orbital Hall conductivity in certain light metal systems can actually be larger than that expected for the spin Hall conductivity in heavy metal systems. And so now experiments are coming out, and they're quite interesting. Now, what I can comment on here is recent work that we did in our group, but this doesn't work anymore. So, can you move on one slide? Okay. So you can essentially do similar experiments where you inject a current into this time it's a light metal, so for example, chromium, titanium, and observe the torques, measure the torques on an adjacent magnetic layer. And if you do that, you measure certain torque efficiencies, which we can translate into Hall conductivities, that are already quite large. So for cobalt chromium, right, we are about half of the value relative to cobalt platinum. Okay, so that shows that these materials are indeed much more efficient than what was initially thought. There's also a change of sign of the torques when changing the ferromagnetic material, which is not expected at all for spin Hall effect. So that's a signature of the Hall effect, of the orbital Hall effect. But now what is I find very interesting is that if you now insert a spacer layer in between the material that generates the orbital current and the ferromagnet, this orbital torque can be increased by a significant amount. In our case, by something like a factor 4 if we insert terbium in between chromium and cobalt. And the reason for that, we think, is that these rare earth layers, these 4F layers, have a very strong spin-orbit coupling, but by themselves, they don't generate a very strong spin Hall effects or orbital Hall effects. And so they act as converters of an orbital current into a spin current, right? And eventually, if you want to torque the magnetization, you need a spin current. And so in this case, this works very, very well. You see these are the efficiencies that we measure that are larger than cobalt platinum. So I think there is quite some room to play there with this combination of materials where you can actually exploit spin and orbital currents together. And if you get the right conversion, then this can lead to strong effects. I hope that answers.
Okay, thank you. So we are well over time, so let's thank Pietro again.
Thank you.
And the session is closed.
chair the session. My name is Andrei Zaikin, together with my colleague. Let me announce the first speaker is Professor Vasenko from High School of Economics in Moscow, and the title he will announce himself.
Thank you very much, Andrei, for introducing me, and I would like to thank the organizers of the conference for giving me an opportunity to give a talk on this conference. So, the title of my talk is Hybrid Helical State and Superconducting Diode Effect in Superconductor Ferromagnet Topological Insulator Heterostructures. So actually my affiliation is HSE University, which is a rather young university in Russia, and Lebedev Physical Institute, actually where I'm working in the group of Professor Zaikin. Let's start with helical state. So helical state, actually this is a rather new field. So what is a helical state? It's developed usually in 2D superconductors, and two important ingredients are needed. So it's a breaking of time reversal symmetry. For example, it can be in-plane magnetic field, but as well it can be exchange magnetic field. It means it can occur in SF hybrid structures and so on. And another important ingredient is breaking inversion symmetry. For example, spin-orbit coupling, but there can be other more exotic variants like asymmetry of the junction and so on. So in our case, it will be spin-orbit coupling. And I would like to explain how the helical state is introduced. So usually if you have spin-orbit coupling, you have this kind of term in the Hamiltonian, where sigma is a Pauli matrix vector, so it's spin matrices, P is the momentum of the electron, and N is a vector normal to the surface. And we consider 2D materials, yes? So, and then if there is a, so this term is the signature of spin-orbit coupling. But then if we apply it magnetic field, we make, for example, spin down state energetically more favorable. What does it mean if you look on the Hamiltonian term? So it means that due to this term is called spin momentum locking, because spin is locked to momentum. Due to this, it will result in the fact that some momentum will be more favorable, yes, also as well. And this will lead to the appearance of the spontaneous current. But of course, the system will develop a phase gradient which exactly compensates this current. So this is, will result in the Feyting homogeneous zero current state. The Q0 vector will be chosen in such a way to compensate these spontaneous currents, and this is called a helical state. So helical state is a rather recent topic. So for example, one of the first papers in 2005 in PRL was helical vortex fuzz detected in non-center symmetric superconductors. Then there was a theory of what's happening. I was trying not to. Okay, thank you very much. Then was a theory for quasi-classical theory for disordered Rashba superconductors, which means Rashba spin-orbit coupling in superconductors. And in our case, we consider so-called hybrid helical state. In a few minutes, I will tell what it is. So actually, my talk is based on the single paper. It still did not published. It's submitted to PhysRFB. And one of the main workers is my PhD student, Erjan Karabasov, also collaborating Irina Babkova and Alexander Golubov. Probably you already know them. And a few words first about topological insulator. So this is, I show this slide in many other talks. So what is important that it's, we will consider 3D topological insulator because there exists 2D, of course, also. That means that the bulk is insulating, the surface is a conductor, and it's not just a conductor, it's conductor with this spin orbit, strong spin orbit coupling and spin momentum locking. So spins are locked to momentum on this Dirac cone. What will be our system? Why I call it hybrid helical state? Because in our case there is no, there is a spatial separation of ferromagnetic order and of superconducting order. And still we have a helical state. So what we will consider? We consider a three-dimensional topological insulator. On top of it, on its conducting surface, we have a hybrid structure considered of ferromagnetic insulator or ferromagnet with superconductor. So we consider what is happening on the conducting surface of topological insulator, and we will roughly divide it in two parts. One part is topological surface with induced ferromagnetic order, another with induced superconducting order due to superconducting proximity effect. So then it's, that's why we call it hybrid helical state. And of course, due to this three ingredients all together, ferromagnetic order, spin orbit coupling, and topological insulator will, which produce spin orbit coupling, we have a helical state, and then of course we have spontaneous currents distributed over the system. And what I should also say, the system is finite in x direction, but infinite in y direction. So I briefly say a few words about models. So model we start with Uzadal equations, which are valid in dirty limit. And in case when we calculate a critical temperature, we linearize them. So this is, these are linearized Uzadal equation in superconductor, gap equation, and so-called Uzadal equation in topological insulator, which was derived actually in this paper of Zuzan, Mohamed Ali Doust, and Daniel Loss in 2016. And what I also should say, after calculations, we mentioned that so exchange field, H, is a field of ferromagnetic insulator or ferromagnet. It can have, because we have two-dimensional system, two HY and HX, and HY is not important for us. It just enters as a phase factor and didn't come to any physical variable. But HX component has an impact on the critical temperature, for example, and on diode effect and so on. So we just call it H in the end. So then we have the following NZs, which actually reflects the situations that we have this helical state. And the problem is to find this Q. Q, it depends on the state of the system. So, of course, Kupriyanov-Lukachev boundary conditions. On the boundary condition between ferromagnetic insulator and superconductor, we have two parameters. One, basically, is the strength of inverse proximity effect. So sigma is a conductance, and Xn is a coherence length in both materials. And another is the strength of the interface barrier. So if we have large gamma B, then we have a large strong insulating barrier here. And when it comes to supercurrent calculation, we actually use non-linear Uzadel equation. So first, hybrid helical state, and here I proceed to the results. So we calculate critical temperature for two directions of the exchange field. So you see the critical temperature has different values. And what is interesting that the maximum of TC don't correspond to zero momentum Q. So that exactly means that we have a helical state, because in principle the system should choose the situation with the maximum of critical temperature. So actually either this or this depending on the direction of the exchange field. And you see that it doesn't correspond to 0Q. So it does mean that there is a helical state, and if we, so we call this point QS. QS is a ground state of the system with this Q. So if we plot this QS as a function of exchange field, alpha here is just Fermi velocity, it's just to normalize. We see that this plot actually drops, means coming to the normal state, and naturally if we have transparent barrier, gamma B is equal, it means transparent barrier between ferromagnet and superconductor. Then this Q is most pronounced because we need this ingredient exchange field to develop the helical state. So here I have some analytical results for actually very small Q, where thickness small and gamma B is 0. I just show it's quite interesting that this result is proportional to this factor. Later I will get this factor in analytical result of other sense, of analytical result for the diode effect. And it means I will comment it later. So here I just prove that QS is a node function of H. And let's go further. So we also calculate supercurrent. You see supercurrent is distributed. So there is a density of current, and to calculate it flows only in the x direction because, I'm sorry, in the y direction. Because it's the direction where we have the oscillations of the exponential, this phase factor of the delta potential. And we should integrate on both F layer and S layer to calculate the whole current. So this I will call IT and this IS. IT means ferromagnetic part, IS superconductor part. So if we see the plot, this is the supercurrent, we immediately see that there is a non-reciprocal behavior, so-called. You see, so this curve, so this minima exactly correspond to black maxima. Actually, these two curves are for two different direction of exchange field. So red curve is plus H, black curve is minus H. So you see that there is a difference in maxima and minima. It can see if we consider these two defects. So this is non-reciprocity. We also see that it's, you see, non-linearity. So this part is smaller than this. And this state is chosen if, you see it's again correspond for non-zero Q, if we have no current in the system. If we applied external current to the system, the current, the state will choose different Q, of course, if we have some current bias. If we apply currents higher than this, it will mean that the system will immediately go to the normal state. What is also interesting that there is some, you see there are two Q corresponding to the same current. Actually, in calculation we have showed that smallest Q will be chosen because the temperature is larger, the critical temperature is larger for the smaller Q, which means that in these two, this one will be chosen. So, due to this current non-reciprocity, I also would like to say you the distribution of the currents over the system. So, please pay attention that the scales are very different, unfortunately. So, Terjan prepared it like this. So, you see here's -1 and here's close to 0. So, it doesn't mean that the same color on the different plots are the same current densities. But this current densities for three different states. For state B is most interesting. When there is no current bias, then the system is in the ground state. Yes, and this two states when maximum and minimum currents, which means that we bias our system with some external current. And because of this current non-reciprocity, there is a possibility to develop a superconducting diode effect. What is this? So it means that if we have this system and we bias it with the current in one direction and then in the same current in the opposite direction. Actually, it means that the currents will be different. So in this direction, you see the current is larger than in this direction, yeah, because there is a difference. It's not so big anyway, but there is a difference. In the middle, when there is no current bias, we have Q equal to Qs, that's the ground state, and these two currents calculated in ferromagnetic and superconducting part will be exactly opposite to each other. So they are flying equal and flying in the different direction. And because of this, we can develop superconducting. Oh, it's again happening. What's it? Maybe I should be like this. Should be more careful. So what is superconducting diode effect? It's if we have a current in one direction, there is a non-zero critical temperature, everything is good. But if the current is applied in the other direction, it can be already normal state. So this is just a very radical case. And actually, diode effect was first observed and very recently by Ando and co-authors in layered systems. So they really discovered this current non-reciprocity. And it was then later theoretically proven with these materials with broken time reversal and inversion symmetry. It's some helical superconductors by these guys and also Diado and co-authors. But now there is a huge amount of these papers who on theoretical papers on superconducting diode effect. And also I should mention the paper from the group of Bouzdin in Bordeaux. So they have very similar setup as ours, but instead of topological insulators, they introduced here, it's theoretical paper, introduced a boundary between superconducting and ferromagnet, which spin orbit coupling in the boundary. So the boundary condition implies spin orbit coupling. So they also have some teeny diode effect. In our case, we can plot this, what is the diode effect. So it's maximum minus minimum critical kite divided on the plus of these guys. And of course, you see it's 10 to minus 2, so it's not very high amplitude of this diode effect, but we studied the dependence of the exchange field. We see some some maximum. So there is some exchange field where the diode effect can have maximum. And this is dependence of the gamma parameter, which means how strong the inverse proximity effect. Actually, it does not plot it here. If we increase gamma more, it's again decay. So there is some optimal gamma. And this is the dependence of the strength of the gamma B. It's the strength of the tunnel barrier. So you see if the tunnel barrier is very weak, around 0, so it means almost transparent barrier, and we have a huge exchange field. Here we don't have any curve because superconductivity is broken by the exchange field in this case. Yes. So also we plot dependence on the temperature. We also have some interesting nonlinear behavior with some maximum in temperature. And finally, we did some analytical result for thin S and F layers, and actually here and small q. So this is valid. So this red curve is actually the numerical calculated curve, but black one is the analytical result. And what is interesting, so this result can be calculated in case of small exchange field, also small this factor, to the very interesting result. And this result we see, it's again, we can compare to result of QS. It's again governed by this factor, HDF over DS. So this is kind of factor which in case of small thicknesses govern our superconducting diode effect. We also see here interesting dependence of the temperature. So then I'm coming to the end of my talk, and my review is that the ground state of the system is characterized by superconducting order parameter modulated with finite momentum QS. So this state is accompanied by non-zero current distribution by zero average value. So, and this state is responsible for non-reciprocity of critical current, which actually manifests itself in superconducting diode effect. And also some important analytical results were derived. So again, thank you very much for your attention.
Okay, so the talk is open for questions.
Talk about the distribution current in X direction, but what about the distribution in Z direction? Does current flow in topological insulator surface?
Actually, in our model, we didn't consider it. In principle, in more sophisticated models, and it can be also considered, but in our model, we consider everything, for simplicity, just happening in 2D. Of course, if you have third dimension, in principle, it will be bad for the situation.
Thank you.
Thank you for your nice presentation. One question concerns this finite momentum. You are using an ansatz for the delta from the very beginning. And could you comment in more detail, how could you relate this momentum Q sub S to, for example, transport current or to other physical characteristics which are measurable? Thank you.
So in principle, we consider, yes, this ansatz, in principle, this immediately reflects this phase that we have this helical state, yes? So it's only with this ansatz we can, so you would say why we choose this ansatz, no, why we don't use another one, yes?
No, this is good.
This is good, okay.
Determine the value Q.
How to determine Q? Okay. Experimentally, you mean? So actually, I think there should be some indirect measurements with theory. So you, of course, you can measure this current non-reciprocity. For this is a measurable value. Then you immediately refer to the ground state Q. But there should be other. For example, you can measure critical temperature. Yes, and so I would say that from this talk, the most correct way, the most easy way is to measure this current non-reciprocity. Then you immediately find the QS of your ground state.
A very naive question from an experimental point of view. You presented just planar structures, right?
Planar, yes.
Yeah, so there is some hope to see something of these effects in a simple, I don't know, bilayer structure in which the superconductor is in an intrinsic non-central symmetric superconductor.
This was already measured, yes.
The very first one that you showed?
This non-central symmetric layered superconductors, this was already measured there.
With a ferromagnet? Or?
No, not ferromagnet.
Okay.
Yeah, it's intrinsic and magnetic field.
Okay, in plane.
Yes, in plane,
okay.
yes.
Thank you.
I touched it, it disappeared, yes.
And it's going to be both on Josephson.
Okay.
I'm sorry. So, the next talk will be given by Mikhail Klenkov, and it's going to be Josephson current stimulation by the temperature gradient in Andreev interferometers.
Thank you for the introduction. First of all, I would like to thank organizers for the opportunity to participate in this event. This work was done in collaboration with Pavel Dolgoriev from Harvard University and with Andrei Zaikin, who is somewhere here today. The outline of my talk is the following. First of all, I will talk a bit about the Josephson effect. Of course, everybody know here about it, but I would like to clarify some points which are important for me. And then I will talk about the non-equilibrium effect, and in particular the non-equilibrium effect in Andreev interferometers under the thermal bias. Well, if you put two superconductors together, then there is a non-dissipative current flowing across the interface. And it's important to control somehow the properties, the magnitude of the current. It can be done in many different ways. We can control phase difference, we can change temperature, we can, of course, choose geometrical parameters, we can apply magnetic field or electromagnetic radiations, and many others. For instance, we can choose geometry. We can make a constriction here. Sorry. What happened? For instance, we can make a constriction here or place different materials in between two superconductors. I will talk about the SNS structure when there is a piece of normal metal is placed between two superconductors. Then we know that due to proximity effect, superconducting correlations penetrate into the normal metal. And they decay exponentially if we go deep into the normal metal. And the length of the decay depends strongly on energy. If we, in the diffusive limit, the dependence is the following. And from this, we immediately obtain important parameter of the structure, the Taurus energy. You see that if the energy is less than Taurus energy, then the decay length of the superconducting correlation is just the size of the system. So we can say that there is a coherence between two superconductors. But if we consider quasiparticles with high energy, we immediately obtain that such quasiparticles couldn't maintain coherence in this system. That's important for my talk. And from this simple consideration, we can immediately obtain the temperature dependence of the Josephson effect in equilibrium. It just is such integral, whereas this term, red term, is just a measure of the overlap of these two functions, and this hyperbolic tangent originates from the Fermi distribution function. Then we can take this integral, transforming it into the sum of the Matsubara frequencies, and in this temperature interval, when the temperature is less than energy gap but higher than Taurus energy, we get fairly simple result that the amplitude of the Josephson current is exponentially suppressed with increasing temperature, and the phase dependence is just the sign. Here I just summarize important energetic parameters of the structure. It's the temperature. The next parameter is the gap. In the following, I will assume that the gap is the largest parameter of the structure. So I assume that the temperature and Thouless energy is much less than superconducting gap. And in the following, simple expression will be obtained in the limit when the temperature is in between the Thouless energy and energy gap. And for simplicity also I assume that metallic region is short enough so that we can disregard the inelastic process. That is just the system under the consideration, the Andreev interferometer. There are two superconducting terminals, two normal terminals, which are somehow interconnected with quasi-one-dimensional normal wires. We can incorporate this system into the external circuit in many different ways. For instance, we can connect two normal terminals via battery. Then we get a restriction on the voltages. Just the difference of the voltages is just V, the battery voltage, and we have a restriction on the currents. The currents flowing into the one normal terminals, the sum of the currents flowing into the normal terminals equals to 0. Or we can consider another situation when the normal terminals are not connected to the external circuit at all. Then we have a condition that there is no currents flowing into the normal terminals, but some voltages can be induced there in order to provide these conditions, the absence of the current. Here is just, I show one of the example, well-known example. Here's actually the same structure I showed you before, two superconducting terminals and two normal terminals, and the voltage applied to the normal terminals. And we're asking what is the Josephson effect in such structure. As we apply the voltage, then we should modify the equilibrium distribution function and replace it by this one. And of course, we expect that as soon as quasi-particle distribution function is not equilibrium, then the Josephson effect should be different from the equilibrium one. And it does indeed the case. We have an expression for the equilibrium distribution function, just an integral of the product of the spectral current and Fermi distribution function. We should simply replace the distribution function by the non-equilibrium one. And what is important that the spectral current is the oscillating function of energy, and changing the voltage, we can choose which energies give the main contribution to this integral. And indeed, it was done by these guys. Indeed, changing the voltage, we can control the value of the Josephson effect in this structure, and even get the zero pi transition in this structure. Also, I would like to mention the thermoelectric effect in the Andreev interferometer. So if we maintain normal terminals under the different temperatures, we can expect that some voltages induced here. And we can introduce the Seebeck coefficient, just the ratio of the voltage difference divided by temperature distance. And the main surprise here that the thermoelectric effect in such structures with superconducting terminals is much larger than the corresponding normal structure. That is because of the interplay of the conventional scattering and Andreev reflection. I won't go in details here, but I would like to say that even such simple structures such as Andreev interferometer actually have plenty of non-trivial phenomena. And let's now switch to the main part of my talk. I would like to consider much simpler Andreev interferometer with the length of the normal wires connected to the superconducting terminals of the same layer. I maintain normal terminals under the different temperatures, and I would like to calculate the Josephson current flowing between the superconducting terminals. In this geometry, actually, voltages are not induced. This is because of the symmetry of the system. And this simplifies consideration a lot. I used the approach of the Usadel equation here, which I believe relevant theory for dirty systems. The central object here is the quasi-classical green function. If we somehow solve Usadel equation and find this green function, then we can calculate the current density everywhere in the system. Green function has three components: retarded and advanced component of the green function describe the spectral properties of the system. And the Keldysh part of the green function contains information about the quasi-particle distribution functions in the system. And it's convenient to parameterize the Keldysh green function by two distribution functions. If we substitute this ansatz into the Usadel equation, then we get two diffusive-like equations for the distribution functions. Here, dt, dl, and y are some kinetic coefficients. They strongly depend on energy and phase difference in the superconducting state due to proximity effect. In the normal wires, they depend on the energy and phase. And G is spectral current. In the normal state, without the superconductivity, dt in dl simply equals to unity, and coefficient y and spectral current equals to 0. And this equation, the diffusion-like equation, should be supplemented by boundary conditions. That is the distribution function, quasi-particle distribution function in the normal electrodes. That is, it's this. And of course, due to diffusion into the, across the system, the distribution function inside the structure strongly deviates from this simple expression. And okay, in the partially symmetric X junction, there's a large simplification, because I said that there is no induced voltages there, so that the HT distribution function equals to 0 identically. And also, again, due to the symmetry, there is no y kinetic coefficient. Y kinetic coefficient equals to 0 in the wires connected to the normal terminals. As a result, these equations reduce to the fairly simple one. In the wires connected to the superconductor, we get just the equation that the distribution function is specially constant there. And in the y's connected to the normal terminals, we get this diffusion equation. Of course, it can be easily solved in the quasi-one-dimensional geometry, and the result is the following. The result, it's convenient to introduce two parameters in this system. I called them spectral resistance. If we, this spectral resistance in general depends on energy and phase difference, but if at large energies, dL tends to unity, and this spectral resistance is simply the normal state resistance of the corresponding wire. So we can say that this spectral resistance is just the resistance of the wire at a particular energy. The energy dependence, again, arises due to the proximity effect. And then we can just write, solve the equation and write the distribution function inside the system in this form. You see that it is a weighted sum of the equilibrium distribution functions with some weights which depends on energy and phase difference. It's convenient to rewrite this expression in the form where the weights are not energy and phase dependent. It can be done, but the additional term appears here. It's function W. Actually, we can't evaluate the function W, but it's again some combination of the spectral resistances. What we know about this function, that it is even in the energy and phase and rapidly decays when the energy exceeds the Taurus energy. So now we have all ingredients to evaluate the current. Sorry. We just have this expression for the current. We should substitute here the non-equilibrium distribution function. As a result, we get three terms. Integrating this term, we get just the equilibrium Josephson current evaluated at the temperature T1. Integrating this term, we get again equilibrium Josephson current evaluated at the temperature T2. I call these two terms as just quasi-equilibrium contribution to the Josephson current. And the last term is just the integral over this term. It's the essentially non-equilibrium contribution. And what is important, I will show you that the temperature dependence of these terms are very different. You see that integral representation of this term looks like similar, while the temperature dependence should be very different. But actually, there are one important difference between these two expressions. The point is that the spectral current G is actually a real part of the analytic function in the upper half plane. But from the other hand, the function W have no any particular analytical structure anywhere. And that is the essential point. Evaluating this integral, we can use Matsubara technique. And in the temperature interval, when the temperature is much larger than Taurus energy, we immediately get well-known result that the equilibrium Josephson current exponential decay with the temperature. From the other hand, we can't use a Matsubara trick here in the non-equilibrium term. In the leading order, we can simply expand the hyperbolic tangent in Taylor series, and in the leading order, we get this very simple result. So without actually any particular calculations, we get the temperature dependence of the non-equilibrium contribution. And we see that instead of the exponential dependence, we get just one of the t dependence in the non-equilibrium contribution. It's actually the main point of my talk. You see that non-equilibrium contribution in the thermally biased junction can be much, much larger than the equilibrium one because of the different temperature dependence. That is indeed the case. Using some dirty tricks, we can actually evaluate the function W and find the phase dependence of the non-equilibrium contribution and the prefactor here. And you see what is important, that non-equilibrium contribution first depends on temperature only as 1 over T, has quite unusual phase dependence. And the third, the sign of the non-equilibrium contribution depends on the geometrical parameters. So changing the geometrical parameters of the structure, you can change the sign of the non-equilibrium contribution to the Josephson current, or just changing the temperature. You can also change the sign. And that is important. Here's the shown the result of the numerical calculations using just Uzadel equation without any approximation and our formulas. You see that at low temperatures, quasi-equilibrium contribution to the Josephson current dominates, but that is the temperature dependence of the critical Josephson. That is the critical Josephson current as a function of T2 when the temperature T1 is fixed. So at low temperatures, the quasi-equilibrium contribution to the Josephson current dominates, but starting with some temperature, non-equilibrium contribution becomes strong, and actually the critical current increases starting with some temperature. Here I plot the dependence when the length to the first terminal is larger than the length of the wire to the second terminal. In the opposite situation, we get a similar picture, but now the sign of the non-equilibrium term is opposite. So at low temperatures, when the T2 is low, we get this black curve for the current phase relation, and we see that just conventional, slightly modified sign dependence. But when the temperature becomes higher, then we see that the junction switched to the, I said, almost pi state. So in the thermally biased junction, changing the temperature, we can switch it from the 0 to pi state. Actually, we can generalize these results to the Andreev interferometer or the general geometry. And again, we can show that the total current flowing from one superconductor to another can be represented as a sum of the three terms. The first two terms is just a weighted sum of the equilibrium Josephson current evaluated at the temperatures T1 and T2. And the third term is essentially non-equilibrium contribution. And again, we can show that the non-equilibrium contribution has this particular one of the T dependence, which again can dominate the equilibrium contribution at large enough temperatures. And for X junction of the general geometry, so there is no restriction of the length of wires, we can obtain this approximate result, which shows that the sign of the non-equilibrium contribution again can be controlled by the temperature or the junction geometry, and has this particular phase dependence. And what's important that this function P1, it's just a universal function, doesn't matter, but it can be large. What I can say that tuning the geometrical parameters, you can enhance even larger the non-equilibrium contribution, so that it can be observed at lower temperature. So this effect of the thermal bias can be larger. That is the summary. We proposed a new type of the junction, thermally biased Andreev interferometer, which can be parameters of the junction can be tuned by the temperature. And we find it's quite unusual that changing the temperature, we can switch with junction from 0 state to the pi state. And what's important, the temperature dependence of the Josephson current is 1 over the T, the dependence of the non-equilibrium correction. So one can think about the situation that in the equilibrium there is no Josephson effect. It's negligibly small, but applying the thermal bias, we can obtain Josephson effect in this system. Thank you for your attention.
Thank you. So the talk is open for questions.
Could you tell us a little bit about the material, so to say, absolute numbers involved? Bias, how many Kelvin and current of how many amperes? This, for instance, you have all in this ETH measure, which is what I mean.
This is just conventional Josephson junction, so it depends on how to prepare it. Here's, you show that in this partially symmetric junction, non-equilibrium effect can be observed if the temperature is about 50 of Thouless energy. So you should quite long.
Okay, but that is precisely my question. When I look at this figure, 50, how many Kelvin should I imagine is this 50? Also this 10 to the minus 4, how many amperes should I imagine in a real device this would be? If you actually made such a device, you would be dealing with kelvins and amperes. And I'm just asking to translate this graph into an actual laboratory measurement. What numbers I should expect on the two axes in Kelvin and ampere?
Oh, of course, if you have a critical temperature of the superconductor about, say, 1 Kelvin, then of course you here at sub-Kelvin temperatures.
And if I have, say, 39 Kelvin, like magnesium diboride, then what is 50 here?
Well, I will say that for simplicity here, we consider the situation where the temperature is much less than the superconducting gap and much larger than the Thouless energy. But actually, the first restriction that the temperature is much less the superconducting gap is not too restrictive. So this temperature can be around the superconducting gap, so of order of.
Okay, thank you.
Just the condition that the temperature is quite low allow us to disregard the overgap contribution to the current. If your temperature is large enough, then we should take into account that. But I believe that the non-equilibrium contribution to the current, which is 1 over the T, still be there.
So, is it possible to calculate the thermophase Seebeck coefficient in this geometry? People have calculated it in like, the thermophase Seebeck coefficient, can you calculate means what this geometry? Because people have calculated it for simple Josephson junction. If there is a thermal bias between, so
this one, I don't understand, sorry.
The question is that is it possible to calculate a thermophase Seebeck coefficient for this geometry? Means in Josephson junction, if there is a thermal biasing between these two reservoirs, then there is this called thermophase Seebeck coefficient.
It's for the thermoelectric coefficient.
Yeah.
Yes, of course it's possible, but it's the topic of the, say, in our talk. I just, of course, we have several works on the topic of the thermoelectric coefficient in the Andreev interferometers. There is actually a lot of interesting effects there, but it's just not the topic of today's talk.
Okay.
Okay. Any other questions? No? Let's thank the speaker again. It's now time for the last talk of this first part of the session. Do we have the speaker? Okay, it's going to be...
Hello, do you hear me?
Yes.
Okay. I have to open the presentation. Do you see the screen?
We do.
Okay, thank you. So first of all, I would like to thank organizers of the conference for giving me opportunity to present my results. And I apologize that I could not participate in the conference in person due to personal reasons. So I have to make the talk remotely. I am experimentalist and present here to organizations, Moscow Institute of Electronics and Mathematics of HCE University, and my laboratory is in Kapitsa Institute, also in Moscow, in Russia. My collaborators are Jan Lehtinen, who is also experimentalist from Finland, and theoretical support is made by guys from Moscow and Germany, Andrei Zaikin, Andrei Semenov, and Alexei Ratkevich. So what the story is about? Actually, as I understood, I have 20 minutes for my talk, and I'm planning to speak actually quite a lot. So I will go quite fast. I hope in first 5 minutes, I will make a brief introduction about what are the fluctuations of the order parameter and what is the concept of quantum phase sleep. Next 5 minutes, I will spend for relatively old results, our own results showing integral properties and how they are affected due to quantum phase sleep effects. And the last 10 minutes I will spend mainly for the new results, which are not yet well advertised. So what the story is about, I'm going to speak about quasi-one-dimensional superconductors. The characteristic scale is the coherence length. So in our samples, it is something of the order of 100 nanometers. So modern nanotechnology is capable of fabricating nanowires with cross-section smaller than 100 nanometers, no problems, and they are sufficiently long. So the most famous property of superconductivity is the resistive transition, and it would be very convenient to make introduction to fluctuations of the order parameter in superconductors, speaking actually about resistivity. Let us consider that on this cartoon, everything which is in normal state is shown in red, and everything which is zero resistance in superconductor is green. So let us first concentrate on the top of the transition. So resistance versus temperature, and I'm speaking about the top part of the transition. And the answer is known. This is a contribution of Aslamazov-Larkin, which shows that for all dimensionalities 3, 2, and 1D, the impact of these fluctuations lead to rounding of the top part of the transition. So the corner here will be rounded. Now let us turn to the bottom part of that transition, where the system is mainly in superconducting state, but here and there that might appear some normal domains due to fluctuations. One should not be an expert in superconductivity to understand that in 3D and 2D nothing interesting happens, because supercurrent prefers to go along the zero resistive part, the green one here. So whether we have these red spots or not doesn't matter. But situation is dramatically different if one speaks about one-dimensional case where a single fluctuating domain can block the supercurrent. So how it is assessed in theory? So let us suppose that we have a long superconducting wire with cross-section sigma smaller than the coherence length, so it is quasi-one-dimensional system. And theories say that there is always finite probability that here and there, instantly order parameter turns to 0 and phase changes by 2 pi. So there appeared such red spots. It's a dynamic process. So the minimum energy one should pay for destruction of superconductivity in such a point is the condensation energy, which is a very well known how to calculate from any textbooks in superconductivity. And if to consider that these events are quite rare, then the probability of such processes is exponential function depending on the energy spent to kill superconductivity within this red point, normalized by some energy. And the whole story is about what is in the denominator of this exponent. If we speak about the classical approach, then it is just thermal energy, KBT, and it is important sufficiently close to critical temperature. There might be other situation, and that is the point of my talk, when the energy is the gap itself, so it's a quantum fluctuations of the energy gap. There is other approach, also cartoonish type. Let us consider that fluctuations happen in one particular point of the wire, let's say with some, where is some constriction. Then the free energy as a function of the order parameter is a well-known washboard potential. So if we have a classical process, then the whole system represented here by a dot can go over the barrier, and this will correspond to the classical case of thermal fluctuation. But as the system is quantum, it can also tunnel from one local minima to another, and this will be quantum fluctuation. Note that the initial and the final states are different in energy, in finite current, when the washboard potential is tilted, so it will lead to dissipation. So what are the manifestations? The very well-known manifestation, and that has been studied by us already more than a decade ago, and also other groups contributed, is the broadening of superconducting transition resistance versus temperature. Here are the plots from our old results. Left is shown for aluminum, right is shown for titanium. So the conclusion is that for sufficiently narrow wires, quantum fluctuations completely kill zero resistance state, and in the thinnest wire, the extrapolation of the dependence to absolute zero doesn't result in zero resistivity. Lately, for other materials already more complicated, niobium N, which is very disordered superconductor, we also managed to show that in the thinnest wires, there is a contribution of quantum phase slips. So that was about the resistivity, effective resistivity of a superconductor, which is so-called integral property. You need a long, or let's say extended object to measure its resistivity. Other integral property, which also needs a finite dimension system, is persistent current, which happens, let's say, in superconducting rings. So how to measure persistent current in a tiny superconducting ring? It appears to be not an easy experimental task, but fortunately, we know that the system changes from one quantum state to another when the persistent current in the ring reach subcritical values. When the current in a system, in a superconducting system, reaches its subcritical value, it broadens density of state. So if to make tunnel spectroscopy of such a wire where there is a circulating current, we can, by probing tunneling through this ring, somehow recalculate it into persistent currents. And this task was made by us already 10 years ago. And we indeed showed that when the ring has sufficiently thick walls, everything goes according to classical textbook superconductivity. But when the cross-section of the wall starts to be sufficiently small, the periodicity changes strictly to one flux quanta, and the magnitude dramatically drops. And this is also the contribution of quantum phase slips. So to conclude this old part of my talk, one should say that the process, which is called quantum phase slips, leads to broadening of the resistance versus temperature transition and suppresses persistent current in nanorings. Both properties I call here integral properties, which need extended sample to be measured. But what about local properties, for example, like density of state or energy gap, which formally can be measured in a point, let's say by a tip of a tunnel microscope, or in our case, by a tiny NIS or SIS junction. For this purpose, we fabricated a structure which is shown here in the left plot, which has relatively massive aluminum wire, and across it, there were several nanowires of different cross-sections. So the cross-sections of these titanium nanowires were selected like this, that in the thickest one, we should not expect strong quantum fluctuations, but in the thinnest one, which exponentially depend on the cross-section of the wire, the probability of fluctuation, they should be very strong. And in this experimental configuration, we can measure both the integral property of each nanowire, let's say its resistance, or we can measure tunneling between such a nanowire and other massive aluminum electrode where no impact of fluctuations is expected. And here is the summary of experimental results. So for thick wires, we confirmed our old results that they show relatively sharp superconducting transition. For thin wires, the transition was extremely broad and the resistance was not extrapolated to zero. And when we measured the tunneling property, which characterizes the intersection point of the thick aluminum wire and thin titanium wire in the limit of quantum fluctuations, we observed more or less conventional IV characteristics. What I mean here by more or less, that they look very similar to BCS IV characteristics with relatively sharp horns, if to speak about the derivative as function of voltage bias, but they were sufficiently broadened into sub-gap reasoning. And I will now speak about particularly why it happens. And additionally, if to zoom the IV characteristic at the origin at small biases, we observed also a Josephson current. So to conclude the bare experimental results, it appears that for the same nanowire, sufficiently thin, we observe that the resistance is not going to zero, the transition is very broad without reaching zero resistance state, but the local properties like density of state, energy gap, and Josephson currents, they more or less look like in a conventional superconductor. Why it's like this? To speak about the explanation or interpretation of our results, let us now come back again to the issue of fluctuations of the order parameter. So order parameter is, in a general case, a complex function which has its modulus and phase. So what I was speaking so far was so-called brutal fluctuations of phase leaps, where at some moment of time, modulus of the order parameter goes to zero, and simultaneously the phase changes by 2 pi. So these are these abrupt changes of modulus and phase. But one should not forget that there exist also weak fluctuations, so-called Gaussian fluctuations, both of the modulus and also of the phase. And the theorists say that the fluctuations of the phase are responsible for generation of soft plasmonic modes, so-called Muishon mode, which propagate along the nanowire, cause redistribution of electronic states, which broadens the density of state of the superconductor and the energy H. So formally, this broadening of the density of states can be described by the famous Dyne's parameter, that now the density of states becomes a complex function which is broadened. But here the origin is completely different. In original paper, Dyne's considered that this broadening happening due to finite lifetimes of quasi-particles. Here it's the result of quantum fluctuations, the Gaussian fluctuations of the phase. And our theories calculated that indeed the energy gap broadens sufficiently close to the energy gap. And here it is important to introduce two characteristic parameters. One parameter, so-called G with index psi, is responsible for dimensionless conductance, and it characterizes the fluctuations of the order parameter or also of the quantum phase leaps. And it exponentially is in the rate of quantum fluctuations. Other dimensional parameter, so-called admittance, accounts for the hydrodynamic or long wavelengths interaction of fluctuations. And this parameter is responsible when we want to speak about interaction of phase leap events, which happens due to propagation of these Muishon waves. And there is shown that the characteristic value of this admittance equal to 16 corresponds to superconductor insulator transition. And here they have introduced the characteristic length scales shown here at the bottom, which separates the system from being completely insulator from the condition when some superconducting properties might be manifested. So on this image, prepared by my co-author, Andrei Semyonov, naively one can understand what I'm going to speak about. So the quantum phase leap is the tunneling of the flux quantum through a superconducting nanowire. So this characteristic length scale, x with index c, is the threshold. If the system is sufficiently long, then on these scales, quantum fluctuations completely wash out their superconducting correlations. So on the long scales, the measured integral properties are losing their superconducting properties, like I have shown in the first part of my talk. No zero resistance state, no persistent current. But if system is smaller than these characteristic length scales, then superconducting correlations are not washed out completely, and measuring these properties on a shorter scales, like made in this experiment, for example, measuring tonal characteristic, we can detect something which resembles conventional superconductivity. Indeed, so for the same structures I shown you before, the theory fits show that the shape of the resistance versus temperature transitions can be nicely fit by the model of quantum phase slips for different wires. But because the probability of quantum phase slips exponentially depends on the cross-section of the wire, for thicker samples, it's relatively abrupt superconducting transition, but for thinner ones, it is not. But all of these transitions can be nicely explained by the mode. When now we speak about the local properties, here is a family of IV, actually the derivative di dv as function of voltage for the same wire at different temperatures. They are all normalized to be here equal to 1. Again, theory manages to fit to the experimental dependencies. And the broadening I spoke about from the theory point of view, indeed is observed in experiment, and it nicely corresponds to theory prediction. So my conclusions. So quantum fluctuations of the order parameter is a universal phenomena which has impact on both integral and local characteristic, if to speak about quasi one-dimensional superconductor. In sufficiently thin nanowires, a finite electrical resistance can be observed at the lowest temperatures, which is explained in terms of localization of Cooper pairs. The same effect suppresses persistent currents in sufficiently long perimeter nanorings. But local properties measured by tunneling phenomena show some superconducting properties like energy gap, broadened density of states, and finite Josephson current. Thank you for your attention. That's it.
Thanks, Kostya, for your talk. The talk is now open for questions. I see no questions. Everything was clear. Seems to
maybe I was too fast.
Maybe it's okay. So okay, anyway, if there are no questions, then let's thank the speaker again, and now we close the first part of the session. We have a break of, I don't know, 10 minutes. talk will be given by Emil Bozen from Brookhaven National Lab, USA. He will announce the title, and so please.
So today I'm going to talk about the role of ruthenium hexamers in superconductivity of ruthenium phosphide, or rather, it's actually a question whether those fluctuations are actually important for superconductivity. So to begin with, I would like to acknowledge the funding agency, which in this case is majority US Department of Energy, and also my colleagues who contributed to this work. The samples came from Chedrin Petrovich's group. So in principle, to make a general statement, the emergence of technologically relevant quantum orders and the rich physics stems from complex interaction of electronic charge spin and orbitals and their coupling to the lattice. In many materials, complexities of ordered states at low temperature are explored extensively, but much less is known of what happens in the temperature in the phase space away from the ordered regimes. We are particularly concerned about whether there is actually nanoscale symmetry breaking in this regime. And in experimental world, many techniques are actually not very sensitive to the nanoscale simply because they average over the bulk. So when electronic properties coupled with lattice, it's useful to apply so-called advanced Fourier methods and derive pair distribution function approach, which is, in case of powders, essentially relying on two pieces of information: Bragg, that gives you the average crystal structure, and diffuse, which carries information about the deviations from the average. And then if you Fourier transform this signal and you collect it over a broad momentum transfer range, you're going to get a histogram of interatomic distances in the material, and then you can interrogate this function on different length scales and obtain information on how this behaves on different length scales. Or you can take an alternative approach. You can actually study single crystals. And so if you collect data over a broad range of momentum space in 3D, you will, in principle, get Bragg and diffuse scattering components. And the advantage of basically this is that Bragg is usually very sharp and well-defined signal, also very intense, and diffuse is rather broad and weak. And so in principle, you can either treat them together. So you would Fourier transform this entire map of Q space intensity into a direct space, and you're going to get something that is called 3D pair distribution function. Or you could separate Bragg from diffuse signal and then Fourier transform just diffuse to get 3D differential PDF, which is then actually measuring the difference in the local and the average structure given as a function of pair vectors. So to show how this methodology works, this is one simple single slide example. In this system, copper iridium thiospinel, there is a metal insulated transition at around 200 Kelvin. The high temperature state is metallic and it's cubic, where iridium, which is the main player in this system, is sitting on a pyrochlore sublattice. And then when you cool the system down, it becomes insulating and the structure changes to triclinic, where actually you have these orbital molecules that are based on iridium dimers, and they form further larger creatures such as these hexamers. So if you take this PDF machinery on powders and you go to very high temperature, 500 Kelvin, and you basically check the cubic model, you see that it actually works very well over the broad range of length scales, but it fails underneath this second peak, which is actually iridium near neighbor distance, suggesting that there is actually a local state at high temperature that has not been taken into account if you just consider crystallography. Similarly, if you do single crystal measurement at high temperature in the metallic state, you obtain these maps of very beautiful diffuse scattering that has this characteristic bow tie shape. And so, whoops, I have done it. Sorry. Thank you. So basically, this leads to precursor state that exists in the metallic regime that is a very short range, basically nanoscale precursor that relates to orbital sector, in that it's like, you can consider it as orbital liquid that is important for the system. Okay, so that being said, the main part of my talk is going to be on binary ruthenium nuclides, which are explored over the last decade in the context of superconductivity, stimulated by the discovery of superconductivity in iron-based materials. They have the same, ruthenium has the same electron count as iron, except that it's generally less magnetic. This is the state in which nominally ruthenium is. Structure at high temperature is orthorhombic, PNMA, and ruthenium is octahedrally coordinated by nitrogen and forms a 3D network of face and edge shared ruthenium-nitrogen octahedra. As far as properties are concerned, ruthenium phosphate and ruthenium arsenide are systems that exhibit a two-stage metal insulated transition that is accompanied by a change in symmetry, structural transitions, and both of them have non-magnetic ground state. On the other hand, ruthenium antimony remains metallic and does not have any transitions at any temperature. Okay, so this is how the properties look like. So the most robust is the metal insulated transition at a lower temperature in all those systems. But and at high temperature, you have actually a resistivity of the order of 1 milliohm centimeter. And magnetic susceptibility is Pauli paramagnetic. Now, as you cool the system down, you have this metal to insulator transition, but if you carefully look actually in the resistivity, you observe that there is a slight upturn at a higher temperature in resistivity and also slight drop in susceptibility at a temperature of about 50 Kelvin above this metal insulator transition. So these anomalies in high temperature regime are hypothesized to indicate some kind of precursor state to the insulating phase. Okay, there is also at both temperatures, there is also a symmetry change. Now, photoemission spectroscopy has not found any evidence of change in ruthenium valence across the temperature transition, which basically does not then suggest that there is a charge disproportionation in the system. And so strong charge modulation that would be accompanied in case of CDW is not seen. The other aspect is that there is a suppression of spectral weight in the UPS spectra near and above Fermi level that suggests that there is a formation of pseudo-gap at this higher temperature. Okay, and this has been actually confirmed subsequently in DFT calculations. Full gap at base temperature is of the order of 100 MeV. Okay, so when you now substitute ruthenium instead of, rhodium instead of ruthenium, meaning if you dope, this system starts evolving and ultimately it actually displays superconductivity in both phosphorus and arsenic variants, whereas antimony version of the material is superconducting by itself. It's metallic all the way and then at low temperature displays superconductivity. So this leads to a kind of pretty rich phase diagram where in case of ruthenium phosphorus and ruthenium arsenic, superconductivity has a maximum at the quantum critical point of the pseudo-gap phase. The non-magnetic ground state is pretty quickly suppressed, but the pseudo-gap phase persists for a longer composition. And so basically, given the difference between phosphorus, arsenic, and antimony, there is to be expected steric effects that affect the orbital overlap. and also enhanced hybridization with Nictogen p orbitals. And then also rhodium doping, which is essentially electron doping, moves nominal filling from D5 to towards D6. Okay? So this is to say that this implicates the role of bandwidth and band filling into the electronic properties. And also there was an early on speculation that fluctuations of some order parameter might be relevant for superconductivity. Or you can flip this question around and naively say that maybe in reverse perspective, is TC enhanced in ruthenium phosphate as compared to the arsenic variant? And if yes, what is, by what? Okay. So the initial suspects for fluctuations are, of course, antiferromagnetic fluctuations. This has been assessed using 31 phosphorus NMR. And so this is the map of those fluctuations, and it turns out that they become weaker as you move away from the non-magnetic ground state, and they're actually relatively weak, close to the point where superconductivity is maximum. Okay. Good. So in the high temperature metallic orthorhombic regime, there are actually electronic instabilities that are suspected to lead to this structural phase transition and electronic phase transition, and that is that both arsenic and phosphorus variants have flat degenerate narrow bands close to the Fermi level, and that states of interest that actually produce high density of states at the Fermi level are of ruthenium 4D character. And also, there is no obvious Fermi surface nesting features that are observable, again suggesting that the underlying ground state is not conventional CDW. This is the structure. So structure is essentially of manganese phosphate type. It contains, as far as ruthenium sublattice is concerned, zigzag chains running along the A-axis. Those are corresponding to the edge, to the phase sharing of the octahedra. And then those zigzag chains are in the BC plane connected by a ladder of distorted triangles. And what is interesting is that the shortest distance in the system is along those zigzag chains running along the A-axis. The intermediate ruthenium pair distances are actually the rungs of the zigzag ladder in the BC plane, and the longest distances are ruthenium pair distances along those straight chains parallel to the B-axis. So if you do DFT calculation that is orbitally decomposed, you can actually track that the principal instability is originating from DXY, bands derived from DXY orbitals, which are actually running along those longest chains along the B-axis. And so, okay. Since this material is relatively new, it has been speculated for 10 years what is the origin of the electronic transition. So whether it's a charge density wave or some kind of charge ordering, which turns out not to be applicable, at least not in a simple form, spin singlet formation, orbital driven pulse transition via pseudo Young-Teller effect, or formation of molecular-like orbitals that involve dimers, polymers, or molecular chains along the B-axis. However, at high temperature, it has been considered that this degeneracy, that is presumably the driving force, is protected by the non-symmorphic character of the PNMA space group, and that somehow all the action takes place at the transition. So the question is, what are the structures of these lower temperature phases? It turns out that they are actually not very well explored. As a matter of fact, during the work that we carried out, the structure of ruthenium phosphate was not known. It actually just was reported about 3 weeks ago. So the renormalized story goes that basically both ruthenium arsenic and ruthenium phosphate have monoclinic P2 upon C structure, but the structure of the pseudo-gap regime is still not known. It turns out that it's actually incommensurate. In PNMA structure, all ruthenium sites are equivalent, whereas in the P2 upon C, ruthenium is trimerized, such that there is 4 electrons on 3 centers. Basically, it forms trimers, like so. And so this is basically the current explanation of what is going on, again, portraying that all the action is taking place at the transition. So what happens if you engage the PDF machinery? The important motivation for that is that both ruthenium arsenic and ruthenium phosphate are anomalous at high temperature. They have basically poor metallicity, broad Drude-like component in optical conductivity, and also enlarged ruthenium ADP parameters, or Debye-Waller factors. So when you engage the PDF machinery both in the powder and crystalline form, what you do see is, for our samples, we do see both transitions in diffraction. And then when you try to model PDF of the high temperature 370 Kelvin data that is deep in the metallic regime, you see that the PNMA model works very well over intermediate and long distances, so this is the fit. However, that fit is actually giving you back enlarged Debye-Waller factors along the chain directions U2, and so sure enough, if you take a look how that fit performs at basically for the local structure, you see that it actually fails, as if some bonds are missing. So this is a characteristic signature of displacive distortion, which you can actually, through simulations of partial PDFs, track to the distance that is the longest distance in the structure, which is ruthenium along the B-axis chains. So in order to understand this, we used as a proxy the low temperature P21 upon C model. And it turns out that it can actually explain PDF data over the length scale of 1.5 nanometers. And if you then use frozen parameters and extend the calculation to compare it to the data, you see that beyond that length scale, the model actually starts failing. So this is basically how it looks like. So the question is, what does this model imply? So to do this, we have actually carried out sequential refinements over a broad temperature range from base temperature all the way up to 370 Kelvin. And we have grouped ruthenium distances from P21 upon C model into distance groups that correspond to PNMA type distances, and this is what you actually see. You see that shortest ruthenium pairs, which are those green ones along the zigzag chains, and blue ones, which are actually the rungs of the zigzag ladder, do not change much. However, the longest distance turns out to be bifurcated, so you get this basically distribution of distances, which is very broad. It's actually a splitting that has a frequency of basically you have two times more short bonds than long bonds, and that basically is very much deviating from the orthorhombic PNMA structure, whose bond length is supposed to be single valued, as shown by this dashed line. Okay, so another aspect is that basically there is a dramatic, whereas there is no change at all across the pseudo-gap transition, which suggests that this transition is disordered in character, you see basically a much larger distortion in the non-magnetic ground state, which is suggesting that this distortion in low temperature and high temperature is of different origin, that the electronic state is not exactly the same. Okay, so yes, I actually told you before what the ground state is, but when we were doing this, it wasn't known. So if you have a distribution of 2 short and 1 long distance along the linear chain, that is essentially portraying a trimer. If you do a careful assessment of other refinement parameters, such as bond angles, you realize that the bond angles on the zigzag ladder are also bifurcated, that you have 4 smaller angles that are relatively temperature independent and 2 larger angles, which actually portrays that these trimers are further organized into hexamers. Okay, so this short-range hexamer correlation is presumably fluctuating at high temperature and represents a response to the Fermi surface instabilities in the metallic regime. How does this look like in the single crystal experiment? Well, you first observe these rich patterns of diffuse scattering that are actually quite fascinating. And then you can apply this 3D differential PDF methodology by Fourier transforming the entire map of diffuse scattering over a large box in Q space and obtain PDF. And if you do that, you essentially see, here is the differential PDF, which is this red and blue signal, that it's highly one-dimensional. It's actually running along the B-axis, which is precisely pointing to the same type of distortion that we see in the powders. Okay? So if, and then there is not much signal elsewhere, which is suggesting that this distortion is really quasi one-dimensional. If you zoom in this differential signal, here you see basically a red, blue, red type of signal. Blue is negative, red is positive, which means that there is a redistribution of pair distances in such a way that both short and long distances are generated. And then another thing, if you pay attention, the signal closer to the origin is almost, I mean, it is much more intense than the one away from the origin. So to quantify that, you can basically take a cut along that direction, and you immediately see that the intensity that is closer to the origin is about twice as intense than the intensity away from the origin, again portraying a picture of there being linear trimers. So that's that. If you look elsewhere, basically the signal that we see is consistent with actually there being hexamer formations. So for example, intra-hexamer correlations, which are basically those blue bonds, are giving a blue-red-blue signal, which means that this is characteristic of strong bonding rather than that there is some kind of bond splitting. Whereas if you look into the inter-hexamer correlations, which are those basically purple, this purple signal, you see that along the zigzag ladder there are displacive distortions, so you again have red-blue-red signal, but in other directions you see strong bonding. Okay, so this is my last slide. So the comparison of density of states that is calculated for global orthorhombic and local monoclinic structure from 370 Kelvin refinement reveals that there is actually near Fermi level a splitting of the order of 100 MeV in the distorted structure. And when you do the unfolded band structure in the brilliant zone of the orthorhombic unit cell, you also see that along this TRS direction, there is a small partial gap opening that is consistent with the splitting of density of states. If you consider structure that you obtain from the local refinements lower than 200 Kelvin, this suggests further complex oligomerization and development of 3D correlations between those long-range ordered hexamers. So that's that. Let me just conclude by saying that large ruthenium hexamer distortions are found associated with the orbital charge trimerization above the metal insulated transition and above the pseudo-gap phase, which presumably represents a local response to the electronic instability of the Fermi surface. And in that context, non-symmorphic symmetry protection is not operable locally
on a nanoscale. This presumably represents a precursor to pseudo-gap behavior. And we see that pseudo-gap transition is order-disorder in character, and that the states are, in the high-temperature metallic regime, correlated over 1.5 nanometers, or 2 hexamer units. This state is electronically distinct from the ground state, which is singlet trimers. And then the question is, of course, on this phase diagram, since we are probing the regime just above the pseudo-gap in the parent compound, whether actually those pseudo-gap fluctuations embodied in this hexamer kind of object are relevant for superconductivity, meaning is it the orbital charge sector that actually is somehow involved in the either superconducting mechanism or enhancement of DC. And so with that, I thank you for your attention.
Thank you very much. Questions, please?
I would like maybe to ask what is the symmetry of your superconducting state which relates into your system? For example,
the symmetry is
of
S.
your gap and...
So it's a single band S-wave.
S-wave.
S-wave. So the only unusual feature of the superconducting regime is that the upper critical field is linearly increasing with temperature and does not saturate at low temperature. So it is declared to be a conventional BCS superconductor. But
more questions? It's probably not the case. Then let's thank the speaker again. We come to the last speaker of today's session, Andrei Semyonov from Lebedev Institute, Moscow. He will announce the title of his talk.
Thanks to the organizers of this conference and to Andrei Zaikin who invites me here. And this is the title of my talk. And this is a short outline of my talk. First, I would like to discuss superconducting fluctuations, especially the quantum phase slips, and to discuss duality, what is it and why it is important, the Cooper pair localization, and in the end of my talk I present shortly some results which we obtained in this. It is well known that due to Mermin-Wagner-Hornberg theorem, there is no superconductivity in the dimensions lower than 2. So in 2 and 1 dimension, we have no superconductors. However, in the real life, we didn't work with the precise 2-dimensional, precise 1-dimensional systems, but we work with the quasi-1-dimensional, quasi-2-dimensional systems, which means that in the one direction, the size is much smaller than in the other direction. So here, for example, for quasi-1-dimensional system. And if we have the superconducting system such that in one direction the size is much smaller than the superconducting coherence length, that one can consider this system as one-dimensional, quasi-one-dimensional. And this is the system which I would like to talk about, and especially I will concentrate on the quasi-one-dimensional system. And since in the two and one-dimensional systems, the long-range order are destroyed by the quantum fluctuations, it means that in the quasi, one quasi two-dimensional system, the fluctuations plays a very important role and might change the behavior of the system. Okay. Okay. So, if we consider the quasi-one-dimensional superconductors, and it is well known that the order parameter, the main dynamical variable at low temperatures, and in my talk I will consider the temperature near zero. The main dynamical variable is the order parameter, which is a complex, valued, and it can be separated into the modulus of the order parameter and phase of the order parameter. And basically there are two types of the fluctuation in such a system, superconducting fluctuations. The first one is the small fluctuations of the modulus and of the phase of the order parameter. It is just some sort of ripples, yes, some sort of Gaussian small fluctuations. And also in such a quasi-one-dimensional systems, there is another kind of the fluctuations which called the phase slips, and especially quantum phase slips if we talk about the temperature near zero. And this is such a process where at some time moment the modulus of the order parameter goes to zero, and at this point the value of the phase of the order parameter becomes unrestricted, and after restoration it may jump up to 2 pi. So it is basically the very simple picture of such a quantum phase slips. It's just a vortex in the imaginary space, imaginary time-space system. And basically it's just a vortex where one can go around the phase slip. Then the 2 pi, there is a 2 pi winding of the phase. And here precisely the very simple theory which can describe such a phenomena. It's very simple action, which is just the Gaussian one. And I will show how the meaning of both terms. And even if we consider such a very simple action and take into account the compactness of the phase of the order parameter, it means that the phase and phase plus 2 pi is precisely physically the same state. Then we have the rich physical picture, including the quantum phase transition of the Brzezinski-Kosterlitz-Taulis type or Schmidt type. It depends on the precise system. At this transition, such an instanton, such a phase slips, due to interaction, either bound in pairs or unbound, and this changes the behavior of the system from the superconducting when the phase slips are bound, and to the insulating where they are unbound. Okay, this is very simple picture. However, we are interested in another kind of description and in another view. What is it in the real time? Before it was in the imaginary time, but now what it in the real time? And in the real time, the quantum phase slips, it's just a tunneling process. Let me show you. Suppose we have the phase configuration which is given by a red line here. And of course, due to compactness of the phase, the configuration shown here by red, where there is a sharp step in the phase, is precisely the same physical configuration of the phase, because we can change the value of the phase by 2 pi. And on the opposite side, let us consider the configuration of the phase, which is drawn here by blue line, which it's just where the step is just smeared. And what actually we have? We have two configurations. The first one is red, and the second one is blue. This configuration differs physically only in some small area of the size of the smearing size, which is of the order of the coherence length, superconducting coherence length. These two very similar configuration, but they're physically different because the total change of the phase in blue configuration and for red configuration across the wire is different by 2 pi. And phase ellipse is precisely the tunneling between these two very similar configuration, which produce the change of the phase difference across the wire. And it can be, one can see it as a tunneling of the flux quanta, yeah, because the winding of the phase is related to the flux, and it means that the flux quanta is tunnel across the superconducting wire. Okay. Okay, what will be the next? Suppose we have such a quantum phase slip process. And after such a process, the configuration of phase drawn here by red is produced, and after that it starts to evolve in time. And after such a tunneling process, we can describe it semi-classically. And for this, one can write down the simplest Hamiltonian, which is right in here, and it has basically two simple parts. The first one is the capacitive terms, and the second one is the kinetic conductive terms. So it's just basically two terms, and basically such a Hamiltonian is a Hamiltonian for the transmission line. And one can solve such dynamical systems because now the phase configuration in space and time solves the wave-like equation. One can solve it, and the result is the following. After that, the two steps goes in the opposite direction, in the one direction to the other direction. And if we use the Josephson relation, which relates the voltage to the derivative of the phase, then one can understand that this motion corresponds to the motion of the voltage pulses, which goes in the opposite direction with a speed which is equal to the simple speed of the plasmons in the transmission line. And after some time, they go to the detector of the voltage, and on the detector we will see the voltage pulses. And in the one direction or in the opposite direction, and the integral of each voltage pulse is equal to the flux quanta. One can easily check it. And from this very simple picture, one can obtain why the superconductor has the finite resistance, noise, and so on. Because if we put the current through the wire, then the probability for positive phase slips and negative phase slips becomes different, and the net average value over time of the voltage becomes non-zero. So that's why the quantum phase slips produce the voltage in the, and of course its fluctuation and so on, in the superconducting wire. Okay, let us how to understand this in a bit technical view, if you want to describe it. And in order to describe such a system, one can do it in the two steps. At first steps, one makes the phase the single valued by such a trivial transformation with just remove all sharp steps in the phase. And after that, one transforms so the initial variables to the dual one. Here phi is just the operator of the flux, and it is just an operator which has simple meaning. One can just look at this relation. It's a charge that passed through the point x up to the given time moment. So it means the derivative over time of this variable is just the current, and derivative over space variable is just the charge density. Yeah, it's very simple. And after that, one can transform the Hamiltonian to this one. This is very simple substitution. However, in such variables, one can write down the simplest, one can build up the simplest Hamiltonian which describes such a tunneling process. Of course, one can do it by just adding the operator that adds such a smeared step to the unwinded phase variable. So, and this Hamiltonian is just the cosine term. And if you want to speak roughly, then here should be not precisely this variable, but it's merit over the scale equal to the superconducting coherence length. Okay, this is the simplest Hamiltonian which describes such systems, such a kind of systems. And let us write down it again. And below I am write down you a Hamiltonian for the long Josephson junction, where we have now the phase is the phase difference along the Josephson junction, and also I add the current bias to the first system and the voltage bias to the corresponding Josephson junction. And one can see that these Hamiltonians are the same up to exchange of the phase and charge degrees of freedom. So it means that these two systems are dual to each other. Generally speaking, one can make the following, one has the following picture. Suppose we have such a system made of the superconductor, for example here, and suppose we consider the complementary system where we substitute all vacuum by the superconductor and all superconductor by vacuum. This is just the system where we've done this. And the system precisely the long Josephson junction. And after that, the statement is that these two systems are dual to each other, and in the superconductor we have the phase slips or tunneling of the fluxon, of the flux quanta, and in the Josephson junction we have the tunneling of the Cooper pairs. And if first system we have the current bias, in the second system we have voltage bias, and so on. So these two systems are dual to each other, and the precise duality transformation each stated here. We should interchange the charge of the Cooper pairs to the flux quanta, interchange the rate of the quantum phase slip creation to the critical current density, and interchange the inductance and capacitance. So it's just the duality, the phase charge duality. Okay, if we if we have such a system, it's basically the simple Sine-Gardon model, and it is well known that in such a Sine-Gardon model there is a quantum phase transition, which is just a transition of the Brzezinski-Kosterlitz-Taulis type, and this is a transition which is related to the bound and unbound of the Cooper pairs, or on the phase slips of the opposite sign. And this transition is controlled by the parameter lambda, which is given here. And if lambda greater than 2, then quantum phase slips are bound in pairs, and it means that the parameters, the system renormalized to the near free one, and one can use perturbative theory and so on. And this is the superconducting phase. However, if the lambda is less than 2, then the quantum phase slips moves freely, and the superconductivity in such a system are destroyed. However, and Konstantin Rutyunov also told about this, this is not such a simple, because the answer, does superconductivity destroy it in the system or not, depends on the scale, or otherwise depends on the property which we want to measure in such a system. If we consider the system on the large scale, for example, we want to measure the resistance of such a system, then it is a global property which is related to the phase coherence between the two opposite ends of the sample. Contrary, if we want to measure the local density of states, it is a property of the given point. And the interesting point that in the insulating phase in such systems, the locally superconductivity is still present. However, globally, the superconductivity due to effects of quantum phase slips are destroyed. It means that there exists some scale which can be found by considering the renormalization, group recreation, and scaling of such renormalization group recreation, below which the samples are superconducting one, and all the physics related to the superconductivity are present. And if we consider the samples greater such scale, then the superconductivity destroyed. And it means one can see on it as a localization of the Cooper pairs. So phase slips, which are just the tunneling of the flux quanta from one side to opposite, are randomly tunnels, and this produces the localization of the Cooper pairs living in such a wire. And basically such a localization is produced on the some space, on the some length equal LC, and written here. Okay, I'm going to the last part of my talk, more technical, where we present how to calculate the counted statistics of such a systems, of such a phase slips. And in order to understand this, it is necessary to evaluate the generating function, where V is the operator of voltage in such a system, and J is just the source. By taking the variation derivative over such a source, one can obtain all the cumulant of the voltage and all the statistic of voltage fluctuation in such a system. And here is the most general result which one can obtain using the perturbation theory in the QPS rate, and as I say, it works well in the superconducting phase and below the coherence length in the insulating state. And here's just the general result. And one can consider just the limiting case in order to understand the physics of such a general result. And the first limiting case is the limit of the zero frequencies, where one interested in the statistics of the average voltage, average over time voltage. And one can evaluate this and obtain that the generating function is like this. And this is precisely the generating function for the Poisson-like process. So, and where the value staying here, it's just the rate of such a Poissonian process. It is given by the following expression. And it means that on the large times, on the smaller frequency, the system behaves like the Poissonian process, where the phase slips is just the random jumps of the random voltage pulses. However, if you go to the finite, or it's just here, we can evaluate all the cumulants. It's just the result. However, if we come to the finite frequencies, we can also find all the cumulant, but of course only for some simple systems. And here just the simple system of the example of the short superconducting QPS constriction. And here just the grid function, which can be substituted into the general result. And we obtain the result for the all finite frequency voltage cumulants for any frequencies, even and odd and even, so for any value of frequencies. And here just the picture for the noise power. This is the third voltage cumulant in such a system. And this is my conclusion, and also the reference to our recent review paper, where you can find all the details and a lot of references to such results. And thank you for your attention, and bon appetit for our team.
So thank you for a great talk. So question is are your results confirmed experimentally, and can you create a software predicting the occurrence of phase slips in given electronic element, superconducting electronic?
About the experimental check of our results, of course, the Kostya Artyunov tells about the physics related to the phase slips and the Cooper pair localization. It was confirmed in, one can find it in our paper in the communication physics. What is related to the voltage and to average voltage of the superconducting wires, it's also observed in the experiments. What about the noise? It was observed, but there is no, there will be no comparison because it's not easy to justify that the noise which originates in such an experiment is precisely due to phase slips. It's there is some evidence, but not the smoking gun experiment. And of course we can predict, and but we don't have any software just. But all our results can be put into the can be used for calculation of the all necessary properties for such a system. So it's very general, and one can use it.
Yeah, maybe one more question. So there is a concept of a kind of like washboard potential concept that you are using, right, in the description of phase slips.
No.
But because you make a comparison with the Josephson effect. We make a comparison of with Josephson effect. Can you come to the slide?
Okay. At first, we don't use washboard potential concepts at all, but because it's a bit different situation. If you have the Josephson junction, then in Josephson junction, the modulus of the order parameter is destroyed in the insulating barrier in the Josephson junction. So you have two superconductors there. It modulus is destroyed. However, in our system, the superconductivity or the parameter, its modulus, it's precisely the same along the wire, and such a process is a dynamical process where by fluctuating, it's tunneling, it's some sort of the virtual process where virtually the modulus of the order parameter destroys to zero, phase wins, and the system restores. So basically it's a bit different systems. Of course, from the macroscopic point of view and on the level of the effective theory, one can write down the similar, it should have similar behavior, but microscopically it's a bit different, different mechanism, and so that's why the systems is interesting and why it is no trivial that in such systems one can see such sort of behavior. It's okay.
Because I mean, washboard potential is effective potential. It's not fully justified from BCS theory. That's why I'm asking.
But here I didn't use washboard potential. This theory is justified from the BCS theory because the BCS theory from the of course, I write here this is in some sort of the phenomenological manner, but of course we can derive this from the microscopic point of view, starting from the BCS theory by separating all the degrees of freedom, collective one from the fermionic one, integrating fermionic one and so on in the gauge invariant way, and so on. After such all the steps, you can find this in the such a review and in the references which can be found here. We can go down to such an effective theory, and of course, we have all the way. And on this way, we didn't use at all the washboard potential and so on. And of course, if you want to describe it macroscopically, so you should find out the precise form of the instanton in the imaging time for the whole action obtained after the integration of the, and yes, it is done by Zaikin and Golubov, and yes, we have all the understanding of it.
Maybe I can add just to clarify it once again. I mean, the washboard potential all people use depends on one variable, the phase, okay? Here, and the phase tunnels, yeah, between the minimum of this washboard potential can tunnel. Here, what tunnels is the field. So it's not just one variable, but it's a collection of variables because it's the order parameter field which depends on coordinate and on time, okay? And it is described by this action, and in fact, it's more complicated than this. So in this sense, it's completely different object.
This is the field which can be derived from the microscopic point of view. Yeah. So it's not, but of course it can be understood from the very simple phenological arguments, but of course, no. Okay.
Thank you so much. Thank you.
I have a question. Do you hear me?
Okay, so we start from Kostya then, perhaps.
Yeah, Andrei, thank you very much for your interesting talk. I'm a little bit confused about the introductory part of what you showed. When you showed these pulses propagating left and right from the phase slip event, I have a question, experimental one. Yes, exactly this. Does it mean that if we connect to our nanowire governed by quantum fluctuations a high-speed oscilloscope, we will see these pulses of voltages, positive and negative? Or what experimentalists can see is only the time-averaged voltage governed by Josephson relation?
Okay, This is a simple quasi-classical picture where you have such voltage pulses. But if you go into the quantum level, of course, this process becomes the quantum tunneling. And this is like the, for example, the tunneling of the, in the, for example, tunnel barrier. If you have the tunnel barrier, does it mean that you will see the current pulses where the integral equal to charge? Of course, no, because it is quantum process, and we can talk about it in some sort of the average, yeah? And this is precisely the same way. Of course, quasi-classically, this corresponds to the such pulses, but on the quantum level, you should average over all possible places where such a pulse, over all possible configurations and so on. And in general, you will see only the average voltage. However, such a nature of such voltage pulses originates in the presence of the short noise, because you know that the short noise is related to the quantization of the charge. And so if you want to understand how to see the presence of such voltage pulses, you should go to the voltage, and so our results on the short noise showed that there should be one can track that what is tunnels is just the flux quantum. So maybe I answer.
Okay.
Yeah, thank you. So the short answer is that for experimentalists, there is no chance to see individual voltage shots.
Yes, because the system is quantum one. Yeah, because of it. Yeah.
Okay, Vladimir?
Thank you for your nice presentation, and could you try to appreciate the possibility of transfer of your conclusions beyond quantum phase slips in one-dimensional superconductors? If this is another type of phase slips, which is thermally or current or field induced in a quasi one-dimensional, to which extent is your set of conclusions transferred beyond this narrow limits?
Okay. At first, if you have not the quasi one-dimensional systems, but this is, for example, stripe, then of course the physics will be the same, but now flux quantum will enter into the stripe and goes as a vortex across such a stripe and goes into from the opposite sides. So from such point of view, if you look microscopically and measuring something like the voltage fluctuation and so on, of course you will see precisely the same situation. However, if you have the wider strip, then the probability of such a tunneling becomes smaller and exponentially smaller. So it's, of course, it should be, but from the experimental point of view, it's may not occur. And first, of course, the phase charge duality also is a very general property, so it should present despite the quasi one-dimensional systems, but it will present in more complicated system. What is about the thermal phase slips? And if you go upper in temperature, then of course there will be the phase slips due to thermal activation, and some results can be transferred. However, I want to say that near the near the transition temperature, you can separate such a simple dynamics because you know that the Ginzburg-Landau equation is a nonlinear one, and so such a simple picture of for example, voltage pulses which flows and so on doesn't applicable because due to nonlinearity there will be a lot of interesting features. You should solve precisely the for example, Ginzburg-Landau-like equation, something like this near. And so technically, this situation might be the different. However, what is related to the general phenomena like the average voltage, voltage fluctuations like the short noise, it should present and so on. But technically, my results are applicable in the low temperature, so quantitatively. But qualitatively, of course, the behavior might be similar.
Okay, any more questions? Comments? Okay, seems to be not the case. Then let's thank speaker again. And we close the session.
Today we continue with the half plenary session. Umut Aydemir from Koç University. The title of the talk is Enhancement of Thermoelectric Efficiency in Semiconductors through Nanoparticle Inclusions. The stage is yours.
Thank you very much, dear Chair. So my name is Umut Aydemir from Koç University. I am actually the director of this Koç University Boron and Advanced Materials Application and Research Center. So today I will briefly describe you our center and then what kind of, let's say, like research activities are carried out in our center. And main focus will be on thermoelectrics. Okay, so this center is was founded in 2017 in collaboration with a company. And currently we have 28 researchers with 4 scientists, senior scientists, 2 postdocs, around 15 graduate students, 4 undergraduates, 2 technicians, and a visiting scholar. So our main research objectives are designing novel high-tech boron-based materials for advanced applications in the fields of energy, metallurgy, biomaterials, automotive and space industry, conducting groundbreaking interdisciplinary research in a broad spectrum of state-of-the-art materials, including thermoelectrics, superconductors, batteries, catalysts, hydrogen storage materials, laser crystals, and materials showing unusual properties like thermal contraction with heating. So we would like to patent materials with high potential of industrial applications, and we also initiate pilot scale production of these materials in collaboration with our industry partners. And last but not least, we establish a pioneer outreach program to develop an interest in boron and advanced materials research for whole Turkish community. Okay, now why boron? Maybe you are interested in why we are interested in or why we are doing research on boron-based materials. So let me tell you the motivation. So boron in industry is mainly used for glass fiber to make glass fiber, ceramics, borosilicate glass, in agriculture for fertilizers, and in drug and cosmetics. In more advanced applications, as you know, this is a magnesium diboride superconductor, which is superconducting around 40 K, which is actually relatively high TC. And then it is used in energy. You can make magnets with this magnesium diboride. Boron-10, an isotope of boron, is also a nuclear absorber, which can be used in nuclear power plants. Military use, boron carbide, for example, is a very mechanically stable material, and it is quite lightweight material. That is why it is used in armor. It can be used also in airbags. Now, the world boron production capacity for 2018 is around 4.1 million ton, and Turkey itself is providing almost like 2/3 of this boron production. Now look at the revenue. 2018, the total revenue is around $30 billion, which is quite big. But Turkey gets only 1 billion, which means we are producing 60% and getting only 3%. Now, our main motivation is to convert the boron from the mineral source to high-value materials. So, in this case, we are doing some energy-related research like superconductors, fuels and propellants, absorbers for nuclear reactions, or pyrotechnic materials. We do also make research on, for example, next-generation 2D materials. So we try to make borophene, which is the boron version of graphene. So which means instead of carbon, we have boron, and it shows like extremely interesting, let's say, like properties, even superseding the graphene. So we make also refractory materials, and we do some high-tech ceramics and etc. And we do collaboration with some other professors, and we are just like trying to produce biomaterials for cancer therapy. This is boron neutron capture therapy, or we try to produce therapeutic nanoparticles. And we do also prepare some composite materials or materials which can be used as missile fuels. Okay, besides boron-based materials, we do also other advanced materials for thermoelectrics. You can see this is a Curiosity rover, which is powered by these radioisotope thermoelectric generators. We do research on batteries, catalysts, for example, this boron-based magnesium diboride is also a very good catalyst. So in addition to these superconducting properties, it is also a very good catalyst which produce basically hydrogen as a clean energy source from water splitting. We work on superconductors, not only magnesium diboride, but even clatrates, for example. They show superconducting behavior. Some laser crystals we develop for niche applications, and we work on these materials displaying zero or negative thermal expansion. Most of the metallic materials expand as you heat them, but these materials, because of their unique crystal structure, they have either zero thermal expansion or contraction, negative thermal expansion. We do this with collaboration with other research partners. So just to show you our infrastructure, this is one of our lab with a laser flash apparatus here, ZEM3, resistivity measurement, thermal conductivity measurements, our XRD, thermal analysis with DSC, TG. We have glow box for air-sensitive materials. We have our own SPS to sinter powder materials, high temperature furnaces that we can heat up above 1500 C. Some other furnaces that we grow single crystals, for example, for vapor transport method. We do some battery research in this glow box as well. And here you can see that this is a cold isostatic press that we sinter the materials at low temperature, at room temperature, if we try to avoid high temperature annealing. So here are the companies that we are interacted with. So we do provide some service activities for, let's say, like governmental companies. They are mostly like national or like defense companies. So we also do collaborate with other or finance with other private companies. And we do collaborative research with some international and also the national universities here. Okay, so thermoelectrics. Today there were a couple of talks given by experts. They were describing the thermoelectric effect, but let me revisit here one more time. So out of 100% energy, still mostly from non-renewable energy sources like petroleum, coal, natural gas, you can see that only 1/3 of this energy is provided for energy, like for the energy services, which is the useful part of this energy. 2/3 is rejected as mainly waste heat. So our main motivation is to convert this waste heat into electricity to kind of like contribute to our global energy sustainability. Okay, these materials are solid-state materials, which means everything is happening through the atomic scale. They don't have any moving parts. They don't need maintenance. They have long and scalable life, and they can be scalable, which means you can do micro scale application to like large-scale applications. So for a very long time, they have been used for powering the spacecrafts, for example, Voyager, which is investigating the interstellar space more than 45 years now, is powered by these multi-mission thermoelectric generators. So for the current ones, for example, Mars Curiosity rover, this rover, and even the last one, the Perseverance, for example, that was sent a couple of years ago to Mars, they are still producing their energy through this multi-mission thermoelectric generator. So they use the radioisotope decay, the heat produced by a radioisotope decay of plutonium oxide, and convert this heat into electricity. So you can also convert waste heat in automotives or like automobiles, for example, to kind of like power the lighting, for example, in the car. You can just like use it for energy harvesting, for example, as a medical sensor or smart watches, basically. And then, besides these power applications, they can be used for cooling and thermal management, which means you can create these small refrigerators which needs more precise cooling and noise-free precise cooling. And then you can just like use it for cooling the car seats. Optoelectrics actually, or detectors, they need more, let's say, precise local cooling. So thermoelectrics can provide solutions for that. So here are the thermoelectric theory. These are based on the Seebeck effect. So this is for power generation and Peltier effect for cooling. So here we have NNP type semiconductors. And then if we apply this circuit, we create such a circuit and apply thermal gradient, then this produces voltage, because we force these charge carriers to move from hot side to the cold side, similar to the gas materials, for example, and this creates a potential difference. So this potential difference that you create per temperature gradient is called the Seebeck coefficient. For the same circuit, instead of applying the temperature gradient, if you apply current, then you create yourself some temperature gradient, which means you can use it as a Peltier cooler. So this part will be cooled, this part will be heated. You can dissipate this heat with some methods. So in the materials part, we have this ZT called the thermoelectric figure of merit, dimensionless thermoelectric figure of merit, related to the Seebeck coefficient square times the electrical conductivity divided by the thermal conductivity times the temperature. So for high thermoelectric efficiency, we try to get good electronic properties, but at the same time lower the thermal conductivity, which is quite demanding and hard. So if we go to the efficiency, so this is related, device efficiency is related to the Carnot efficiency times the function of this material ZT. And you can see that rather than having high ZT at one particular temperature, we target the high ZT over large temperature window so that we have high average ZT, basically. Okay, so these are the thermoelectric couples. You can see we have some metal substrate here, some ceramic parts. So you create the modules when you just like put these thermoelectric couples electrically in series and thermally in parallel, and like tens of them. Okay, so what are the ideal thermoelectric materials? So phonon glass electron crystal is telling these materials. So this is telling that the materials should have very good electronic conductor like perfect crystals, but at the same time, they should have low lattice thermal conductivity like glasses. So this is hard to make in one particular material because of this conflicting transport coefficients, because if you have large carrier concentrations, okay, so this is provided in the metals basically. Metals, they have large carrier concentration, but when the metals have large carrier concentration, they have low Seebeck coefficient. So on the other hand, for the semiconductors, you can see that they generally have low carrier concentration and large effective mass. So here you can see that the power factor, which is the multiplication of this Seebeck coefficient times the square of the Seebeck coefficient times the electrical conductivity, is maximized for basically the carrier concentrations within this window. So let's say 10 to the 19 to 10 to the 21 per centimeter cube of carriers. And this is kind of like valid for the heavily doped semiconductors. So you should tune the carrier concentration in a sense to tune the electronic properties. So for the thermal part, thermal conductivity part, you can see that this is composed of two contributions. One is the lattice thermal conductivity, another one is the electronic thermal conductivity. So this is kind of like Wiedemann-Franz law. So the electronic portion of thermal conductivity depends also on the electronic structure of the material. Now the only thing which is actually independent of the electronic structure is the lattice thermal conductivity. So it means we have to find some materials that kind of display good electronic properties and low thermal conductivity, and you can tune these properties either by charge carrier optimization or lowering the lattice thermal conductivity. So let me describe how we can do that. So the first thing that we have to establish for the good electronic transport is the band gap. Now materials should have a band gap, because if you don't have a band gap, then you have both kind of like carriers, both type of carriers. So this band gap should be basically small enough so that you can dope this material either p-type, as you can see here, the Fermi level in the valence band, or n-type as the Fermi level in the conduction band. But it should be also large enough, as I said, so that you don't have two separate n and p-type carriers like electrons and holes at the same time, which kills the Seebeck coefficient basically. Now what about the thermal conductivity? So for thermal conductivity, I told you that this is the electronic part is connected to the electronic structure through Wiedemann-Franz law. So the lattice one, you can see here, the lattice thermal conductivity, it is kind of like dependent on the specific heat times the phonon velocity and the phonon mean free path. So you can lower this relaxation length or the phonon mean-free path by introducing different scattering sources into the microstructure by nanoparticles, by introducing large density of grain boundaries, and also some point effects. In an alternative way, you can go from, let's say here, this is the silicon, the lattice thermal conductivity of silicon with respect to the temperature. The natural silicon has still high thermal conductivity, but if you go lower the dimensionality, let's say like to 3D, to 2D or 1D, and then at the end, if you have, let's say, like the amorphous one, just like make nanoparticles with the amorphous nature, then you can basically lower this lattice thermal conductivity to the glass regime. So you can also, as I said, introduce some nanograins, which means, let's say this is your grain structure, you have this grain sizes, large grain size. For example, if you grind this, you can create smaller grain size, which means you introduce a lot of densities, grain boundaries here, you increase the grain boundary density, and this is scattering more of the heat-carrying phonons and it can lower the thermal conductivity. So you can also create nanocomposites. So, which means you can, for example, introduce intentionally some, let's say, secondary phases either within the grains or at the grain boundaries, and they also act like phonon scattering centers. So you can, this is nicely shown, for example, for nanoparticles of lead telluride inside the silver telluride, or by using the phase diagram of these systems, you can create such eutectic structures, and these are like lamella structures of lead telluride and antimony telluride. They have also kind of like impact on lowering the thermal conductivity. So for the lattice part, we can also tune the velocity because this lattice thermal conductivity depends on the phonon velocity as well. Here, this is, as I say, like simple scheme showing that if you have small unit cell composed of exactly the same atoms, you have only one phonon mode here, longitudinal phonon mode, and the slope of this dispersion curve is giving you the phonon velocity. Now, if you introduce a secondary atom, you just increase the size of this crystal structure, then this one mode falls into two. If you introduce more, you increase the lattice, and then you shrink the Brillouin zone, and then you can see that you create a lot of optical high-frequency phonons as opposed to low energy acoustic phonons. And these phonons, you can see that they are flat, which means their phonon velocity is almost zero because the slope is zero. In this way, if you just increase the size, if you increase the number of atoms, different types of atoms, you basically have larger unit cells, which leads to more low-velocity optical modes that lowers substantially your thermal conductivity. This is nicely experimentally shown for a particular family of materials, which is called the Zintel phase. So you can see that this is lithium zinc antimonide, strontium zinc antimonide, all the way to ytterbium manganese antimonide. Similar materials, like the atoms are similar, but the difference is the complexity. You can see that this is only 6 atoms per unit cell, and you increase the unit cell size, you introduce different, let's say, like local environments. Here you can reach 208 atoms per unit cell. Large unit cell, very different local environment leads to lower thermal conductivity, experimentally shown. So this is this one, lithium zinc antimonide, and this is for the ytterbium manganese antimony. So this is extremely low lattice thermal conductivity. And you don't need to do anything. This family of material has complex unit cell which introduces or which shows already low thermal conductivity inherently. So now let me just tell you what is a Zintel phase. Maybe this is the first time you are hearing about it. So most traditional thermoelectric materials like lead telluride, silicon germanide, these are the materials used for this space applications. They are covalently bonded materials, you know, like lead telluride, silicon germanide, typical covalently bonded materials. And they are composed of these p-block elements. Zintel compounds contain both electropositive cations, as you can see here, these ones, that donate their valence electrons to the more electronegative, let's say these p-block elements, which use them to form the correct number of covalent bonds such that each element has a filled, basically, shell, which means it is kind of electronic transfer from the cation to the anion. And this electronic transfer leads particular connectivity of the atoms. So, and I mean, this cation can be, again, these alkali metals, alkali earth metals, rare earths, even transition metals, and generally the anionic part is the p block element. Now, these interfaces, they are unique because they have an anionic substructure. You can see here different anionic substructures, zero-dimensional, one-dimensional, two-dimensional, layered-like, or even three-dimensional structures. They have strong directional two-electron, two-center covalent bonds, which accommodate in the cavities, as you can see, these blue atoms, the cations. These cations act like soft, non-directional. They have soft, non-directional ionic bonds with the covalent framework. So they are kind of like composite materials in atomic scale. So most of these materials inherently show p-type properties. So 122, 526, 313, 14111, 122, they inherently show p-type behavior because of these cation vacancies. Generally, when you make them, you observe that there is a very stable defect in the structure, which is a cationic defect. Okay? Calcium, magnesium, or whatever. They show inherently p-type behavior. But only recently, there was a paper coming out from the Panasonic group. They just showed that this material, magnesium 3 antimony 2, which is a typical zintal phase with some magnesium deficiency, it was showing p-type behavior so far. It can be made n-type, and the n-type analog can show even better thermoelectric efficiency. So they showed that you can make this n-type, and you can see that the ZT is generally 1 for state-of-the-art materials, but this easily reaches to 1.5 at relatively high temperatures. To make this n-type, there is a unique strategy. You have to add excess magnesium. When you start making this material, you have to add some excess magnesium to suppress the formation of this magnesium defects, which leads to this p-type character. So we knew that you can make this material n-type. But then we just thought, how can we improve the thermoelectric efficiency, or what else we can do? So we applied a melt centrifugation method, what we call melt centrifugation method to this material. We used this melt centrifugation technique on bismuth antimony telluride, which is the best low temperature material actually. So the idea is this: you add intentionally an element, for example tellurium, inside this material, bismuth antimony telluride plus some excess tellurium. And with a technique, you just remove this molten tellurium at high temperature. So this could be done with spark plasma sintering. What we did is this: we just put a little bit of tellurium, excess tellurium inside. We just put this material in an oven, high temperature, and then we quickly took away it from the oven and made the mass centrifugation and removed the tellurium from this phase. And we saw that in bismuth antimony telluride, you can have a lot of grain boundaries, ordered grain boundaries, and within the grains, we have a lot of lattice dislocations. You can see that in like lattice dislocation networks or like regular lattice dislocations. And this lowered the thermal conductivity substantially. This is a non-centrifuged material, and you can see that you can lower it to 50% thermal conductivity, and ZT can be also improved a lot. Okay, idea was this: as I said, you have bismuth antimony telluride. If you add tellurium, you have this eutectic point here. If you just heat this material around 500 degrees, you can remove this melt, and you can create such microstructural features. So we thought, okay, why not applying this to magnesium antimonite? Why? Because the nature is similar. Here you can see this is magnesium 3 antimony 2. Here we have magnesium, and between magnesium and magnesium 3 antimony 2, we see also such a eutectic temperature here. So we just went a little bit higher than 650, maybe 750, by adding excess magnesium and applied this technique. So we added 20 and 46 weight % excess magnesium, and then did some research to see the effect of it. So this is done in situ and external addition. Let me explain it to you here. So you can put all these materials in a steel vial, do high energy ball milling, let's say 2 hours of high energy ball milling. If you add the magnesium at the very beginning, this is in situ. If you add magnesium after you do this 2 hours ball milling, if you add the external magnesium afterwards, this is called the ex situ preparation. So this will lead to powder material. You do sintering with spark plasma sintering at such certain condition to make this bulk material. And then we seal this bulk material in a quartz ampule under protective atmosphere, because if you take this, put it in an oven, it will be oxidized. To avoid that, we just put it in a quartz tube and then put this in an oven. Did a quick centrifugation. You can see that the magnesium at the molten state, it just comes out from the bulk piece, and you can clean this and see that, investigate the microstructure. Of course, the first thing we do is XRD for phase analysis, TEM, SEM for the microstructure analysis, LFA for thermal conductivity, and ZEM3 for the electronic transport characterization. So this is the XRD diagram. This is the theoretical pattern. You can see that this is magnesium 3 antimony 2 as it is. Then we add a little bit of bismuth and tellurium to basically tune the electronic properties, and then add extra magnesium. By adding extra magnesium, you can see that sometimes even we introduce this melt centrifugation, there is some residual magnesium left in the structure, microstructure. You cannot 100% remove it with this one, but we could also remove it 100%. So it depends on the experimental conditions. So this is the microstructure with TEM without melt centrifugation. You can see that very condensed, highly condensed, regular microstructure, let's say, and you can see that this is the average grain size, couple of 100 nanometer. What happens if we apply this melt centrifugation? We create large pores, as you can see here, but at the same time, small pores, which means microscale pores or like nanoscale pores. At the same time, you can see that we create these ordered grain boundaries. They are nicely ordered, right? It is completely different than these grain boundaries. Plus, we show that we have also some lattice dislocations within these grains. And we hope that this substantially reduces the thermal conductivity. So here is the electronic transport characteristics. This is magnesium antimonite. Resistivity is quite high, as you can see. If we dope it with bismuth and antimony, bismuth and tellurium, we can just like lower it to here, the resistivity. And then with this melt centrifugation technique, we can also tune the electronic properties together with the Seebeck coefficient. You can see that we have high, like low Seebeck coefficient with high carrier concentration, or high Seebeck coefficient with low carrier concentration. So the thing is this. You see that the power factor is still high for this MSBT phase, in which we don't apply any melt centrifugation. Okay? So we just checked the weighted mobility here. You can see that this material is around, let's say, like 70–75% dense, which means there are 25% kind of like voids or vacancy, but still the weighted mobility is not much lower than the other bulk materials, in which the density is around 98–99%. It is quite good, which means electronic transport is not severely affected by these methods, although the power factor is slightly low. So power factor is slightly low, but you can see that the thermal conductivity is substantially low. This is undoped, this is doped material around 1.2. When we do melt centrifugation, the total thermal conductivity is 50% reduced. And lattice thermal conductivity as well. So this overall leads to around 43% enhancement if you just compare it with the MSBT phase. You can see it here. And if you calculate the device ZT, we can see that we can reach around 1 at this temperature, and the theoretical efficiency of this device would lead to around 12%. So these are not experimental, but theoretically calculated efficiencies. Okay, so far it was for magnesium antimonite. We did some research also for the bismuth antimony telluride and bismuth selenide telluride. These are the low temperature materials that are mainly used for Peltier coolers. So you can see that this is the P-type, this is for the N-type materials. For the low temperature, they are kind of like the best materials. So bismuth antimony telluride, BST phase, is very good for the P-type, and bismuth selenide telluride is very good for the N-type. So the others cannot compete except for the magnesium antimonide so far. So here are the unique crystal structure of this. So we see in this crystal structure these layers of bismuth tellurides, which is called quintuple layers. So here in the microstructure, you can see that in the crystal structure, we have these bismuth atoms octahedrally coordinated with the selenium, with the tellurium. And you can see that if you just like do kind of like solid solution of bismuth telluride with the antimony telluride, you can also engineer the mobility, effective mass, and the band gap. And we just like focused on these two materials. One is with bismuth 0.3 and the other one is bismuth 0.5. For the selenium case, you can do the same. You can just like basically do solid solution of bismuth telluride with the bismuth selenide. They have the same crystal structure, which means you can combine them in any ratio you want, and you can also optimize their transport properties. So now we saw that in literature, copper is a very good dopant to basically optimize the thermoelectric properties of bismuth telluride. And while we saw this paper, we were basically making another research on copper telluride. So this copper telluride is a synthetic ricardite mineral. It shows nice properties. Like here, you can see that you can just straightforwardly make it with solid state synthesis. You see that this is very good crystalline, purple-like crystalline material. So you can make it with this method. And the crystal structure is also kind of layered-like. It doesn't show here, but it is like layered-like structure. So here you can see that we have very nice grain distribution. So this is the polarized optical image, optical light image. So you can see that very nice grains oriented in different ways. It's like an art. And the good thing with this material is this. At low temperature, this material is undergoing a phase transition at around 150 C. And at little higher temperature, around 350 C, it undergoes another phase transition. And this phase transition nature is reversible, which means you heat it, you see these phase transitions, you cool it, you see the same phase transitions at around the same temperature. And at low temperature, this shows a metallic character, which means here the ZT is almost negligible. And after this transition, you can see that suddenly the ZT goes up quite a bit. Still low, around 0.2, but it is promising. Now, as a copper source actually, or metallic nature, we just put this material in bismuth antimony telluride. So here we prepared the bismuth antimony telluride, solid state synthesis, grind it, put it here in a vial, still vial, added copper telluride, did XRD analysis, SPS, LFA, and all the other analysis, transport characteristics. And these are the X-ray diagram. So here, this is the theoretical pattern for copper. This is copper telluride. This is the bismuth antimony telluride. Here, you can see different, the black ones are the bismuth antimony telluride. The red one is copper telluride. So almost single-phase bismuth antimony telluride, no detectable copper telluride. So these are the copper telluride because the amounts of doping here, you can see it is quite slow. This is X from 0 all the way up to 0.15. Small amount of doping. Similarly, this is the BST5, which is bismuth 0.5. This is BST 3-phase, which is BST 3-phase. Okay, here are the microstructure. You can see nicely that these are the grain boundaries, very good oriented, I mean like not oriented, but let's say like well-resolved grain boundaries. And at the grain boundaries, we see mostly copper telluride. Copper telluride that we introduced there are mostly decorating the grain boundaries. So this is good because this is a metallic material, might help with the electronic conductivity, but at the same time, it is a secondary phase, can lower the thermal conductivity. So here you can see this is the mapping, elemental mapping. This part, so this is this region. You can see that this part is bismuth antimony telluride, and here this black one means this is antimony deficient, but copper excess. So which means this is copper telluride, and this is bismuth antimony telluride. This is the same. You can see that this is copper telluride, and the rest is bismuth antimony telluride. So this is the optical images. this is the cross-plane direction, this 2, and this is in-plane direction. There is a kind of like striking difference between them. You can see that in the in-plane direction, we just see these very nice layers of bismuth antimony telluride, which means main orientation is towards the in-plane direction. This is the perpendicular to the SPS direction. This is also nice because this can also improve the electronic transport through in-plane direction. So here are the transport characteristics. You can see that this is undoped material, low electrical conductivity. If you dope it with copper telluride, you can see that you can really tune with the copper telluride amount, the electronic conductivity goes up all the way. And Seebeck coefficient, in similar manner, you can see that they are high because carrier concentration is probably low here. And as you increase the copper telluride amount, carrier concentration, probably through copper doping, for example, of this material, is getting higher, and Seebeck coefficient gets lower. Thermal conductivity, of course, it's a metallic material, which means metallicity actually increases the thermal conductivity as well. Okay, let's see the overall effect. So this is kind of like no heat, nothing like our typical BSC. This red one is that we made 10 minutes of ball milling, and the others is 10-minute ball milling plus the copper telluride addition. So still, at low temperature, you can see that this is comparable, like our best material is comparable at low temperature with the 10-minute ball milled material, but at slightly high temperature, like 450 K, it outperforms. Like we reach a ZT around 1.3. It is quite important improvement for this material. So this was cross-plane direction. We see similar effect in the in-plane direction. The transitions are like the same, almost higher electrical conductivity, lower Seebeck, little bit higher thermal conductivity, but still, especially, so this is 1.2 around when 10-minute ball milling is applied, and at higher temperatures, still, copper telluride addition of, let's say, 0.025 gives much higher ZT values, which means by introducing this nanoscale secondary phases, you can optimize the thermoelectric efficiencies or performance of these materials. So in addition to the transport characteristics, it is better to also check the micro hardness, or let's say like the mechanical properties of these materials, because when you do module applications, we want to have durable materials. Here you can see that this is a synthesized materials. They are black. This is bismuth 0.5. This is bismuth 0.3. When we add copper telluride in cross-plane or in in-plane direction for both of the cases, we see substantial increase in the micro hardness, the mechanical properties of this material. Okay, so here I need to acknowledge these funding sources, let's say, including TÜBİTAK. So this is our kind of like Kuban researchers, including my daughter, Lisa, my catalyst, 2-year-old girl. Hopefully she will join me this evening. So with her contribution, I could finalize this work. And I would like to thank you for your attention.
Thank you.
Yep.
Any questions?
Thank you very much. I feel like I have been refreshed about the thermoelectric field because of your great presentation.
Thank you.
So I have just a couple questions about your zintal phase materials.
Sure.
Zintolate. So you said that magnesium looks like play an important role in the transport properties of these materials.
Mm-hmm.
So have you ever tried like a calcium or sodium instead of the magnesium? What's the magnesium is preferred?
Okay, so you can tune the properties by adding sodium or other elements, because magnesium is, let's say, like 2 plus here in magnesium 3 antimony 2. If you add sodium, it means you are replacing 2 plus with 1 plus. So you are pushing it to the p-type material. So our motivation here is not to touch p-type, because we know that p-type ZT is much lower than the n-type ZT. That's why we were kind of like focusing on magnesium, not adding any alkali metals. But you are right, so instead of magnesium, you can dope it with calcium, 2 plus. Maybe you can lower the thermal conductivity even further. We didn't do it, but this is doable. It's a meaningful strategy. The only thing is this, maybe you will end up with calcium antimonide as opposed to like magnesium calcium antimonide. Because magnesium antimonide, calcium antimoниdes, separately, they are very stable phases.
Thank you.
Yep.
So maybe the last question I can ask you, the copper 3 tellurides is the same crystal structure of the antimon telluride, right?
No, they are completely different.
Completely
Copper 3 telluride has, I think, orthorhombic structure at the low temperature, and it goes to a tetragonal structure, and then to hexagonal structure. Like copper 3 tellurium 2 has different structure with the antimon telluride.
Okay, then your motivation for this study was like just to put some different nanophases in the structure, or do you have some idea to?
Yeah, exactly. So
Okay.
let me just show you here. Maybe I just like didn't mention it
And
quite
also
well.
maybe did you try for N-type too?
Yeah, so the idea was this. So when we were dealing with this research, we just like found that there are a couple of research publications, let's say, they are dealing with this bismuth telluride with doping copper, which means they are doping this material with copper and getting better efficiencies. Now, okay, we don't want to repeat that, but we have copper telluride, which can act like a copper source, and at the same time, this shows this phase transition, strange phase transition, and it is metallic. We thought like, okay, rather than using pure copper, why don't we use copper telluride? Why? Because copper is a mobile ion in copper telluride as well. It has high ionic mobility. It can diffuse easily to bismuth antimony telluride, perfectly fine. And we have also tellurium. That's good because the main material has also tellurium, which means if there is any loss of tellurium, this can compensate this loss as well. So this was kind of like two different aspects that we introduced into the structure, and then saw that this is really working quite nice. So we didn't publish this paper yet. We are just writing it.
It's a very good idea.
Right, right.
So about the N-type bismuth telluride, did you like put some?
Yeah, I didn't show it here. Yes, we tried some bismuth selenide telluride, and then rather than copper telluride, we just dope it with boron actually, carbon-coated boron or boron, and we could increase the ZT quite a bit. We did it as well. So around 20–30% increase, right?
Because the biggest problem for bismuth antimon telluride is
N-type, exactly. We did it as well, but here I just showed these two results because this paper is also not written yet.
Yes. And also that's interesting that the mechanical properties also improve with this.
Right, exactly, exactly. When you add,
design.
I mean, this is the usual thing. Generally, this bismuth antimony telluride, as you know, very anisotropic material. There are some cleavage planes. It easily like breaks down the material. When you add this metallic, ductile material, it improves the mechanical properties. Meaningful.
Thank you.
Yeah.
Any other questions?
Yep. Here. Sorry. Bir tane daha sor. Maybe if you just say.
No. Okay, so you had a figure where you showed that with 0% copper telluride, the temperature trend was down in this
Let me
figure
show.
of merit. It's a bit later, I think.
Here
yes,
you mean?
Yes. Now I have this very simple question. Both figure of merit and Seebeck coefficient have exactly the opposite temperature trend at 0% copper telluride and not 0%. Okay?
This one you mean?
Yes.
The red
this
one.
one sticks out.
Right, like
so
this.
Have you some kind of simple, quick way to understand that?
Yes, sure. You mean Seebeck coefficient, right? Yes. This going down of the Seebeck coefficient as opposed to others.
Yes.
Kind of, yeah. So that is the thing. Now, you can see that this is bismuth antimony telluride. Again, no copper telluride addition. This is called S-synthesized. The main difference between the black and the red is this. In the red, you may remember that I am telling you that this copper telluride is added by 10-minute ball milling after we synthesize this material. Now, we synthesize this material, did 10-minute ball milling without any copper telluride addition. Then the other copper tellurides also are done in the same way, 10-minute ball milling with 10-minute ball milling. So we wanted to show what is changing here, right? So the main thing is this: bismuth antimony telluride has very small band gap. You know, if we do ball milling in this material, probably we are also changing the composition and the electronic structure, which means probably we are shrinking the band gap. And if we shrink the band gap, as you know, if you increase the temperature, at one point, the minority carriers, let's say this is p-type material, the electrons will jump from valence band to conduction band, which means this will basically kill the Seebeck coefficient. So what is going on here is purely minority carrier effect, actually. We are activating the electrons as opposed to holes because of the shrinkage of the band gap due to purely ball milling. Because this ball milling, in the ball milling, we are kind of like forcing the steel balls to hit each other, and then we have powder material here, and this is creating local heating and local pressure, and this is probably introducing a lot of additional defect to the crystal structure and kind of manipulating the band structure. Yeah.
Thank you.
Okay, thank you very much.
Our next session will start at 3 p.m. according to the program, but maybe we can have a 10-minute break and start at 10 past 3 p.m.
Hello, Professor Ivan. This is Ali Gencer speaking with low voice.
Yeah, nice to see you, Professor Gencer.
How are you?
Yeah. I'm fine, thank you.
Okay, how is life in Nanjing at the moment?
Well, all the things are fine. The only thing is the pandemic control is very strict, so that's only a problem. But all the work and experimental work in the lab are fine. Yeah, so all the things are going smoothly.
Well, great to see you, having you as a plenary speaker, and we still have
Yeah.
many people at the
Yes.
conference, although it's last day.
Yeah, thank you so much for the nice invitation. I really love to go to the beautiful country, Turkey, to see the beautiful place, Bodrum.
Yes,
but it's a pity. It's a pity because of pandemic control in China. Yeah, very strict, very strict. Yeah, I cannot get the visa, get the visa passport. Yeah.
Yes, we hope the pandemic will
Okay.
be over, as we will have next ICSM here too in next May.
Yes, to be over very soon. Yeah, I think.
From
Yeah.
7 to 13 May, and we will be happy to have you among us, and let's keep in touch. And we will probably start in a few minutes. I think we are having some people. I will give this moderation to dear colleague Professor Ali Bozbey, so we will be happy to hear you.
Okay.
Welcome to the last plenary session of the conference. Our first speaker is Haihu Wen from Nanjing University from China. His talk is about local pairing format and interplay between superconductivity and antiferromagnetism in cuprate superconductors. Professor Wen, please, stage is yours.
Okay, thank you, Chairman. Thank you. First of all, let me thank Professor Gencer for the very nice invitation and for the nice efforts for this beautiful and nice conference. It's quite pity, as I said, that I could not attend the conference locally because the pandemic control in China. Turkey is a beautiful country and very, very pleasant and friendly. So I really want to visit Turkey many times. Okay. So today I want to give the talk about a strong local pairing, interplay between superconductivity and antiferromagnetism in cuprate superconductors. It sounds a very old story, but I will show new data. 3 pieces of new work coming out from my group in Nanjing University. My name is Haihu Wen, so you can see the photos of the young brilliant student in the group and my young colleague Huang Yang. So the work many experimentally done in the group and also samples from several other places. I will mention these collaborators later, okay? So we know that cuprate was found in 1986. And in 1988, very quickly, the Nobel Prize was issued to Benos and Miller. And the typical structure for the cuprate is this carboxygen plan. Okay, we know that this is the major player for cuprate for superconductivity, and between them it is a charged reservoir layer. Okay, actually, after so many years study, nowadays I probably can conclude for some consensus yet. Now, for example, the parent phase is antiferromagnetic multi-insulator, and the electron conduction and the superconductivity arise from doping a multi-insulator. And I personally believe that the D-wave pairing has been proved, which reflect the repulsive induced pairing. So it must be most likely the magnetic origin. Otherwise, we cannot get this repulsive induced pairing. Okay. Can you see my mouse here on the screen? It's moving. Chair. Okay. So this is a generic phase diagram for the cuprate superconductors. We know that starting from this parent phase is the undoped parent phase. Which is antiferromagnetic order, and gradually superconductivity comes in. Okay, so this is And on the t equals 0 state, you can see a lot of competing orders. So there are many competing orders. These orders compete or coexist with the superconductivity. However, many questions remains unclear. For example, how is the Mott-Nace related gap filled up together with the vanishing of the long-range anti-Fermi order? And how do the low energy density state accumulate near EF, the Fermi energy? This is very important, the second part, because in the correlated system, we don't know how the low energy density state accumulate. We need some direct data, direct evidence for that, okay? And also whether the local parent, Cooper parent really exists and in what form, and whether the anti-Fermi order can re-emerge in the superconducting state, okay, if it's a competing state order, okay? And how far is the normal state from the Fermi liquid picture? So this is some very important topic I want to address today through our data, okay? So my talk is outlined as the following: 3 pieces of recent work. One, I will show you a so-called local pairing through a very interesting confined pneumatic state within the basic 4A by 4A plaquettes in extremely underdoped BISCO 2201. The second part, I will show you direct visualization of a re-emergent static incommensurate F order, even in the optimally doped BISCO 2212, which indeed shows that the anti-Fermi order comes out with the gap intact. Okay, so the superconducting parent gap are still there. And then finally show you another piece. Third piece is about the Plancking dissipation in the normal state. And also want to show you the so-called Ginsburg-Landau type apocritic field in this optimally doped BISCO 2201. And finally, I give some concluding remarks, okay? So this is the phase diagram for the BISCO 2201 showing here. This is the crystal structure, okay? So you can see that up to about 10% doping, always the people draw the phase diagram that it is anti-Fermi order. But besides some neutron data, show some trace that actually is not clear. We don't have direct evidence for the so-called anti-Fermi order. I will show the direct evidence today. And also in the neighbor, it is a superconducting dome. And the boundary locates at about 10% doping, okay? So here we take 2 special doped sample. One is 8 doping, one is 10% doping. So you can see we measure the resistivity of the sample single crystal. So this 8% doping shows a very huge and strong insulating behavior. And the 10% doping, the resistivity becomes much lower, but however, still shows a semiconducting behavior, okay? And please remember that the superconductivity just appears at the boundary of the 10%, okay? About the parent phase and the underdoped side, actually in the cuprate nowadays, we know that it is due to the strong correlation. And the correlation, this so-called correlation gap, U, is quite large. However, in the cuprate, we know that this lower half of the band and the oxygen band are hybridized. So in that case, we have so-called charge transfer gap, which is also Mott-Nace derivative gap, okay? And the early picture about superconductivity, it was very strict and very interesting, says that the parent phase is due to this kind of spin liquid, and each spin singlet is just a Cooper pair. When you dope holes, this singlet will move, they will behave like superconductor. However, later experiments show that the parent phase is anti-Fermi order, and the evidence for this RVB state is still lacking, okay? So this picture may not be completely correct, okay? However, we can still get some feeling that the parent phase is a multi-insulator, and the local super exchange J produced by this correlation leads to the anti-Fermi state. So this theoretically can get the precise solution. And the superconductivity emerges when some effective density state appear near the Fermi energy. But how the effective density state appear in the correlated system, that's a question and a big problem, okay? And how do the charges move on this doped multi-insulator? There are many models. As I said, the first, for example, the so-called sunrise singlet based on the Hubbard model. So the holes are doped to the oxygen side. and they will form a singlet with the nearby spin of couple. Okay, that one move lead to the conduction, and also the sorry. Yes, and also the quasi-particle, like the so-called coherent quasi-particle based on TJ model by Xiaogan Wen and Patrick Lee proposed, and also through phase separation and stripe phase proposed by Emery and Kieferson and Itel. Okay, and also very interestingly, based on the RVB picture, Professor Zhengyu Wang in Tsinghua University proposed that it could be form this kind of phase string effect that leads to the pairing and the charge moving. Okay, and also a model by Professor Wei Ku et al. Just generally they call the charges in the normal state as the bosons, which is called a bosonic liquid. So there are many models. Okay. So first, let me show you the data, the transport data for this 10% doping, supposed to be at the boundary. So you can see that this single crystal, if we measure resistivity, when the current is large, then we see a huge insulating behavior. Okay. However, when we lower down the current, then the superconductivity somehow sets in. Also, the transition is not complete. Okay. And for some samples, we don't see, even with the smallest current, we don't see this transition. If we blow up, take the sample 2, blow up the transition part with a different current, you can see that even for this sample, with a very small current, we see the superconducting transition. Okay, and this transition seems to can be suppressed by the current and also by magnetic field. You can see that. So with a small current, you can see superconducting transition. However, when you apply a field, then transition gradually smooth out. So even for this so-called sample on the boundary, supposed to be a long superconducting sample, but actually when the measuring current is small, then you see superconducting transition. So this is not a matter of the sample quality. They are single crystal samples. It is the intrinsic property of the sample at this doping level. It says that we have a fragile and superconductivity on top of a strong correlation background. Okay, even for this sample on the doping level. Then we use a spin polarized STM to measure whether we can see the so-called anti-Feynman order. So we thank to Professor Wissendanger to help us and give some advice for us to build up this STM with the spin polarized ability. And we published some papers based on that kind of study. So we first characterize the spin tip with so-called ion tellurium. And this sample, you know that it is antiferromagnetic, okay, which has a so-called bicollinear antiferromagnetic. So we measure spin up and spin down topography with subtract. Then we see this kind of bicollinear structure. Let me move here. And by doing the Fourier transform, you can clearly see this spot. This is due to the typical bicollinear antiferromagnetic order in the ion tellurium. So that's a check to the tip. And then we measure on this so-called 8% doping and 10% doping. You can see we use a spin down and a spin up to measure this topography. We subtract. Then we can see this kind of a blue and red, which shows the intensity of this subtraction. You can see that it is the anti-Feynman order clearly visualized by the spin polarized data. Doing Fourier transform, you can clearly see that the anti-Feynman order. So I must say that this is the first time, very first time, to directly visualize the anti-Feynman order in the cuprate. Okay, and for the 10% doping, then you don't. We also measure spin down, spin up. Then we subtract. We don't see such order. After Fourier transform, we also don't see the spots. So that means that the anti-Feynman order exists at 8% doping sample, but on 10% doping sample, it does not exist. Then we take the 8% doping sample, we measure tunneling spectrum from the area with anti-Feynman order to the area without. Then you can see that the tunneling spectrum changed from a so-called charge transfer gap region. So the gap is about 1.5 milli EV, okay, 1.5 EV, which is almost featureless in the region with anti-Feynman order. However, when you move into the region without this anti-Feynman order, then you will see that some kind of density state piles up in a very wide energy area. And the Fermi energy is pinned here, okay? So you can see this kind of hump. This is due to the density state, quasi-particle density state through the doping. If we use this line as a subtract all the curves, okay, as a background to subtract all the curves, then you will see that once you go to the region without anti-Fermi order, you see this kind of density state piling up in this charge transfer gap, okay? And which forming a so-called large pseudo gap with energy about 200 millieV. There is a hump here, okay? So this is a quasi-particle doped into the anti-Fermi order in the model gap, charge transfer gap to form this kind of density state. It is quite interesting to mention that actually in these iridates, Alain Milan's group also measured tunneling spectrum. They also see this kind of large pseudo gap. So for the strong correlated system, it seems they are behaving in a very similar way. And for the 10% doping, then we found that actually in the real space on the density state mapping, you can see a lot of blocks, okay, this kind of little blocks with the 3 bars inside, okay, 3 density state bars inside. We do the Fourier transform, then we see 2 scattering spots. One is 1/4, okay, another one is a 3/4. Okay, this one means that we have this 4A by 4A block, okay? And this one corresponds to the 3 bars within each block. So if we measure the tunneling spectrum, from outside of the block to inside the block, outside the block, it shows some kind of featureness. Inside the block, you see this density state again, okay, this density state by subtracting the background, okay. Let me continue. So then we pay attention to this particular block of the 4A by 4A, and we figure out the atoms of the couple and oxygen, okay. And in that case, you can see that this tunneling spectrum, if we measure on the boundary, we don't have this low energy density state. We see a large V-shaped gap without a low energy density state. However, if we move into the block, let's say on the central bar, then we see that a low energy density state comes out clearly and with a small gap. And this gap is about 20 millieV. This mapping was measured on 20 millieV. So it seems that this very unique block 4A by 4A is very important. And it shows this kind of internal pneumatic state of density state, low energy density state, okay? That shows some kind of small gap, which looks like the superconducting gap, okay? Then we make a cut, a crossing, this central bar. Then you will see that actually on the oxygen side, we see some kind of peak and the knees, which means that the whole doped induced density state has some kind of maximum or knees near the oxygen, which strongly suggests that the holes are really doped to the oxygen side. So our data directly prove that the doped holes are really going into the oxygen orbitals, many on the central oxygen 2 and the oxygen 3, as pointed out by Emery and Zhang Rice in the early studies, okay? So in that case, we plot this cartoon picture within this 4A by 4A, and we have the density state of this kind of parallel bars. This density state is high and forming a small gap, which is nearby the Fermi energy, which is very important, we think, for the pairing, okay? So this slide shows a control experiment to prove that the holes are doped to the central oxygen side. So you can see these peaks appear on the oxygen 2, oxygen 3, okay? So this as a control experiment. So we have measured for such. And to count the hole number. Suppose that we have 2 holes on 1 plaquette, then for this 10% doping, we expect about 313 plaquettes. Okay, this kind of pneumatic 4A by 4A plaquette. And we did the analysis, we found that the total number is about 297. So which is 0.019, 9.5% doping, which is close to the nominal doping. So this slide shows that we probably have 2 holes are doped to 1 block that form a pair, and that to form this kind of 4A by 4A, a very unique structure. Okay, so that's a basic pairing element. And for our 4A by 4A structure with internal pneumatic structure, one of the probability it is due to the pairing density wave. Okay, and that one gives the low energy gap. About the pairing density waves, there are a lot of studies from Shims-Davis group and from Professor Yao Yuan's group. Okay, so either 4A or 8A, some measurement. Okay, and also even in the superconducting sample for this CCOC, you can see that for the superconducting sample, Hanaguri-san and in Shims-Davis group by that time also see this kind of 4A by 4A plaquette. And within that, they also see this 3/4, okay? And if the blow up, you can also see some kind of 3 bars of density state that's corresponding to this 3/4. So for that data, we can conclude that the 4A by 4A checkboard is quite universal, even in the very underdoped sample, but that one is not due to the quasi-particle interference. And we see this very unidirectional 3 bars of density state within the block, even for the superconducting sample. And also for other samples with a different area, you can see this big hump, pseudo gap, large pseudo gap, and a low energy gap. And the data looks very similar like ours. Even our sample is not superconducting and a very similar energy. So in that case, so the second probability for the small energy, small density, the density state at a low energy under the gap is due to the precursor gap for superconductivity. Okay, so in that case, here I show you 3 pieces of work. This one on BISCO 2201, and this is also in this optimally doped last time BISCO 2201, and this is overdoped in this paper by Professor Yao Yuan's group, first time to mention about this so-called 3 unidirectional bars from the self-correlation. Okay, so our key discovery is on the boundary phase of conductivity, we found this kind of a pattern, which has a 4A by 4A within each plaquette. We have the 3 unidirectional density bars. And on these bars, we see this density state and a small gap, which mimics that of superconductivity. We think that it is coming either from the consequence of the pair density wave or the local pairing, the precursor pairing. Okay, so this is the first piece of work. This is about why it is a pneumatic within the block. We can find several literatures. Here I mentioned first one to you. So the Emery in the early days says that the holes may be doped to the oxygen state, and the pairing is mediated by strong local pair, strong coupling to the local spin configuration. And our data somehow is quite consistent with this one. But of course, there are other theoretical papers to show that in the underdoped side, it is easy to form this kind of a pneumatic state. Okay. So then I come to the second piece of work. So second piece of work is optimal doped BISCO 2212 with ion doping. Using ion doping, 3% ion doping, we suppress the TC to about 65K. Here shows the resistivity. And by using the magnetization data, using the Curie-Weiss fitting, we found that the ion yields a magnetic property. And because the tunneling on the ion purity, it shows this kind of tunneling spectrum. So we can use a high energy tunneling spectrum to find the ion spots here. And on the ion spots, we see that the gapped feature on the tunneling spectrum is still there. But far away, then you can see that it become a normal superconducting curve, okay? So this is on the ion impurity doped BISCO 2212. And here shows the contrast for the tunneling spectrum measured far away from the ion impurity, which shows a typical D-wave superconducting tunneling spectrum. But on the ion, you can see that the coherence peak is strongly suppressed, with the gap, however, intact, which again shows a strong local pairing. Okay, so here I also compare to nickel and the zinc doping. The ion doping somehow only suppress the phase coherence, the coherence peak, but does not change the gap too much. Okay, and before going to the spin polarized data on this sample, here I show you that actually on this BISCO 2212 optimally doped sample, we know that it has such a kind of Fermi surface. We have a 7 scattering spot, okay, and according to the D-wave gap, then we have the 3 scattering with the same side of the gap, 4 scattering with the opposite sign. Then we use so-called phase referenced quasi-particle interference technique. This is a new technique. Then you can clearly show that which one is the scattering between the same side and which one is opposite side. Okay, we found that 3 are having the same sign and 4 have the opposite side. So this is a new technique to show the evidence of D-wave pairing in the cuprate. And this new method avoids the challenge of fabrication the Jefferson device and the measurement, which is very difficult normally for checking the pairing symmetry. Okay, so this is another story. Let me come back to the ion doped BISCO 2212. So you can see that this is using tungsten measured mapping tensor state. You can see this kind of block again. And we do the Fourier transform, we see a set of spots. One is a 4A by 4A. Another one is a 3/4 here, again, on this, even for this sample, okay? This is 2 typical scattering spots. However, if we use a tunneling spectrum, spin polarized tip, for spin up and spin down, then we subtract these 2 topography, then you will see that nearby this ion impurity, you see clearly this anti-Fermi order. This is the blue and the red shows anti-Fermi order. This is a Fourier transform. After subtraction, you can clearly see these spots, which is corresponding to this anti-Fermi order, but it's incommensurate static anti-Fermi order. It is a little bit less than this V vector of the anti-Fermi order in the parent phase, okay, which is about 0.85. For the parent phase, the anti-Fermi order is 1 here, okay. So our theoretical collaborators, Professor Ilya Ermin, did the calculation. They assumed the on-site Hubbard U for the repulsive for magnetic state, and the nearest neighbor for the attraction for D-wave superconductivity and a single point like magnetic impurity. They did a calculation shows this kind of spin polarized contrast pattern, and which you can compare to our experiment. It looks very similar, okay? And also this intensity oscillation, this dispersion also. So it seems that the anti-Fermi order and the anti-ferromagnetism and the superconductivity, they are very strongly, they are closely interplayed each other, okay? Then I come to the third piece of work, which I will show you the normal state of the BISCO 2201, which has a Plancke dissipation, and we found that the upward field is a long Ginsburg Landau type. Okay, we all know that in cuprate there were very strange behavior for the so-called BISCO 2201 without the lanthanum doped one. In early time, in 1990, this is a canonic curve, okay? So the near resistivity goes from TC about 7 Kelvin to 700 Kelvin. So that violates so-called phonon scattering. And based on that data, several theorists, especially Jan proposed so-called novel dissipation governed by the many body effect in these correlation systems. So in the entangled compressible quantum metal, and it shows the scattering rate should be linearly versus temperature with this kind of quantum number. Okay, the alpha is close to 1, and this phenomenon has been found in many cuprate, and iron-based heavy forming resonates. Okay, and also in this paper, these people collected a lot of transport data and to prove that indeed the alpha is quite close to 1. So that indeed shows such a behavior. And we want to measure more precisely. So we fabricate our single crystal into this bridge, and with a very well-defined size and thickness. Then, and for this sample, it's good that because the TC is quite low, so we can use even the lab magnetic field can suppress superconductivity completely. So this is near optimal doping, and this is the resistivity shows quite close linear behavior. This for this physical to the 0 single crystal. By using a 15 Tesla data, the superconductivity is almost suppressed completely. Okay, above the temperature of 400 millikelvin. So this is a transition. Then we try to use the Drude model to estimate the scattering rate. But here we have two unknown parameters. One is the effective mass, another one is the so-called charge carrier density, N. So we use the Hall effect measurement to get the Hall number, and from the Hall resistivity, we determine this charge carrier density, and also from specific heat, we can determine so-called effective mass. Okay. We found that the Hall coefficient actually changes slightly with temperature. So we take the average to calculate the charge carrier density, which is gives this value. And also from this specific coefficient, we determine this effective mass. Okay. And finally, we get a mass in this value is about 7.33 times of the Bell mass of the electron. And then we use this formula to fit to the resistivity data down to low temperature. We found that the contribution is mainly contributed by a linear term. So here we separate, after the fitting, we use the parameters to calculate the data. So the blue one gives by this quadratic term, and the black one gives by the linear term. So the linear term dominate here, okay? So from the linear term, from the mass and from the charge carrier density, we can definitely determine the alpha. We find it's very close to 1, you can see, okay? And actually some groups say that in the Mercury 1201, they found that if you calculate the so-called Hall angle, which does not depend on the charge carrier density, okay? So in that case, they found that it becomes a linear, so-called fermi-liquid like quadratic. And we follow the same way in our sample. We found that even we just calculate this 1/12 by timing this charge carrier density, the temperature dependent, we don't see a linear, we don't see this quadratic temperature dependence. Instead, we see this so-called still rather linear in low temperature region, okay, for this dissipation. So our sample seems different from the Mercury one. And also we determine the upgraded field by using the Euro weight. So from the transport, 95% of the normal state, we determine the upgraded field. You can see the data here, which is definitely deviating from the Ginzburg-Landau prediction. The difficulty for this Ginzburg-Landau predicted upgraded field is that you always have a bending down in the low temperature region. But the cuprate sample shows this kind of divergence. Actually, this behavior has been found in many other systems, such as in Thulium-201 and YBCO by different groups. Then we notice one paper by Alexandrov et al. Says that for the critical field of uncondensed bosons, which means that this is not real upgraded field, it is for the condensation temperature and field. It gives some kind of theory, and following the theory, we put forward this kind of empirical relation for the upgraded field. So this 1/1 minus T is given by the dropping down of temperature of superfluid density with temperature, and it gives the T power law in here. So here we assume a small delta here. So we propose this kind of empirical law. We found that the data can be very nicely fitting by this empirical law. So which suggests that we have uncondensed bosons, okay? Here are Cooper pairs, even above the ubiquity field. This boundary just reflect the condensation temperature of field for the electron systems, okay? Actually, in the cuprate, we have been told many times by the so-called local pairing gap and also superfluid density determines the so-called TC DOM. This is given by Emery and Kieferson. And also in the APES data by Donglai Feng et al. They show this kind of coherence peak follows this kind of curve, okay, shows the TC correlation. And also this kind of a cartoon picture says that in the cuprate, we probably have a local strong pairing with a BEC, and when the Cooper pairs the density becomes higher and higher. In that case, we are crossing over to the BCS crossover region. So in that case, I plot this kind of cartoon picture. So in the BCS case, we have the Fermi surface instability due to the weak coupling, like a phonon, exchange phonon. And in the cuprate, probably, as I showed by three set of data, three piece of experiment, that we have a local strong pair due to the correlation, and also the TC is determined by the phase coherence, okay? So here I draw a general camp for superconductivity. So in this big camp, the BCS just sit in the corner, which is due to the so-called weak coupling picture instability of Fermi surface. However, in the cuprate, we have a local pair due to the strong correlation. And in that case, we have some kind of finite density state, and gradually we have superconductivity. So the TC is determined by the superfluid density. And then probably the ion-based superconductors is in between this, in this region, corresponding to the BCS to BEC crossover. Okay, so this is my final picture to conclude our data. So then let me come to the conclusion. The first is that is in the underdoped, very underdoped region, we use a spin polarized STM to first time to review that this charge transfer gap will be filled up by density of state in a wide range of energy when the anti-Fermi order is diminished. And the anti-Fermi order is for the first time viewed by the spin polarized STM directly. And at a higher doping, the charge transfer gap is completely filled by DOS. And with a hump in this region, this corresponding to the J value, okay, in the same scale. And meanwhile, some 4A by 4A plaquettes of density state are formed. Within each plaquette, an internal pneumatic state is observed with the peaks of density state at the low energies, okay? And the highest density state peaks appear on the oxygen side, implying that the holes are doped into the oxygen orbitals. And as counting the density, it is tempting to conclude that it seems 2 holes per plaquette. We argue that the local Cooper pairing may exhibit as a confined pneumatic state with a 4A by 4A plaquette. The low energy gap arises either from a pale density wave or the precursor gap for superconductivity. And also, we found the ion-doped BISCO 2212, we found a re-emergent anti-Fermi order with this shorter wave vector, okay, which is incommensurate. And also with the linear transfer data, we found the Plancking dissipation. And also we found ubiquity field, which is not the Ginsburg-Landau type, but it shows uncondensed Cooper pairs above TC. So this again shows, all this data shows that we have strong pairing with variable phase coherence. So this is generally consistent with the picture of superconductivity arising from a doped Mott insulator. So with that, I thank you very much for your attention.
Thank you, Professor Van. Any
Thank
questions from the audience?
Yes.
Yes, please.
Thank you for that very nice talk. I have a question about what you showed with the local antiferromagnetism in impurity doped BISCO. So around some of the impurities, you found the local antiferromagnetism, and then you took a Fourier transform of it. If you could put that slide back
Yes.
up, I had had a question
Yes,
about the Fourier
yes,
transform.
yes. I try to move to that. Yeah, sorry. So you mean the second part as ion impurity, huh?
That's right.
Yes. Wait a minute. The web has. Wait a minute. Sorry, I come to the second part. Yes. Yes. What's your question, please?
So let's see. There's a slide where you show the Fourier transform of that
Yes.
local you see the local antiferromagnetism, and then you show a Fourier transform of it.
Yes.
Here it
This
is.
one,
This
yes.
slide. This slide right here. So
Yeah.
in the lower left, you're seeing.
Yes.
It looks like you're seeing some arcs rather than just peaks. But in the lower left, you see what looks like some arcs. Is that real, or is that just sort of a trick if I'm sitting too far back from the screen?
No, I don't think this is real. So this is you know, it's a Fourier transform of this single spin up mapping topography. Okay, so this is I think it's due to Fourier transform effect. So it's not, so you can see this spot here. Okay, which looks like using a tungsten. And actually, actually, the one quarter one does not show up strongly, but here there was spot. And you mean this arc, huh?
Yeah, I mean
this
that
one,
arc.
huh?
I was curious if
No,
you think that's real or
that's
an
not
artifact.
that's not a true effect. I think it's due to the Fourier transform on this picture induced for some reason. Yeah.
Okay, thank you.
Mm-hmm. Thank you.
Any other questions?
Yeah, maybe a comment and a question. First of all, congratulations for these very nice spin-polarized STM measurements on the static and the ferromagnetic ordering. Now, the question is, do you think that there's a chance also to reveal maybe antiferromagnetic spin fluctuations which might survive even at a level where you do not see the static antiferromagnetic order anymore? So there are new techniques, of course, available combining spin-polarized STM with dynamic processes. So did you think a little bit in this direction?
Well, that's a good question and proposer, but I must say that I don't have idea how to realize that. You know, spin fluctuation could be very fast. Okay, so our STM measurement is quasi-static. So in that case, probably some short time, time reserved STM can do such thing. I hope so. But for us, for our technique so far, we cannot do that. Okay. That's a very good suggestion. But we are now, next step, we are trying to using a magnetic field to suppress the superconductivity, then to see whether this magnetic order, static order, or some kind of order will appear again. Yeah, that's is underway. But for the quick fluctuating antiferromagnetism, I don't have the idea so far. Probably some quick measurement, time reserved STM can do. Thank you. Yeah.
Time resolved as SPSTM or ESR as PSTM might be valuable tools to look at the.
Yes. That's a good point indeed. Yeah, we need some new technique on the tip. In that case, we can reserve the short time. So that will be very interesting. Yeah. Thank you for the suggestion.
Yes, please.
Thank you very much for the very nice presentation, Professor Heichman.
Yes, thank you. Thank you, Professor Genser.
As an organizer, I cannot commit myself to listen to talk, so I may have missed something that you already mentioned, maybe. So
yes,
I'm just going to ask about this iron-based superconductors, thin films.
Yes. Yes.
Is it possible to make reproducible reproducible monolayers for quantum applications for the iron-based superconductors. I mean, do you have a plan to make this in your laboratory, or is it?
Oh, actually, in China, I think several groups can reproduce this monolayer thin film. Yes, in Tsinghua University and also in other university, now they can produce, like Shanghai Jiao Tong University can produce this monolayer ion selenium film, and the quality looks quite nice. And yes, that's possible. But in my group, we have not tried that direction yet. Yeah, certainly in ion selenium thin film, people try to find the Majorana mode on the vortex core, but it seems on the intercalated ion selenium film, people find such zero mode, but in ion selenium monolayer film, it does not exist. So it could be interesting. Yes, some groups in China, they are growing and reproduce the monolayer thin film. But with magnetization TC, it's about 40 to 50 Kelvin, something like that. Magnetization, yeah, measurement.
I think China is making heavily investment in the field of superconductivity, and this is one of the highlights of the conference. So maybe you can give us some more details if this is available with you.
Oh, if you have time, I can say a few words about that. Yes, indeed, in China we have quite how to say some investment on either fundamental research and also for the application. For the fundamental research, we have the national project from the Ministry of Science and Technology. We have several, I think maybe less than 10, but something close to 10. Something like how much is 30 million yuan, something like that project. And also in the Chinese Academy of Science, we have a much bigger project. For the goal is to fabricate the high temperature superconducting magnet, okay, to use under 20 Tesla for the nuclear physics. I mean for the fusion tokamak, and also for the high energy physics for the accelerator. Okay, so that's the big project is running now. So we have either fundamental and application. We have some project, but money is always not enough. So it's I can say it's in a good state. Yes.
What about the big complex in Hefei about quantum technologies research in general, not only superconductivity, maybe?
Oh, that's certainly a big project. That's for the quantum informatics and also quantum computing. Actually, they are also doing the superconducting quantum calculation. So it's a big complex. Not only Hefei. I mean Hefei certainly Professor Pan's group and team is big, and also it's spanning in whole China. I think it's helping China to explore towards that direction for the quantum informatics and also quantum computing. Both are going parallelly. Yeah. Yes, it's going. Yeah.
Okay, thank you.
Yeah.
We thank the
Okay,
speaker.
thank you so much. Yeah.
Thank you.
So shall I stop share? Yes.
You can stay connected on internet, and Professor Latore from Singapore will be talking about quantum computing. Maybe
yes, I will. I will stay here to hear. Yeah, thank you. Yeah.
So please stay connected and listen to Professor Latore from Singapore.
Sure.
Okay.
Sure. Sure.
Okay. Thank you very much.
I would love.
We are very pleased.
Thank you, Professor Genser, again.
Okay.
Yeah.
Okay. Cheers.
Our next speaker is from Singapore Center for Quantum Technologies, Jose Latorre. He will talk about quantum computing is coming. It's a very exciting talk, I think.
Thank you.
Thank you.
Well, thank you very much, and I'd like to start by thanking Ali, of course, and Sherman for the invitation coming here. And there are two reasons I want to mention in the very beginning. The first is that when Sherman talked to me, I told him immediately, well, I think that part of the future of quantum computing is in the material science. There's no question for many of us. So this is an excellent opportunity for me to meet some of the people that are in the field. And the second is that he was very obvious. It was obvious that I could say anything. He said, okay, if you can review a little bit what's going on, no need to be politically correct. Wow, that's a pleasure, no? As director of CQT, I always have to be careful, so today, no. I'm also directing the center, the new center in Abu Dhabi, the TII. There is a Quantum Research Center, which only has 2 years, but in 2 years we already have a small quantum computer. So the barrier to make a quantum computer is not that high. Okay? And finally, I produce a startup in Barcelona, where we are also working superconducting qubits. So does it work? Oh, down. The first comment I want to do is that quantum computing is coming, indeed, no question about that, but it's not coming at the pace of the hype in the media. It's coming definitely at the pace of science. And that requires a lot of patience to deal with the media, and in particular with people that provide the money, okay? There is a misconception that we can go very, very fast in quantum computing, and this is certainly not true. What I will be doing today is to talk a little bit about the landscape of quantum computing, figures of merit, how a quantum computer is good or not, and then go back to a little bit of theory, talking about the Hilbert space, these ideas that now we have about tensor networks, variational quantum algorithms, and the new focus on sustainable computing. So the landscape, just in one transparency, things which are going on. Well, there are like 3 main ideas. One is universal quantum computation, the other is quantum simulators, and the third one is quantum annealers. Let me make it very clear. The first, you want to do any computation. You want to do Shor's algorithm and break cybersecurity. That's a quantum computer, a universal quantum computer. And ideas, we have qubits based on transmons, which are superconducting currents in ions, in solid state, spins in NV centers, in cavity, in photons. At CQT, we have actually the 6 platforms, so we work with all of them. Quantum simulators is something different. You don't have universal gates, but you have enough control of matter to simulate other quantum systems. And now, in particular, in the last couple of years, there has been an enormous progress in cold neutral gases and also in integrated photonics. So there, the spirit, actually, one of them is to simulate condensed matter systems and also materials. And the third are quantum annealers. And they are both based on more simple qubits like transmons, also on the more a different set, which is flux qubits, even fluxonium. Okay? So on the first column, the companies are, there are a lot of companies working on that, and those are, you know very well, Google, IBM, Rigetti, IonQ, all of them. Let me just highlight a few of the recent news for you. IonQ just released now a 23 qubit machine where they have interaction all with all order of magnitude of the errors, 0.01% per gate, which is really remarkable. And with gates which are not two-body, they have many-body gates, okay? So that's the interactions of nature. let me mention IQM. IQM will be releasing the 25-qubit machine in January. This is in Finland. Quantware, they are doing something very special. Because it's so difficult to characterize a chip, they are fabricating chips and selling them without characterization. It's up to you if you believe this will be a good chip or not. So at present, Quantware, they are selling 5 and 21 qubits, and they will be selling 64 qubits at prices which are really not that high, so that you can work with them. Let me mention, for instance, Colquanta is trying to sell Einstein machine, Albert machine, that in principle automatically will take you to nanokelvins. Okay, they have an emphasis in sensing too. Or Xanadu just released a photonic chip for boson sampling of more than 200 waveguides. And on the D-Wave, as you know, they have gone a little bit crazy to 5,000 qubits. And I will mention our initiative. So Kilimanjaro is leading an initiative in Europe to make a quantum annealer which is coherent. So the emphasis is coherence. So not like D-Wave, not the number of qubits, but coherence. To this, you have to add all the labs. There are many universities which are doing a fantastic job. But in particular, I want to mention HPC centers, so high-performance computing centers. You may have read the news that a month ago, the European Union, through the HPC initiatives, they issued, it is called HPC Quantum Computer and Simulation, CSC, Quantum Computer, QCS. They fund now 6 quantum computers in Europe, which are sitting at supercomputing centers. So the idea is that quantum computation is thought as coming to the places where supercomputation is. Okay. For why there are still so many platforms? Well, because there is no winner of what the best quantum computer platform is. And why there is a competition? Because there is a clash. Okay, it's an obvious clash, but many people don't see it. The clash is that on one hand, you need to protect your qubit against incoherence. You have to protect it. But if you protect it, then it's very difficult to interact. If you have a qubit that interacts easily, then it's very difficult to keep it coherent. Okay, so this is the clash. Who is good to maintain the coherence? A photon. Okay, but then, you know, QED tell us that photons interact with alpha over pi divided to the 4 power plus extra factors that makes negligible. So you need matter, and then you have to interact through matter, and then it's probabilistic sometimes. So it's extremely difficult to get something. Who is trying to do that? Psi-quantum. On the other hand, transpons can interact, but then they immediately, you get decoherence. Okay? And this is the fight that we are in the middle of. Ions are in between. Ions have the privilege. The qubits are there. Nature gives you qubits for free. You simply pick one, and that's a qubit. An ion is a qubit. You don't have to do anything. Now, you have to keep it there. So the new idea is that people have levitating ions on chips, and this is the way now we manipulate them. Okay? So we go from traps in 3D to levitating ions over a 2D chip. All this is going on, but from the point of view of business, the companies that are doing very well, extremely well, are those related to enabling technologies. So, as you know, I give you an example of Blue Force in cryogenics. Well, I cannot remember the exact number, but I think last year they sold 200 dilution fridges. So this is really spectacular. Fast electronics is moving very, very, very fast with all these, the old and the new companies. So you have the old, but you also have Q-blocks, quantum machines, And they are all trying to get fantastic control at the nanosecond scale of the electronics. Then you have cables, superconducting cables like Delft circuits and Blue Force also, quantum amplifiers, all the pieces which are needed, and even the control software is suffering a transformation. So you have companies like Orange Computing, Ketma, Horizon, Classic, all of them want to achieve a much better control of our physical devices through software. Okay? There is an ongoing big expansion of the use of FPGAs because it's needed. And many labs, little by little, they are working like integrators rather than developing the software. So the example is that now you can buy almost everything and try to put it together, including the chips. Okay? But it would be unfair to say that because quantum computing is coming, there isn't efforts on the classical world. So actually in the last couple of years, the progress of classical computing has been astonishing. The first idea is that people have been focusing on what is the best way to simulate states so that you can mimic a quantum computer. We have been working a lot on simulating quantum mechanics, but typically we did that with Monte Carlo or exact state simulations. The push now, enormous push, goes in the direction of tensor networks. And I will mention lately what is the central idea of a tensor network so that you see why classical computers are getting so good nowadays. There is this new idea of quantum-inspired algorithms. So those are classical algorithms, but the logic they follow is suggested by quantum mechanics. An example for that is the solution of linear systems, that there is a quantum algorithm called HHL. And what you do is now you program the quantum algorithm, you simulate it. It turns out to be an excellent idea to solve these kind of systems. And recently, as last week, people have discovered that tensor networks, if you can represent your data with a tensor network, the Fourier transform, the standard Fourier transform, is extremely efficient. So if you codify the data as a tensor network, the Fourier transform is fantastically fast. And you have an advantage over any classical Fourier transform. And people have even been building classical machines which are quantum inspired. And you have machines like NVIDIA with the quantum. So what is the idea? That given that the operations you do for quantum are related to the manipulation of tensors, they are optimizing the flow of data between the units of computation. Or Atos has created a machine, Fujitsu has created a machine. Fujitsu has created an annealer, is simulating the annealing process on the classical hardware. And the middleware, something that very few people mention. In order to have a quantum device and a high-level algorithm, you have to connect them. And this is what people call a full stack. Now, the full stack is non-trivial, and there are not that many. You have Qiskit, they are all proprietary in the sense that the language may be open source, but the hardcore, all the parts of these are proprietary. Circ, Gulax, Forest, Penny Lane. A common language, which is OpenQuasm, to talk to the computers in the very end. And you have to provide everything. You have to provide cloud access, you have to provide applications, you have to provide scheduler, you have to do the calibration, automatize, you have to do transpiler, you have to go to the native interactions of the system. Quite an effort to do all that. What we are doing, and this is what I'm trying to show over there, is there a pointer? The first one, okay. Uh-oh. Yeah, not very intense. What we are doing under the name of Kibo, it's an open source initiative that wants to be a sort of Linux for quantum devices. What we are doing now is backends of simulations. We have already multi-GPU, multi-node to go to supercomputers, tensor networks, and we deal with the lab, with transmons and ions. And now we are building the drivers to the machines so that actually Kibo at the top level, you can give instructions and they understand the equipment that you may have in your lab. A lot of the emphasis, as I said, is being pushed to FPGAs. So why we need FPGAs? Because typically FPGAs are used, for instance, for high-frequency trading in the stock market, because you need to get the news and take an action very fast. The limit nowadays is of the order of 60 nanoseconds to take an action in the market. In artificial intelligence, you use them because you want extreme power, adaptive extreme power. Ours is different because what we need is a control at the natural scales of the physics, which is nanoseconds. So actually, we have really to work on the nanosecond scale with our electronics. We cannot use electronics of microseconds. We have to go to nanoseconds. That's why FPGAs are now dominating the landscape. And finally, I should mention that there is a big issue about how they call now segmentation, no? Instead of globalization, segmentation. To give you examples, we have gone through clearance procedures to buy equipment from Europe, okay? We have suffered exportation bans both in Singapore and in Abu Dhabi. Pieces of equipment which are not sold. And definitely there is an issue of talent. Immediately as you educate somebody, puff, yeah, you lose him. In general, all countries are conscious of the idea that they have to develop their own strategy. And you may be familiar with many of the national plans that are going around. All of them are very similar. All of them talk about the three pillars: quantum computing and simulation, quantum communication and cybersecurity, quantum sensing and metrology. And now many more people talk about enabling technologies and obviously basic science. Because without basic science, it will miss the big progress which is coming. Given that all this is similar for every country, you see that what makes the difference really is the speed. So what we are seeing everywhere is that those countries with a lot of bureaucracy are lagging behind, literally. Okay, literally lagging behind. European Union flagship is lagging behind. Why? Because it's an amazing amount of bureaucracy. You see actually the opposite, that the startups are doing well because they have less bureaucracy. I'm the direct witness of different countries because in the European Union, I'm involved in 3 places, and by far the progress is related to the lack of bureaucracy. Okay? Of course, of funding. You need funding, but you need agility. Okay? Okay, this was a little bit of just to say what's going on in the planet. Okay? And what I would like to do now is just to go back to, little by little, to theory, to tell you a few of the things which are going on, okay? It's my personal choice. It's not that this is the most relevant thing going on. So I will, I forgot. I would like to mention just that the figures of merit that people are using is a mess. We all agree that this has to be cleared. So when you go to marketing, news. Actually, I said here the figure of merit is the number of qubits. Any announcement says that many qubits. Well, the figure of merit is money. The first thing they say is how much money. Okay, they got. But the number of qubits is typically used as a figure of merit. Then, if the communication has a more solid background, they start to explain that there is a coherence, and they talk about coherence time. And they talk also about get fidelity. But as a matter of fact, you never see news that tell you about the depth that you can support in your chips, the fidelity of the circuit, not of the gates, or the expressibility you have, or the entanglement support, or many other names that we are using constantly in science that never make it into the news. Just to give an example, I know it's an obvious thing, but let me do it. If the number of qubits is everything, well, you know, and there are claims now, as you may know, of quantum computers with more than 100 qubits. Well, then you can factor. And Shor's algorithm only needs 2n plus 3 qubits. So you can factor if you have such a computer. And with this number of qubits, you should be able to factor a number of this size. As of last year, the largest number we have factored is 21. So what's the meaning of the figure of merit of number of qubits? Is really irrelevant, okay? And I mentioned a few problems, depth, circuit fidelity. Let me give you an example. I go to depth. This is a state, quantum state, which is called absolute maximally entangled. It's a state that has a peculiar thing, that whatever partition you make, you have maximal entropy. And you can make a circuit for it. Okay, so we have a quantum computer. Let's check it. Let's do it. And you do it, and when you look at the detail, when you put it in a real quantum computer, this is a real example, okay? This is one of the quantum computers of IBM. Well, that circuit is implemented like this. And then on top, this has to be translated to the native gates of the circuit. So you see, when you count the depth, which is how many things you can do in parallel, so here you have formally 1, 2, 3, 4, 5, 6 of depth. As a matter of fact, it's 17. And as a matter of real fact, when you do the native gates, is even worse, okay? So how much depth you can get? Well, it's related to your T2 versus the gate time. And in some cases, you go to up to 200 nanoseconds, and you have T2s of microseconds. So formally, you think you can do 1,000. In practice, it's less. So actually, we are dealing nowadays with depths of 20 to 30, no more than that. And with that, we can do very, very, very little. Okay? That's the reason why practically we don't have any good result. But to solve that, you have to go to the real physics. You have to understand why this is the limitation. This is an example of the circuit fidelity. Again, I propose a challenge. You tell me, I have a quantum computer. I said, I don't believe you. I don't believe you. So give me access, and remotely, what I do is that I run Bell inequalities in your computer. I see if this is a quantum computer. So the generalization of Bell inequalities are Bell inequalities for multipartite systems. So this is an example of the 3 Mermin inequality, 4 and 5. And you can run them. And this is the result. Huh? You have 2 local realism, 4 and 4 for 3, 4, and 5 qubits. The limit in quantum mechanics, if the state is perfect, would be 4, 8 to the square root of 2 or 16. And when you do the experiment, the numbers you get are those. Okay. So as you can see, for 2 and 3 qubits, you do violate Bell inequalities. For 4, it gets tough. For 5, essentially, you are not violating Bell inequalities. So although these circuits only have depth 10, and all the gates have a 99.99% of supposedly fidelity, the circuit fidelity is dramatically low. So there is something in between claiming a gate fidelity and claiming a circuit fidelity, okay? Which has to do with the crosstalk of the qubits, how they interfere one with the other. So how you can protect them. All these examples are done with superconducting qubits, okay? All of them. Would you get better numbers with ions? Yes, ions come out better. So you have a better result if you work with ion traps. Now, in order to do real progress, the community is starting to understand a number of things. That, sorry, this is you, no? Not me. The community is understanding that on top of defining our secrets through a process of characterization and calibration, when we go out to the public or to other colleagues, we have to do a severe benchmarking, which is not existing nowadays. There is no accepted way of doing the benchmarking of a chip. There is a thing which is randomized benchmarking that we are doing nowadays, but this is not enough to define it. It only gives you averages of the quality of your gates. We need to go deeper into how you define the quality of a chip. And finally, we also need validation and certification. Okay? So we need eventually to certify a chip, which is not there. On the other hand, nobody is mentioning that, but for quantum computing being meaningful, you need cloud access, and that implies a lot of cybersecurity, okay, with it, because if finally your quantum computer is attacked by whoever, then it's useless. So we need a lot of work on the cloud access. A lot has been done, by the way. We need federated computing. Those are ideas which are very nice. Blind computing, for instance, is a beautiful idea. It's a classical idea that has a counterpart in quantum computers, which is, I want to do a quantum computation. You have a quantum computer, but I don't want you to know what you are computing for me. So can I disguise my problem in a way that you execute it in your quantum computer, I get the result, and I solve my problem, but you don't know what you solved? And the answer is yes, there is a way to do that. This is blind computing, okay? Are there schemes? We have schemes, but that will have to be put in place in the future. And definitely quantum internet. As you know, there are efforts around. There is an initiative in Europe to have progress in quantum internet, which depends on physics. Again, quantum repeaters is a problem of physics. So all these things are showing that at some point you may see a separation between the people that produce quantum computers and the people that benchmark, certify them. And we are starting to do this step. So in TII, we are building the characterization facility, and as of the end of this year, we will be characterizing chips from 5 different vendors. Let me move little by little to more theoretical aspects. Everybody says, well, quantum computers are good because you have a huge Hilbert space. Well, indeed, the official standard argument is that in n qubits, you can store 2 times 2 to the n minus 2 real numbers. And this is certainly true. I mean, the characterization of a cat needs this amount of numbers. So vice versa. If I manage to put all these numbers in a state, I'm doing an amazing compression. Okay? I only have n elements, n physical elements. I have 2 to the n real numbers. The numbers go that 53 qubits, which is, as you know, where people claim that there is quantum advantage, is a petabyte. 1,000 qubits is 10 to the 282 exabytes. So it's ridiculous. But nobody says, oh, and indeed it is certainly true that if you manage that, any processing is done in parallel. So if you have a superposition, it's done in parallel. That's quantum mechanics. What people don't say is that there is an issue about upload of this information. How do you upload all this data into quantum state? How do you read out? It's probabilistic, the readout. So that means that it is not true that a quantum computer will accelerate any computation. It's by far not true, okay? In particular, it may be helpful if the way you encode problems is very compact and the solution to a problem is very compact. In the middle, you may use the Hilbert space, but the upload and retrieval of information should be very compact. That's exactly what happens with Shor's algorithm. You give only n bits, you end up reading the period, n bits. In the middle, you develop a lot of entanglement, but you only need to upload and to retrieve a logarithmic number, okay, of bits. This is not true when people think that you may deal with, you know, the clients of a bank on the millions, because then you need classically to upload all this information. So there is an issue of uploading information. I'm not saying that there are no other ways. I will give you an example which is very peculiar. Can I upload very fast a picture in a quantum computer? Well, formally, Seth Lloyd produced this example. Said, okay, my picture is in a CD, which are mirrors. So I simply say light, it bounces back, carries the information of the picture, and I capture with in guides. So I've uploaded in one go a lot of information. So there is no obstruction. But as a matter of fact, we have never been able to upload a large amount of information in one go so far. Okay? So this is one of the big issues. Now, let me refine a little bit what I said about classical improvements in the last years. And this is a very nice one. So of course, you can simulate quantum mechanics in an exact way. You simply write the ket, and that's it. This is limited to around 50 qubits. Okay? There was an effort for this competition that Google made in 2019, and you may know that it was done in Jülich, and they got up to 50 qubits with 3 months of computation or something like that. Limit is 50 qubits, okay, 52, 54, no more than that. Exact, okay, exact simulation. You can do Monte Carlo, but as you know, Monte Carlo suffers the problem of the sign problem. You cannot attack problems where you have frustration, genuine frustration. If you analyze critical systems in condensed matter, you find the critical slowing down of all these, the correlation between the configurations. You have to kill that. And they're very difficult to analyze problems which are not just an average. So time evolution, very difficult. Tensor networks came up as a solution to all these problems, has no sign problem. It adapts to entanglement. It adapts to the geometry of the physical system and hence the many names of matrix state, projected entangled pairs of multi-scale renormalization ansatz, which are common names for these tensor networks. There are very nice libraries being developed. It has fantastic applications for finance and for chemistry that have been proven, and definitely have subtleties, like I mentioned before, the synergy with the quantum, with the Fourier transform. I'm using quantum, but it's a classical Fourier transform. So what is the idea in one go, just for you to know what's going on? Well, if you are strict that you want an exact representation of a ket, you have to deliver all these 2 to the n complex numbers. The idea of a tensor network is very, very deep. Can you represent this tensor as a product of tensors? If so, it turns out that each of these tensors has a dimension, is a matrix, has a dimension chi. So the counting of degrees of freedom is 2 to the n here versus n times, because there are n matrix, 2 to the chi square, which are the coefficients, and the qubit, the physical index is 2. So formally, you reduce any ket to this amount of degrees of freedom. So if I want a better representation, I simply need to increase this chi. This goes increasing, and I have a much better representation of the state. So it's adaptative. This chi can be proven to relate to the entanglement of the system. If it is a product state, chi is 1. If you have maximal entanglement, chi is 2 to the n halves. If you want to manage in an efficient way, you can handle up to polynomial number of n for chi. This has been used now very extensively. There is, if you check the literature, there's an explosion of people working on this, because you can try to revisit the simulations of condensed matter, and you can now really revisit even quantum computation. The pictures that you will see if you go to talks by these people are all how they set up the tensor network that describe your system. So really you have to go to your system, see if you have a honeycomb lattice, if you have a square lattice, if you have whatever, and you adapt your tensor network, and then you go through that. And just to give you an example, I think it's a funny way. Take a picture. Let me show you how I can handle a classical problem with a tensor network. I take a picture, divide in quadrants. Each quadrant is a quadrit, 1, 2, 3, 4. The first quadrant I divide in 4 quadrants, and so on. So my I index is labeling the address of the quadrant, and finally C is the level of gray. So actually this is a very simple way of seeing that 4 to the n numbers can be put in a ket of n quadrit. So you see this amazing compression. And next, what you can do, for instance, is to take C and represent as a product, as a tensor network. And as you increase chi, you have a much better representation. If you go lower chi, you're having a approximation to the picture. And you can see this is absolutely competitive against JPEG, for instance. Okay. But what's going really on nowadays, it's an effort called variational quantum algorithms. And it's really an interesting idea. So what is a quantum secret? A quantum secret is nothing else but a global unitary. So it's something that will take you from one point in the Hilbert space to another point in the Hilbert space. What you hope is that this this quantum secret will take you very near where you find the solution to your problem. But this is it. A quantum secret is a combination of gates. So how do we find a quantum secret that solves my problem? Well, there is a solution, hopefully. And this is, call it V. V is the one unitary that would solve your problem. And the question is, can I do it with a secret? And if I can, how many gates I need? And this is a wonderful theorem by Solovay and Kitaev that says that the increase in the number of elements in your secret is very moderate. So this is an existent theorem. It is not a construction theorem. It's not telling you which is the secret that solves your problem. It is telling you that at the most fundamental level, you can prove that there is a quantum secret that solves the problem for you quite efficiently. So there is hope. Huh? We have some mathematical steps that tell us that there is such a thing as a secret that solves the problem. Well, I think it's a very profound theorem. Actually, the proof of this theorem is so highly non-trivial in that it's never taught in any course. Okay? It's very, very difficult. So, hence the idea, okay, there is such a secret, but I don't know how to construct it. So I will do the following, and this was the idea by all these people from IBM. Let's make a secret which is random. Random. But with parameters that I can adjust. For instance, if there is a rotation, the rotation of a qubit is adjustable. And I play with that. Can I do a cycle where I start with a random secret, I read whatever I want the solution, doesn't work, and I feed back machine learning, and I change the secret. And I keep working in a cycle. So I applied machine learning to defining the secret. And they did that, and this was the first time that molecules were attacked, the first paper on quantum chemistry done by the IBM group a few years ago, and they attacked all these molecules. Okay, was the first time that with a quantum device, people got a number for these things. This can be now understood much better, and to do that, let me take a trivial example. I want to do a quantum circuit which is only 1 qubit, and my gates are here, and I want to classify data that I put here as X. Can I classify by training these alphas? And indeed, you can see that depending on the number of these guys, I classify anything. So we see that we can build quantum classifiers, we can build any circuit that does the task that you want. Why this is possible, let me just mention, and this is an experiment to do that, because what you can see is that in this structure, what you are doing is playing with these alphas variationally, and when you expand all that, you see this is a Fourier expansion. So actually, all these gates, when you concatenate them, what you see is that your parameters are just defining coefficients of Fourier expansion. And this is the fundamental theorem, no? That Fourier expansions reproduce any functionality point to point, okay? And this is an experiment that shows that 1 qubit is a universal approximant. So to be very, very, very precise, 1 qubit plus real loading of k gates is as powerful as a neural network with an intermediate layer of k neurons. And both are equivalent to Fourier expansion. And this is what we call expressibility. Your circuit has this expressibility. But for condensed matter, things require more qubits. And nobody knows really what is the optimal way of doing that, how to encode the data, how to process, how to read out. The common and standard procedure is to make quantum circuits that are ordered by layers in this way. Every qubit can be transformed. There are interactions between the qubits, and you make layers. And as you increase the number of layers, you increase the precision. And this is the solution to this problem. In particular, this is a simulation of the Ising model, how to find the ground state. Here is the depth of the circuit in vertical. Horizontal is the precision. In log 1 over epsilon, epsilon being the error, so 10 to the 10 precision, 1 part in 10 to the 10 precision here. And indeed, as you increase the number of layers, you get a better simulation of your quantum system with a variational quantum eigensolver. So this is the idea. We are now doing the first efforts to go to 2 dimensions. So of course, people are starting to work with condensed matter standard systems. Hubble model is waiting for us in the future, okay? So we are preparing the circuits for the 25 qubit machine, and we will try to use variational quantum eigensolvers to attack condensed matter systems of 2 dimensions, which is, that's one of the spirits of the quantum computers. I think, I don't know what time I should finish. Say that again? I can go? Oh, okay. No, I only have one more item. Either I take it out or not. I just wanted to add one item that may sound so strange to everybody. Everybody says quantum computers are faster than the classical computers. They can attack problems that nobody can attack and so on. Well, I think there is an issue which is overlooked by everybody. Quantum computers may not be faster than classical computers, but they may be energetically more efficient. So I will give a number. The supercomputing, our supercomputer in Barcelona spends 1.5 million euros in electricity. This is my Nostrum 4. My Nostrum 5 will spend a total of 100 millions in maintenance for 4 years. 100 million, maintaining the classical computer. And the reason is electricity, okay? Chilling the machine and computing. So far, 1/3 chilling, 2/3 computing. well, why not thinking whether quantum may be a solution to energy? Okay, that's the idea. And it's a very naive idea, but I will use an example. And this is an example that makes sense because you may know that the energy on the planet, humans use less than half. The other half is used for computing services, not for heat or for transportation. So computing is taking an enormous amount of energy in the planet. One of the many things which are being done systematically, besides Bitcoins, okay, that take a large percentage, is this thing, is checking the risk of portfolios. And as you know, every bank has a place where they spend hours and hours there computing for every client the risk. It's a very repetitive computation that has to be done systematically because the market is changing, okay? Simplification of the kind of things that you do is option pricing. So the idea is that S is the value of a stock, and you have it as time t, and you want to know at time much larger, capital T, maturity time, and I want to predict what is my expectation of making money. So if the value at the maturity time is bigger than a threshold, I call it strike, I will make money. If not, I lose it. So I have to compute this thing, the probability of that the value is ST times ST, and that will be my profit, okay? If not, I'm losing. I take the average. So what people do is that they simulate the evolution of this stock with a Black-Scholes equation, no? They think that there is an interest rate that will force an increase, but there is a stochastic variable and a volatility associated to that. And then that's it. Because there is a stochastic element here, what people do is a Monte Carlo. So they make trajectories towards the future, and these trajectories spread little by little, related to the volatility, and you end up here, and now you have to collect those that are on top of a value and discard the others, and that would be the way you compute your return. So this is a more realistic thing, 10,000 paths, and how people compute this. That takes a lot of effort. You don't have an asset, you have many assets, and they are correlated. So the evolution is not that simple, it's a correlated evolution. So what about making that, like that, making a photon that enters waveguides and can jump just like this, and finally you get the probability distribution. And then I collect the light. So does it make sense? Can I make a circuit where I do amplitude distribution, compute the expected payoff, and even if it is quantum, I can do amplitude amplification. Grover's algorithm apply here. And indeed, you can do the gates to generate the amplitude. You can compute everything. And you can design now a chip. And here are the pieces. They are going down and down till you make them very precise. And we did it. Okay, so at NTU, part of CQT and our team did the chip that computed this thing. A single photon enters. Those are the generator of single photons. It's probabilistic, so you try to get one photon at a time. Those is the module that computes everything, and you have single photon detectors in the very end. And as you see, foundries are part of our teams, okay? And this is the match between the expected probabilities and the real ones, and as you see, well, of course, physics obeys the laws that they have to obey. So it fits exactly what we wanted. The error goes to 0, and everything is good. And you can even say, okay, now you have the differential equation, but if not, you can train any probability distribution by the technique of generative adversarial networks. So you make two elements, one generates probabilities, the other discriminates. That's how you recognize faces, how you generate content nowadays. It's a standard technique. And we did that. So we trained the circuit. This chip is trainable, okay, against the neural network that was discriminating. And it works. And the results are as you expect, the real distribution versus the one. So we have a chip that learns any probability distribution. It bypasses Monte Carlo. And then it computes at the speed of light. And there is no need that this is done with single photons. It can be done with light. So there is an effort in Singapore to take these kind of ideas a step further, which is think of the problem you want to solve and adapt what we know, the elements we have from quantum mechanics, to find a solution which is energetically better. Not faster, energetically better. Okay? So we are building two plants, actually. One plant putting together everybody, and then a particular action separate, and we're involving the foundries and all the teams to see if we can do these kind of things. I think this is the future. A piece of the future of integrated photonics. I'm not saying this is the future for everything, but keep in mind, quantum advantage may be quantum advantage in energy, not in speed. Okay? Challenges. Well, look, this is my last transparency. I've fought with many of my colleagues that say that quantum computing is a matter of engineering. I disagree completely, okay? I disagree. I think it's a matter of physics. Since the last, I don't know for how many years, there has been no dramatic improvement of the coherence time in our devices. In none of the, not in ions, not in superconducting currents. So the depth of the circuits are exactly as they were, okay? Now, if the depth is what it is, imagine you want to do a variational quantum eigensolver. In order to entangle pieces, qubits in your chip, you need layers. If you don't have depth, you cannot even entangle your qubits. So actually, we are building, at this moment, universal incoherent machines. So we are building incoherent D-waves, but they are universal. So there is an absolute need, okay, in improving the physical properties of our system. So as you know, so for instance, a lot has to do with fabrication. So Abu Dhabi is a new place, so we made a clean room that we are not doing any other thing to avoid cross-contamination. In Singapore, we had a clean room. It got cross-contaminated. It's a mess. We have to replace the evaporator. So, and that's an expensive, and in particular, delay in time. You know that there are many people, the guy, Quantware, he's obsessed with analyzing niobium, titanium. This is a chip that we are doing at CQT, 10 qubits. Now, all the connections are being changed to indium, okay? And so on. So every day, there is a progress to improve these things. Yet, there is no way, I mean, in average, all the chips have coherence times of less than 40 microseconds in general. There is a well, as you know, Nakamura was the guy who first made this qubit in '99. He himself has reached 400 microseconds, but in the chip he's producing, out of 64 qubits, it's less than 50 work. It's not on, the yield is, they don't even have a chip that works all together. So it's extremely difficult, okay? So if we don't fight the coherence, there is no meaning in the number of qubits. If we don't find the crosstalk or any other source for the secret fidelity, there is no meaning. And if we don't manage a relevant scaling, there is no meaning to call in all these quantum computing. You know, there are really experiments which are very peculiar, like the cosmic rays. Okay, cosmic rays now apparently, well, they break the Cooper pairs, and you're done. Okay, so there are not that many, but if we go to larger systems, that it will be an obvious source of problems. Okay, so we are conducting another experiment in the mountains of the Pyrenees down to analyze in detail the effect of cosmic rays in this. Okay, I think this is everything I wanted to say.
Thank you.
Thank you. That was a great talk, from saying that quantum computing is here to saying all the barriers. It was a very honest and clear talk, and I really appreciate it, not to mention impressive. So I've been reading about neuromorphic computing, and I was extremely intrigued by the end when you talked about the energy, and that's why they're selling that. Are you working on that, or do you know of successful approaches?
Actually, the last member of CQT that has come is a woman, Alexia Ofrèvre from Grenoble, and she's only on that, and she's building on a manifesto along these lines for the planet, and there are many people joining, and yeah, it's one of the new lines of CQT is exactly this one.
But you're actually looking at possible devices for new
So there are two
materials?
things. One is the theory, so this is thermodynamics, quantum thermodynamics, let me call it like that. And the second is that we are trying to do an effort in photonics. Okay? In
Thank you
photonics.
very much.
Yeah.
Please.
Yeah, they're coming.
Thanks, very nice talk. Just a quick question. You mentioned right at the beginning there is a tension, or let's say competition between two contrasting requirements, having non-coherence and interacting. And now, in your view, it seems that ions are the best, let's say, for this kind of, for fulfilling this condition. But now, if it is so, why there are still people using other, let's say, technologies?
Yeah, let me be super honest. I had to choose the platform in Abu Dhabi, and I chose superconducting currents, okay? Because although at present ions produce better fidelities and better results, and they have very, very many nice things, they are limited in size, okay? So to be more precise, IonQ, Chris Monroe, probably you know, Maryland, what he is doing now is a chip of 23, but the next is 32 qubits that they can talk to each other, and as I said, many at a time. In 18 months, he is promising to sell machines, no cloud access, sell, okay? That would be the following. There would be machines of 32 qubits, and they will define 32 as the block size of the number of qubits, and then another 32, whatever number of 32s, controlled separately. And now they can move them, you know, this was an experiment many years ago, they can move them, talk, and take them away. And from then on, you can do whatever swap, okay? So the idea is, in ions, they are levitating, they are 32, and on the chip, you move them, you approximate, you take them away. On top, you have to read them. And read out is very difficult. On top, it has to work forever because you're serving the community. They claim that they will be able to upload the ions in 1 minute, and they will sustain the performance for a month. That's a claim in 18 months. Technical, and he claims, is one of the guys who says, this is engineering. I do have my doubts. Now, on superconducting qubits, we have a lot of challenges, and you guys know better than me, okay? We should maintain these superconducting currents, no matter all the things which are going into them. And we have to keep them on the tight control. The big problem is that they are very sensitive to magnetic fields, and immediately you have crosstalk, immediately. There have been ideas which are very clever, like making 2 qubits and putting a 3rd qubit, which is dumb, but it makes a quantum barrier between them. I love this kind of idea. It's so different. So that's the idea of Google. Okay, you know they put 54 qubits. One didn't work, but there were 54. There were 80 qubits separating the other, pushing down the crosstalk. There are other ideas, like also IBM, of annealing. They call it annealing, burning the Josephson junctions so that they are better and homogeneous. You need homogeneity. But when I look at superconducting currents, I see continuous progress myself. And they scale well. Then you can scale, okay? It's my bet. There are other people, and I know other people that are with big pockets. They believe that the solution will be photons. Photons do not interact. So this idea of psi-quantum, of making a state, which is a cluster state, probabilistically, but then you know exactly who is entangled with whom, and now do a series of operations which are measurements, and this is the one-way computer philosophy that was many years ago. They claim that this is the way to go. As a matter of fact, there has been 0 papers proving that. I understand it's secret. And they claim that they will only come public when they have 1 million qubits. What can I say? I mean, look, it's like playing poker here all the time, no? I mean, I'm familiar with MV centers. I don't think they will get anywhere in the short time. I think they are fantastic sensors. Cavities, I think they are creating cut states as qubits. Wow, making an interaction between 2 cut states is really a mess, really a mess. I appreciate a lot what is going on in neutral atoms, because as you know, with tweezers now they can do anything. They can move them, put them here, put them there. We have in our team, Huan Chan, she was in one of the lectures. Huan Chan has managed to have hundreds of atoms, and she has drawn the Merlion, which is the symbol of Singapore, with tweezers. I mean, wow, that's impressive. Yet, interactions on the control, we have not gotten any. It's a complicated situation, and you're putting a lot of money, a lot of money, you know, just buying the fridges and the electronics. I just counted, the cost nowadays of a machine per qubit is $30,000. 30. So if you go to 60, it's 1.8 million. Given that you have already a lab and you have everything, okay? Just the cost of going for that chip. So it's heavy. Yeah? Yeah.
I mean, it seems to me that as electrical engineer, I can recognize that, practically speaking, implementation of Scholl algorithm is a kind of a dream, but not exactly implementable. So from that point of view, we always see that we have to face small quantum chips embedded among massive classical chips.
Mm-hmm.
And looking into that, so then we need to partly give up orthodox approach to a quantum computation, right? And we can think about hybrid solutions. And could you see, for example, combination of rapid single quantum flux electronics as implementing classical chip, plus interface with flux superconducting qubit or with transform qubit as a solution?
Yeah, you are fully right. So Shor's algorithm is far in the future. Therefore, and now we work tomorrow to do what? Okay, so let's forget Shor. So this was the name of NISQ era, the near intermediate noisy computers, no? Noisy intermediate quantum computers that Preskill put forward. In the NISQ, there is a fundamental idea, which is with the few qubits you have, do a variational quantum algorithm. And this is massively done. What you're saying is I think, if I understand well, is a more subtle thing. Let's look at the problem and let's try to combine everything we have. So this is, for instance, what a company called Horizon is doing. They take your problem, they look at your problem in detail, and they see what are the bottlenecks. And only in that bottleneck, they accelerate it. So they make very small calls. But hopefully, this is enough to accelerate the whole thing. And this, as I said, is a big, they got $12 million, just people that do that on a software piece. I see this coming more and more, and the fact that now quantum computers will be in the supercomputing centers, I will see this more and more, okay? How far you can combine the two things. Many people say that a quantum computer will be only a QPU. You will have CPUs, GPUs, you have TPUs for tensor product units, and you will have QPUs. But the real thing will be done centrally and only making selective calls. And I agree with this philosophy. I think it's the future, yeah. Well, meromorphic was also mentioned, no? So now the future of supercomputers is not a unique solid thing. It's an extremely diverse machine, okay? That depending on the problem acts in a different way. So I think there is a lot of thinking in the HPC community how to integrate quantum inside. There is another piece which I didn't mention, which is cybersecurity. Cybersecurity is critical for every country. Quantum is essential there. And you may see protocols added to classical computation to authenticate, or to share a key. So you may see mixings which are unexpected as of now. Well, you may have distributed computation nowadays. You may add layers of quantum to secure it. Again, so computing mixes with quantum, but in a different way for a different purpose. So it's quite a hectic moment, I would say.
Thank you.
Thank you. We are behind schedule. I know there are questions, but maybe we can continue. You can continue after the session. So we thank the speaker. Okay. Okay. Now we are starting.
Hello, Ivan, are you online? Okay. Nice to see you again.
Yes.
Sorry, I don't have
Thank
a
you.
nice voice. Okay. Well, we have 3 chairs, so one you will be chairing from Brookhaven. So Herman and Ali Bozbey together. My voice is not very good. Please carry on and make your comments and suggestions. We will start the closure session.
Should we start right now or wait a little?
I think we have enough people in the audience, so we can start.
Okay. Okay, so let's see. Can you allow me to share the screen? Well, I was scheduled to talk first, and then Professor Davor Pavuna was supposed to be next, but he is on his way to airport right now, and he asked me to actually cover for him. So I'll try to combine what the two of us had to say into one thing. It was a difficult task because the conference had 4 parallel sessions, so clearly I couldn't listen to everything, and you will see that some of these things were added in the last minute, literally, like talk of Professor Haiku Van was just before this plenary. So this may not be as coherent as I would like it to be, but I'll do my best. So one thing that a number of speakers pointed out in the high TC line was that we all believe that the high temperature superconductivity in cuprates is an important problem, perhaps the most important problem in condensed matter physics today. And by the high TC problem, what we really mean is what is the origin of the high temperature superconductivity? What is the microscopic mechanism of high temperature superconductivity? But one can debate even whether it is an open problem or not, because quite a few people have claimed from as far back as 87 January or February is to have solved the problem. And the problem is that there are hundreds of such proposals, and they are orthogonal to one another. So not all of this can be true. Now, at this conference, probably because of the great, fantastic location and the great food and interesting program, the atmosphere was non-confrontational, unlike in the early days of high TC or say in the Bell Labs. But while we can have different opinions, you know, and still be friends and sit together, the ideas actually clash. So the explanations that were proposed, and there are only some of these that I've listened here, are actually not compatible with one another when you just give it a little critical look. So part of the confusion or disagreement may be in the semantics, and this question was raised by Professor Sunko earlier. So I'll try to define, you know, at least how I use these words, and I'm trying to follow the majority, the crowd, when it comes to semantics. So a BCS theory or orthodox BCS theory is the theory as formulated by BC and S. And if I want to be generous, you could include Bogolyubov and Migdal and Yashberg and Gorko and so on. The characteristic is that it starts from a Landau-Fermi liquid theory, and then you add a weak retarded electron-phonon coupling that produces a weak pairing interaction, and it causes an instability in the Fermi liquid below some temperature, at which two things occur at the same time: electron pair and condense. Now these pairs are large. They are in K-space, they are entangled, and they wrap very densely. There are very many pairs in coherence volume. And since they are all entangled, in the density of states appears a collective gap. And it's collective in the sense that it depends on how many pairs do you have. If you break pairs, then the gap shrinks. Now, you could formally replace in the same formalism phonons by some other bosonic excitation like excitons or magnons, and that was done long ago. But there are some problems. One is that in superconductors are metals in normal state, and in metal there are no excitons. When you create an excitation, you excite an electron, you leave a hole, but the electron goes one way and hole goes the other way. However, Ginsburg argued 60 years ago that maybe this could still work at metal to semiconductor interface. The electrons that are next to the surface could interact with excitons which are right on the semiconductor side. However, this was never observed experimentally in a convincing way. And then we have the BC theory, which starts from small electron pairs that are compact and behave, and they are far from one another, so they don't overlap. Therefore, they behave as bosons. What is characteristic here is that to have that, you need a very strong unretarded pairing interaction. Then you will have a local bound pair state. So the gap, the pairing gap that you will see in the spectroscopy and density of state is actually property of individual pair. It's local rather than collective, which means that upon pair breaking, the gap will not shrink, but it will fill in from the bottom up. And you will have pairs present well above the coherence onsets at TC in the system, and you have server gap, etc. And again, this was never observed experimentally in very convincing to everyone. Now we have also this BC-SBC crossover, and the idea, I think, was probably first proposed by Eagles, but more powerful, influential work were done later by Tony Leggett and Philippe Nozier and Schmidt-Rink. And more recently, this was pushed by Mohit Randeria and Kathy Levin, and experimental by Neil Harrison. There was a PRL-sponsored talk very recently about experimental data that favored something like that. Now, this is another, and one axis. The other one is, Fermi liquid versus doped mode insulator. What is doped mode insulator? How do I define that? It's a somewhat fuzzy notion. Actually, Bob Laughlin, who is generally recognized as one of the best and the brightest in the field, even by Phil Anderson, was arguing that mode insulators do not exist at all. So they exist in paper, but not in nature. So what I mean by that? Well, there is a 2D Hubbard model where we start from something that looks like tight binding, but then we add ad hoc by hand a large on-site Coulomb repulsion U. And this has to be large enough. I mean, in mathematics, you can make it infinitely large, but the point is it needs to be larger than the bandwidth, the width of the relevant electron band, and then this becomes the dominant energy scale, and the behavior changes quantitatively. Now there are two leading contending variants, single band, 3-band model. The single band model in simplest variant has just a square lattice, and you have a hopping integral T, and then you have exchange J, and that's all you have. The experimental support for that is that according to ARPES, in Lanthimos-Cupra there is really one band that crosses Fermi surface, and there is only a single Fermi surface. But then experimentally, again, more than 30 years ago, beautiful experiments by Jörg Fink at Karlsruhe using electron energy loss spectroscopy, he showed that holes are actually not sitting on copper, they are sitting on oxygen more or less. Or at least 80% of the whole spectral weight was coming from oxygen. And that means that in this plaquette where you have coppers and oxygen, there is a hopping integral matrix element which is hopping from copper to oxygen that is actually crucial. And that's a justification for 3-band model. It doesn't have to be a hover. You can do a 3-band tight binding model, but what I'm talking about multi-insulators here. So to make it a 3-band hover model, again, you add this large U to it, and it has to be dominant energy scale. And you can voice many reservations about this model. First, that it is ad hoc. The Drude model and Landau Fermi liquid theory were theoretically justified by starting from exact Hamiltonian, which we know, we just cannot solve it with 10 to the 23 electrons. But you could do some mathematical trickery, which Landau did, and to show that in some approximation, when you're coming close to the Fermi surface, then you have this theory. Nothing like that was ever done, to the best of my knowledge, to the Hubbard model. So it's a toy model, it's an ad hoc model. It ignores phonons, it ignores the ionic charge reservoir. When you allow it to be doped, it is not even thermodynamically viable. As you add more and more charges, if you make the system infinite, the energy will go to infinity. And then we have this issue of multi-layer cuprates, where certainly there are more bands. They are coming from different layers. And in a beautiful talk by Xinjiang Zhou, he showed very clear signatures of band hybridization. In a bilayer Bisco, you have bonding and anti-bonding bands. And if you have tri-layer, then you have 3 of these. Now, question is whether this is essential or it is just a complication. And people who push the single band Hubbard model or 3-band Hubbard model, they would say it's just a complication. So you don't need that to explain high TC. Now, what do experiments say about this U and J? Well, Seamus Davis showed a beautiful experiment where he was using STM, scanning time microscope with a superconducting tip, and was monitoring the pair tunneling. It was incoherent pair tunneling, not a Josephson tunneling. And he inferred from that somehow the superfluid carrier density, and also from the spectroscopy inferred the value of the charge transfer gap. And then he found that the superfluid carrier density determined this way scales with the charge transfer gap, and therefore it should scale with J. Amit Keren, in his talk, presented evidence that in his material, which name of which I cannot even pronounce, is that TC actually scales with J. And there was a little bit of debate. Seamus was saying TC is not a good proxy for superfluid carrier density. I don't know what he meant by that, but what we know experimentally is that TC in fact scales with superfluid carrier density. And to the extent that if you tell me the superfluid carrier density in your sample, I will tell you what TC is, and You don't even tell me whether it's lanthanum strontium cuprate or YBCO, whether it's underdoped or overdoped. But there are some more caveats. One is that in lanthanum strontium cuprate, when we go from optimum doping to all the way to the overdose side, there is very little change of the C-axis lattice constant and in-plane lattice constant and the copper to apical oxygen bond. So this hopping integral should not change actually. On the other hand, if anything, the charge transfer gap shrinks if it doesn't disappear. Experimentally, we can a better way to measure J is to look at the paramagnon spectrum at pi over A, and that was measured by Mark Dean in LSCO films by grown by LMB. And what was found is that the spectrum actually didn't change from undoped lanthanum cuprate all the way to metallic and non-superconducting LSCO. But at the same time, both TC and superfluid carrier density decrease, and they actually disappear. They go to zero at the critical doping on the right-hand side of the dome. And the second thing is that, second caveat is that superfluid density is not equal to the pair density. How do we know that? Well, there was this shot noise experiment by Doug Natelson that showed that incoherent pairs are present in lanthanum strontium cuprate at temperatures much higher than TC, and more shockingly, at energies which are twice or more above the superconducting gap energy. And that means that the superfluid carrier density is not equal to the pair density. It's much smaller. And then the third thing that also falls from various spectroscopies is that upon pair breaking, the superconducting gap does not shrink, it fills in. And altogether, all this that I have just counted, it looks certainly much more like BC than like BCS. But I want to emphasize that it is definitely not a standard BC either, because in that theory and in any two-fluid model, at zero temperature, you have quenched all the excitations, so all the normal state carriers must be in the superfluid. But that's not experimentally the case. So any two-fluid model failed. And in fact, actually any mean field description failed. Now, another point of controversy was, are cuprates homogeneous or inhomogeneous, phase separate? And certainly some of them are very homogeneous and can be phase separate. But the question is this necessary or is it just, complication? In other words, if you just want to explain the theory of high T, the mechanism of high TC theoretically, can we just work with a homogeneous, one band or two band, three band model, or we need to build in the phase separation from the beginning? And experimentally, what was shown at this conference was by Seamus Davis is that while pseudogap is very homogeneous, actually it varies on a scale of a couple of nanometers, and it can vary by a factor of 2 or more. However, the superfluid measured by in the same sample with the same technique is actually quite homogeneous. Now, the STM scale is typically, 100 nanometers or less. But my group has shown multi-inductance data showing that in the best lanthanum strontium cuprate films, the variations of TC are less than 0.1 Kelvin out of 40, which is less than 0.2%. And that's on the scale of 1 centimeter. Just to show some figure, okay, these are raw experimental data. They were not even normalized by dividing the transmission to that of the substrate, and you can see that the sharpness of this peak is like a fraction of a Kelvin, and if we had two parts with TC differed by more than 0.1 Kelvin, then we'll see splitting of this peak, which is not seen. So what's the grand total of all of this is that in my judgment, the problem of high TC in cuprate is still very much open, and it is still very much important. Why? First, because it's a challenge, like climbing Mount Everest or solving the Fermat's last theorem. The second is because if we really understand it, that would definitely advance condensed matter physics to a new level, and it may even spill beyond condensed matter physics. Remember, the Higgs boson, was actually following the idea from Phil Anderson on broken symmetry and Goldson mode, and Goldson mode acquiring the mass, which Higgs acknowledged himself. And last but not least, once we understand what's going on in cuprates, that may hint to us at where to look for room temperature superconductivity. RTS now needs to be replaced by a different acronym. Maybe we should say RT PS or AS for room temperature and pressure superconductivity or ambient superconductivity. We have room temperature superconductivity, or at least reported in hydrides, but only at millions of atmospheres. What we really are looking for is something at 1 atmosphere. But so far, theory did not really help much in predicting where to look and discover higher TC at ambient pressure. So how to move forward? I think for theory, I would encourage theorists to be bold and throw some crazy, far-fetched ideas about where to look at higher C based on, plausibility arguments. New ideas in this field have been very scarce. So some theorists long ago proposed that nickelates should be high-temperature superconductors, if doped properly, to look like cuprates. And indeed, after some couple decades, it was observed, not high TC, less than 10 Kelvin so far, but still something. On the experimental sides, I think first and foremost, we need to push the technique further. And there were at this conference several beautiful examples. Xinjiang Zhou showed spectacular advances in laser-based ARPES, pushing the resolution from 5 millielectron volts down to less than a millielectron volt, perhaps 0.1 millielectron volt, and then measuring at 10 millikelvin dilution for each spin result, time result, and so on. Seamus Davis showed STM with a superconducting tip operating in a dilution fridge, and Haiku Van just some hour ago showed spin polarized STM measurements, and these are new types of measurement, new hardware, and it's spitting valuable new information. Now, downside to all this work, if you look carefully, is that they were still working with the same old tired BISCO, after more than 30 years. That's because it cleaves, and you can do STM, you can ARPES, which are surface sensitive. But we need much more. How do we get there? Well, one path, which may not be the simplest, would be to integrate NB and ARPES or NB and STM. And then you grow by STM, and under UHV transfer it to ARPES or STM. I proposed this in 92, but it was declared crazy. Actually, as recent as 2010, our proposals from BNL to build the NB plus ARPES plus STM system were turned down because referees will say it's impossible, it cannot be done. Nevertheless, Davor Pavuna, who is regrettably not listening to this, followed this suggestion, and in late 90s built a PLD system integrated with ARPES at the Wisconsin synchrotron. And then a few years later, he built a tabletop one at EPFL in Lausanne. And they produce some in situ interesting ARPES data on LASCO, for example. Now, our BNL proposal was finally funded in 2014 or 15. And then within a couple of years, we built it, and it's working beautifully. There is a MBE machine and ARPES and STM all coupled together. And at Yale, we have something else, MBE integrated LIM, PIM, and LEAD. And there are, by now, dozens of MBE plus ARPES systems or MBE plus STM systems built in US, in China, Taiwan, etc. Some combine all three, some add PLD, some add sputtering, some add other analytical tools. The fashion has changed. If you talk about quantum phase transition, I underwent one from being obviously wrong to being obvious. By now, if you propose to build a new ARPES or STM system without NMB system, people will say that's crazy. Just not to be showing, just to show some pictures, not just words. Okay, so this is how these things look like in real space. And some people would argue these things are expensive. So this first MBE system cost maybe $5 million. But I would say, while they are somewhat complex and expensive, per Nature paper, they are 100 or 1,000 times less expensive than a synchrotron or than a collider. We need new quantum materials. What has been done? What was being reported here? Well, I was following mostly the high TC line, so I cannot comment about non-superconducting materials, but certainly in terms of new high-temperature superconductors, there was not much. Maybe a couple of USOs reported in the last couple of years. So clearly much more effort is needed. And I understand very well that that is a high-risk endeavor, and so should the funding agency understand. You can spend years and not find anything, but we cannot afford not to look. The potential rewards are very, very high. We could argue that significant new advances have been made in synthesis of artificial metastable metamaterials like heterostructures and superlattices. This is one example, is this lanthanum-strontium cuprate, lanthanum-strontium superlattice. This is new, and you can argue that's a novel metastable material, and it's high-temperature superconductor. It brings in some interesting new physics. What is the importance here? The ARPES and STM are surface-sensitive techniques, and we know from Material Science 101 that every ionic material will reconstruct at the surface because the Madelung cohesion energy is long range, and the surface is seeing half of Madelung energy from the middle of the sample. Therefore, lanthanum, strontium, cuprate, YBC, etc., they all reconstruct in the surface. And this reconstruction is not seen in the bulk. So bulk is different from the surface. Now, in heterostructures, we can bury the interface, and we can bury it between materials which are ionic with similar charges, and thus one has a chance to make these interfaces perfect if you pick up your materials right. And therefore, we can be seeing, like in SAS tunneling, we maybe see something which is more extrinsic and not affected by surface schmutz. So what's the take-home message to the young scientists who will inherit the world? Well, first, trying something new. If you keep doing the same and you're using the same and with the same, then most likely you will get the same. In Alaska, they have a proverb, if you are not the lead dog, the view is always the same. Then the second message is trying something risky. This is a quote from American baseball star. You miss 100% of the shots that you don't take. And then the last one is that science is a marathon, and turtle will beat Achilles in the long run. So never throw in the towel. Thank you very much. That's all.
Thank you, Professor Bozovic. Our next review is about magnetism and magnetic materials by Vladislav Katev. We have a slot for questions, but if you like, we can. Okay.
Ivan, can you hear us? Please stay connected because we will have a few comments or questions at the end.
Yeah, I was just switching off my video so that it is not projected on your screen, but I will stay online till the end.
Okay, fine. Thank you for the nice summary.
Arrived at this site, I found about 250 oral talks on different topics at this conference. And so I was a bit frustrated because it's not possible to a single person like me, for instance, if just to focus only on the talks related to magnetism, to overview all of them, because I also interested in the talks on superconductivity, for instance. So nevertheless, so it doesn't work again. No. Okay, so nevertheless, so I noted in my notebook, so about 36 talks, which I would be interested in. So from these sections present in the conference on topologically protected spin texture, interplay superconductivity magnetism, cryogenic magnum spintronics, complex oxide materials, van der Waals materials, and finally novel spin-dependent phenomena in two-dimensional materials and heterostructures. I failed to attend some of them because of the dilemma of the parallel session. It was not possible. But nonetheless, I got some subjective impressions, which I would like to show you in the next, say, 5-7 minutes. So there are trends visible in this conference, trends of research which can be grouped in 4, say, sub-subjects. One of them, what I call so natural bulk magnets, so that means these condensed matter solids, three-dimensional crystallographic structure, three-dimensional spin structures, big single crystals of different materials. The other extreme are artificial magnetic heterostructures. So this is a deposited or thin or monoatomic layers of magnets, bilayers, trilayers, or heterostructures of different kind. Somewhere in between, so there are so-called van der Waals magnets, which in some sense, so they exist in the bulks as bulk crystals, but they, in many cases, can be considered as natural heterostructures by virtue of the very weak van der Waals coupling between the magnetic layers in these kind of materials. And of course, a very interesting part of this conference was research on hybrid superconducting ferromagnetic systems. Because, well, actually, in this part of research, two most fundamental phenomena in condensed matter physics, superconductivity and magnetism, were brought together. Well, but just I want to show my personal impressions, just a few examples, say, from research on natural bulk magnet. There were several very interesting for me presentations. One of them, for instance, on this material, manganese silicium telluride, where it was shown a very interesting kind of colossal magnetoresistant effect, which is not related to the full polarization of the spin system, like for instance in the double exchange manganites, but it was argued so that a very strong magnetoresistant effect in small magnetic fields far away from the saturation magnetization is due to a novel kind of interaction which is caused by so-called chiral currents on the atomic scale, probably existing in the transition metal oxygen octaeders. A related, or more or less related, theoretical work on the chirality problem on the chiral soliton lattice was discussed in the talk of, in this talk presented by Bastignori from Spain, where the phase diagram was proposed where the chiral spin lattice could be controlled either by magnetic field or also by the applied current. And it turns out that it was predicted so that this chiral spin lattice could turn, it has a certain phase stability area, but it could be turned to the fully forced ferromagnetic states either by application of a stronger current or a stronger magnetic field beyond the critical value. But surprisingly, also when it increases the current further, so the ferromagnetic order is surprisingly destroyed. So possibly due to the enhanced spin fluctuations, so spin waves in this particular regime. So also there were some presentations, one of them given by Gabriela Aurel about this very interesting magnetoelectric material, calcium, strontium, barium, copper oxide, where two order parameters, the magnetic order parameter, the ferromagnetic order parameter, and electric order parameter were brought together, and that, of course, causes some interesting new phenomena which were discussed in this talk. So now coming back to the artificial magnetic heterostructure, so skyrmions were omnipresent at this conference. In early form, in most of the talks, skyrmions or other topological magnetic structures were present and discussed. And there was an interesting visible trend in these presentations focusing on manipulation and control of these topological spin objects with electrical current. In the multi-structures composed of this, of the ferromagnetic material where skyrmions or say domain walls or magnetic bubbles could be generated and manipulated by the currents which run through the deposited, say, metallic layer or stripes with strong spin-orbit coupling, like for instance platinum. That was very nicely overviewed, I think it was today or yesterday, maybe today, in this plenary talk by Pietro Gambardella on manipulation of chiral spin textures, and related talk by Saul Feliz on this current-driven dynamics of Néel domain walls. Well, also manipulation of the skyrmions in 3 layers. So this kind of magnetic 3 layers was highlighted in the talk by Karen Evershaw-Sitte today on how one can control, for instance, the skyrmion Hall effect to enhance it or suppress it and to manipulate with this kind of interesting transport phenomenon. One shouldn't forget, so another interesting theoretical presentation, because, so you see, so this conference is on quantum material, but also on quantum technologies. Therefore, the people that start think on not only some fundamental understanding of this magnetic phenomena, but also on possible future technological application. And one of those was presented in the talk by Andrei Slavin, who proposed a very interesting concept of a generator of monochromatic terahertz waves. So actually, at present, so generation of terahertz radiation, in particular monochromatic radiation, is a big problem. And this concept suggests to make a bilayer structure of the conductor. So this is platinum conductor and a conventional antiferromagnet nickel oxide. And so by running the current through platinum, so generates a spin torque, which generates monochromatic terahertz radiation in this antiferromagnet. So next, actually, so this is also one contribution about the stabilization not only of the skyrmions, but also on the antipodes, so to say, antiparticles, so antiskyrmions, given by Timo Schmidt from the University of Augsburg. So there were also materials presented in this conference, which itself are not magnets, but so they provide interesting spin phenomena. And one of those presentations, which I liked very much personally, was the report on the spin life anisotropy in ultra-thin black phosphorus given in a plenary talk by Ahmed Afzar, I think on the first day of this conference, where it was found that, for instance, the spin transport is very anisotropic in this material. So it's very different if it runs along the edge, along the zigzag edge or along the armchair edge. And more importantly, it was found that the spin relaxation length in this single layer of black phosphorus is extremely long. It amounts to several microns, which is really a very spectacular observation. Another kind of heterostructure where these chiral interactions were considered and experimentally observed is a multi-layer built out of a ferromagnetic strontium ruthenium oxide separated by thin layers of non-magnetic strontium titanate. The magnetic structure of this multi-rate was revealed to be of the spiral character, and it was argued that this is a novel kind of phonon-mediated interlayer exchange which gives rise to these non-collinear spin structures. So, coming to the other research areas, so these quasi-two-dimensional van der Waals magnets, several of them were presented in this conference, and there was a very interesting plenary talk given by Aguj Gulzaren on the magnetic properties of 2D layer materials, where a family of these transition metal ion carbides or nitrides were presented and classified with the aid of the density functional theory, classifying them into having, say, ferromagnetic order state, antiferromagnetic order ground state, and the kind of anisotropy easy plane or easy axis. So that was a very interesting presentation. But there were also really a series of interesting experimental talks. One of them that was a today talk, an overview given by Man Hong Fan on the exchange bias and on the interface related effect in the two-dimensional van der Waals magnetic heterostructures, which is important in two aspects. The one is that one could, the one important aspect is the generation of this exchange bias, so that means the shifting of this hysteresis curve in the desired direction in this, with regard to the zero magnetic field. This is important, say, for the memory storage devices. On the other hand, the enhancement of the critical temperature of the van der Waals magnet, it was shown, for instance, a very spectacular enhancement of the critical Curie temperature of the vanadium diselenide, which was put on the substrate of molybdenum sulfide. And so the temperature, the critical temperature was raised up to the room temperature, and it was shown, so a very nice hysteretic magnetization curve measured at 300 Kelvin. So also a combination of, say, of non-trivial conductor, which is a graphene, with magnetic van der Waals material like, for instance, transition metal dihalcogenates, was illustrated in a talk by Juan Sierra from the Catalan Institute for Nanoscience and Nanotechnology, where they found that the spin currents generated with the aid of these ferromagnetic electrodes on this stripe of graphene can be manipulated by the layer of the transition metal dihalcogenide in the presence of the applied magnetic field, where one can change at will the spin polarization of the cardon from the out of plane and turn it to the desired angle depending on the field strength applied to this interesting, to this bilayer structure. And in this case, of course, so the anisotropy of the spin lifetimes was found, and it is very strong for certain experimental conditions. One particular material from this family of quasi-two-dimensional van der Waals magnets has attracted special attention, and that was chromium germanium telluride, because of its robust ferromagnetic order, even in the few layers limit, which is not very often found in this kind of materials. And for instance, so this specific very useful property was used in the Josephson junction structure discussed by Hiroshi Iduchi from the University of Tokyo in Japan, where they succeeded to fabricate a structure which shows a very unusual Josephson effect. So the superconducting part was made out of niobium diselenide, so this is a non-heterosymmetric superconductor with a strong spin-orbit coupling, and it was observed a very interesting tunneling of the copper pairs with an unusual phase shift. So actually, they also found a very interesting phenomenon of enhancement of the critical temperature of this material deposited on the special tensile substrate, which expands the crystal lattice. And actually, so by definition, I had to attend my own talk on this subject, where we reported on the pressure-dependent change of the magnetism in this material, namely the suppression of the ferromagnetic order by applying a compressive strain. And therefore, that was a really good interplay with the results of Dr. Iduchi, where they found so that if one expands the structure, so the ferromagnetic order gets more stable. Another interesting, so to say, application of the single layer of chromium germanium telluride was discussed by Klaus Zollner from the University of Regensburg in Germany, where he showed so that when this layer is put on the graphene layer, and the twist angle between these two layers could be changed, it leads to a very interesting change in the band structure of the graphene. So where this Dirac cones could be gapped, and this could change. So this is the topology from the trivial to non-trivial and back. That was in fact very interesting functionality of this chromium germanium telluride layer. So last but not least, of course, so this is a hybrid superconducting ferromagnetic system. So in this case, actually, in my opinion, so the magnets, they play a secondary role, because the most focus is to find the most interesting spectacular phenomena in the superconductor, like, for instance, topological superconductivity, the emergence of the Majorana fermions and Majorana modes, but also a feedback from a superconductor to the magnet was actually very interesting. And that was nicely demonstrated by the plenary talk of Roland Wiesendanger from the University of Hamburg, where they showed that, for instance, they build up a spin chain of manganese atom by atom on a layer on the surface of the superconducting niobium. So this is the chain, and so they studied the electronic structure of this chain. And it turns out so that that due to the hybridization of the electronic state of the superconductor with the electronic state of the magnet, so under certain conditions, a special modulation of the electronic structure in the magnetic chain takes place, and more importantly, so a coherent states at the end of the chains are formed within the superconducting gap. And so actually the idea is to move these states to the close to the Fermi energy to realize these Majorana bound states. So another interesting superconducting ferromagnetic system was actually, in my opinion, again, a superconducting Josephson junction made of high temperature superconducting, YBCO, separated by a very thick very thick layer, ferromagnetic layer of lanthanum strontium manganese oxide. And still, so the thickness of this layer was extremely large, so there was some microns, but still they could nicely observe a Josephson effect on this kind of system. So this is really a very interesting experimental observation. One more presentation, more in the direction of the technological application, were more hybrid structures made of ferromagnet, platinum, and a superconductor. So the idea was that as soon as one has a vortex state in a superconductor, so this is kind of periodic topological lattice, and if one put it into contact with a ferromagnet, so then if one matches the periodicity of the spin waves excited in this ferromagnet with the periodicity of the vortex lattice, they should interact. And in this work, so this Alexander Dobrovolsky from the University of Vienna has shown that indeed, so they can bring this vortex lattice and the spin waves in that regime where they start interacting. And really amazingly, so if they then apply a current to the superconducting layer and start to move in vortices, they start to move very, very large velocity. And this gives rise to the generation of so-called exchange spin waves in a ferromagnet. So these are very unusual kind of spin waves, which have a very short wavelength, and it was shown that they don't form as it usually happens in a ferromagnet, so the standing waves, which doesn't transfer any energy, but that was a monodirectional propagation of this of these exchange spin waves, which then can transfer energy. So I think so with this overview, I'm at the end of my presentation, and in my personal opinion, and I think so that you will share this opinion, so this conference was a great success, and of course, so then we have to thank this local organization team headed by Ali Ganser for this really great event in the condensed matter community, in the community of magnetism and superconductivity. Thank you very much for your attention.
Thank you.
So I don't think so that you have questions because I just transmitted to you so the results of other participants.
Our next review is about topological superconductivity by Ahmet Avşar.
Good evening, everyone. So Prof. Vladislav have already summarized quite well with the spintonics and also a bit towards the end, the topological superconductivity part. So unfortunately, because of some emergency, I couldn't have chance to really summarize, so I talked to Prof. Ali Genca. So I decided to give a short presentation on something that we have been doing over the last 2-3 years, and it's a kind of a new direction in the field of like two-dimensional magnetism, but this was not covered in this one, so in this conference, so we thought that maybe it could be a good kind of addition. So as I mentioned, we are working with the two-dimensional materials, and now I will be telling you about the story of the material that we are working. It's called platinum diselenide. And this material is a non-magnetic material in the ultra-thin film limit. So by creating some defects, I will be showing you that we can turn this material into a magnetic material. And it has very distinct magnetic properties like layer-dependent magnetism, etc. And this kind of research was not covered in this novel spintonics aspect part of the ICQMT. So I thought that it could be a good addition. So this is a kind of a material made of like platinum and then sandwiched by the selenium atoms. So the material has very, very distinct electronic properties. This material is semi-metal once it has a thickness above 4 layers. And whenever you thin the material down, the material is becoming a semiconductor. And the material becomes a very good insulator once you reach the monolayer. And but one thing that we were quite interested with this material was the materials showing there were lots of calculations that if you can kick out some metal vacancies, in this case the platinum, you could kick in some magnesium in this material. And creating this kind of metallic vacancy in this material is slightly easier because of the lower formation energies compared to the other materials, to the semiconductors, which similar physics was predicted. And the question was like, do we have this kind of defects? So these two-dimensional materials, they are just surfaces. We have lots of defects on these materials generally. And in the case of the platinum diselenide, we had a defect concentration, platinum vacancy concentration of the defect up to 10 to the power 13. And these results were also confirmed by another independent study with some STM analysis that the material is like full of the defects. And we made lots of devices, and nearly the half of the devices that we studied, the material is supposed to be non-magnetic in the pristine form. And we could see the kind of the very hysteretic magnetic resistance in this device, at least the half of the samples that we studied with a Curie temperature around 13 Kelvin. And whenever we were focusing on the other part of the other devices, basically it was showing kind of like a zero antiferromagnetic ground state ordering at the zero field, but whenever we were applying more fields above the coercive field, the material was getting fully spin polarized. So it's kind of an antiferromagnetic type behavior. So what we were seeing is like nearly the half of the device that we studied was giving the response of the ferromagnetic response, and half of them was giving a kind of antiferromagnetic response. And the question we tried to answer is there any layer-dependent magnetism in this material? And for that, we compared the magnetic transport properties of two devices, but with the thickness of 1 layer difference only. And whenever we studied the magnetic transport properties of these devices, and they were showing the ferromagnetic and antiferromagnetic response. So they were just like 1 layer dependent, 1 layer difference in these crystals, and then we were already seeing like completely different magnetic transport behavior. And we tried to understand, and this phenomena was only visible for the crystals less than 14 nanometer, and whenever you go a bit thicker, you don't see any of these effects. And the MR was decreasing, and we had like more detailed studies, but basically what we do see is like in the material, you have like ferromagnetic or antiferromagnetic ground state ordering, and then by just adding or removing 1 layer, the material turns into a ferromagnet. And whenever you go above 14 nanometer, the material becomes a non-magnetic material. And so we explained this with the ICQMT interaction, and basically these magnetic moments formed due to these platinum vacancies is giving the magnetism, and all these thickness dependent measurements are in good agreement. So, and then we studied also if the monolayers and bilayers of these defective materials also magnetic, and we do see like similarly layer-dependent magnetism down to monolayer in this material. And so I'm a material scientist, and we are very interested in manipulating the materials. And one of the things we are quite interested in nowadays is like modulating this kind of magnetism at the ultra-thin limit. So there are lots of predictions by tuning or modulating the defect concentration of the platinum atoms in these defects in this material. We can increase this relatively low Curie temperature of 13 Kelvin to up to room temperature. Or we have also another approach motivated by some calculations. If you can dope your material with the transition metal odd atoms, you can again increase the Curie temperature. And the good thing is like, all the talks that you have seen about with the two-dimensional materials in this conference were from the intrinsic magnets, meaning that their bulk form, their mother form is also a magnet. But this platinum dicyanide and also the other materials that I will be showing, these are non-magnetic in the pristine form, in the bulk form, and you need to thin it down, and then you need to create some defects. And platinum dicyanide is not alone, so there are lots of materials which shows this kind of defect in this magnetism in the monolayer limit. And one of them was just, for example, this was just published 2-3 weeks ago, chromium sulfide bromide, which shows again this kind of defect in this magnetism. And there was also another study on the molybdenum ditelluride, which was also showing a defect in this magnetism up to 100 Kelvin. And we have lots of new candidates and lots of new predictions are happening that if you have these ultra-thin materials and create some defects in them, you can turn many of these non-magnetic materials into magnetic, and some of them are even like layer dependent. The magnetic properties are depending on the layer. Yeah, so this was done while I was working with Prof. Andreschkis at EPFL, but we are now pushing more towards the monoplating, the low Curie temperatures of this kind of defect in this magnetism. And one of the key aspects of these magnets are they are highly air stable, and any of these two magnets that you have seen in this conference, they are very air sensitive, so meaning that if you would just produce and leave on the table, the material would just disappear within few minutes. But this defect in this magnetism that I showed, the material systems, they are highly air stable. So this could be a way of like engineering the magnetism in the ultra thin limits, and they can be integrated with the spintonics devices. So thank you very much, and yeah, so that's all from me.
Thank you. And last review is about the quantum devices by Herman de la Fuente.
Thank you. We had an excellent talk by Professor Jorge Ignacio La Torre before, so I will restrict myself to something very brief, which is to quickly summarize what 3 representatives from 3 companies have said here. And you have this information also in the YouTube channel of the conference. So first, I would refer to Thomas Ortleb's lecture or comments from, he's from CIS, Forschung Institute für Mikrosensorik in Germany. And he claimed he was managing 120 people working from the viewpoint of taking results from science projects into innovative applications. And, but their business core basically was on classical technology. They, however, had 3 activities dealing with quantum technologies, and they were searching for new apps in quantum technologies from what they see scientifically in scientific developments. And basically the first application that he mentioned was a quantum-based gravimeter as a sensor to detect holes and other undesired features underneath the Earth. And this worked in a quantum regime. And it had been proposed by a UK group about 10 years before, but it had been proposed as a 2x2 meter table, optical table solution. And their advancement is that they made this a 2x2 centimeter sensor. And they have the first 150 orders from the German government in order to investigate soil in new development construction areas. The second one that he talked about was diamond-based magnetic field sensor, which is calibration-free in operation, and it's very difficult to manipulate. So they already have 1,500 orders for this, and the main application apparently is in smart meters that detect manipulation from non-specialists. And the third one is on solid-state circuits based on Josephson junctions, I believe. And in this case, their business is related to the system integration, and this is dedicated to the assembly of the quantum system in smart attachments of optical fibers and transmission and packaging and so on. So that's basically, in some way, there are hybrid applications of quantum systems. And he warned also that there's too much hype scientifically, as Professor Alatorre said before, and that we must be careful, that we must find quantum technology applications within the next 2 or 3 years, or at least they should be addressable. And the second speaker that I give you a summary of is Joanna Skiba. She's from Toshiba in the UK, and she talked about their efforts in building devices with applications in quantum networks, and based on the use of entangled photons. And she talked about the development of materials from discovery to manufacturing, and they were using QDATs. They were using QDATs, side control QDATs, droplet QDATs, and side control droplet QDATs, which were the ones that they have been most successful with. And their applications basically were on entangled photon LEDs for quantum internet, where she said that there should be a drastic change in the coming years, for quantum encryption in classical communications, for quantum sensing, and also for remote programs of quantum sensing. And this based on quantum relays as basic elements. They try to reduce the error rate for intermediate distance transmission. And for example, they have I believe, I understood they have demonstrated this entangled photon transmission over metropolitan areas which were of the order of 18 kilometers. So, and their effort is now to expand the capability of quantum communication on intrinsic security, longer communication distance, and higher efficiency. And now to finish, the third participant from the company was Valery Vinokur, and he's from Terra Quantum in Switzerland. And he talked about quantum computing and security. And basically, there were 3 integral areas where he said which they are addressing. One is on quantum algorithms, which is a hybrid technology, quantum computing, which is hybrid quantum cloud and quantum, what they call quantum MWare, and quantum security. So he claimed also that they can basically, I don't know if this is now or this is coming soon, they can secure 100%, so they can make 100% secure storage and communication data. And what they do is they enhance classical approaches in 3 key spaces. One is optimization, another one is machine learning, and the other one is simulation. And I think he talked also about a paradigm shift related to irreversibility, and he gave an example where there's an instant going back in time, and that this is their philosophy, to protect circuits, so or protect transmission. And he also talked, just to finalize, about novel superconducting qubits, which he believed would work at the temperatures of 10 Kelvin. So I think that's more or less what I think was most, probably I left many things out, but I thought that some of them would be, as they were before in the magnetic materials, would be revised from the point of view of the quantum materials development. So I did not want to duplicate that, and I wanted to be as short as possible. So I must congratulate all the, from my point of view, all the organizers of the conference for an excellent job, and thank you very much.
Thank you. Now the session is open for contributions and questions, but before that we have an announcement. We will have a farewell party at 6:30 p.m. at the same place as the welcome party, which is near the terrace bar at 6:30 p.m. Yeah, we have about 20 minutes for contributions from the audience.
Well, I think I took notes, okay? I just want to say a few words because I don't want to take much of your time. There are two issues that I have taken a note. One is that quantum technologies require cryogenic technology. So without cryogenic technology, maybe photonics could be an exception in one of 5 technologies for qubits. And to achieve low temperatures, we need high purity helium gas. Helium is unfortunately very expensive and has become more and more expensive. Even in developed countries, there is a problem of helium contamination. So even if you have very high-tech dilution refrigerator to achieve these temperatures, if you have a contaminated helium gas and you liquefy it with helium-3, it's very, very expensive. And this is another technical issue that some developing countries may have real problems with this helium because they prefer to buy low-cost helium, which cannot be pure helium. The other issue I just would like to say, as a comment, superconductivity prototypes, qubit systems for quantum computation, quantum computers. And Professor Latorre has given a very comprehensive review. This is just a comment that we are still relying on what Brian Josephson discovered as a Josephson junction in 1962. And there are maybe more than 6,000 superconductors have been discovered since then. So Brian Josephson, as a Nobel awardee, let's say, he was an undergraduate student when he made this Josephson junction. So making Josephson junction is not a real issue. And there are purities and impurities associated with the coherence time and decoherence time. So this is, as Latorre indicated, is a very critical issue for the robust systems to be constructed. So I don't want to take your time, but I think this was to be noted in the conference overview, so I just wanted to add these two things. And the other thing, as an organizer, and this has been maybe, I'm not making overstatement, is the history of science and technology of quantum technologies initiated in Turkey with the minimum lowest funding in the area. Ever since the announcements of Nobel Prize just a little more than 2 weeks ago. You made it, and I'm sure this conference will be one of the tops in the next coming years. And in terms of quality of research, and also in terms of participation from many different countries. And the other thing that we must also consider, participation of scientists where science is underrepresented to this conference. And we need those people in the conference. And with the limited budget, we have tried to make this. And we will keep continue supporting people from the underdeveloped world. And with your support, the main income of the conference is registration fees. And hope that we will have many sponsors in the next edition of this conference. And we will keep continuing finding the ways of living in peace in the whole world. Because advances in the technology sometimes may give some big power to politicians, which may ruin the whole world. Thank you very much.
Thank you, Professor Gencer. So I think now it's time for the farewell party, right? Yeah, yeah, we can go together. Not yet, sorry.
Well, we keep going. Well, next conference we have this the Intermag, which is a well-established conference on magnetism, but applied magnetism. I think it's the best time for us to stay in the same venue here. May will be better than October, we say. And in ICSM, we would like to keep maybe more short focused on quantum materials and technologies to keep the overlap minimum. So you are all welcome, and you will probably make it to come again. So this is so I don't have the statistics of the conference. Roughly speaking, we have 308 registered participants, and some of them online. And one thing we did not ask for approval, that all the presentations are now on YouTube. Next time, for the second edition, we will make sure that these will still be on YouTube, but the passport protection will work. So everyone will be able to join the conference, either online or in person, using passport with security measures. So this will be our second contribution to the conference. So I think we better go to welcome party. If there is anybody else who would like to say something. Vladimir, you want to say something? Anybody? Okay, sorry. Okay, let's have Chris, okay.
There was a very interesting talk by Professor Zajkin today on quantum phase slips and fundamental theory of quantum phase slips in some reference to full counting statistics. So that just probably was not fully underlined in the conference summary. Thank you.
Okay, this will be noted, I think. Is it okay? One more? Right.
Okay, I just want to propose that we thank our chair, Ali, and those unsung heroes once again for this very successful conference. Okay. Yeah.